Have you ever wondered why the universe exists at all? Why isn't it just nothing? Today we're going to explore a revolutionary idea, one that challenges our most fundamental assumptions about the beginning of everything. We'll delve into the wave function of the universe, a concept that suggests the cosmos didn't explode into existence from a singular point, but rather emerged from a surprisingly simple and elegant state. Think of it as a cosmic score, a continuous, unfolding story rather than a dramatic, abrupt event. Imagine you could hold not just a picture of the universe, but the instructions for every picture it could have become, like a quiet score that contains every melody the cosmos might play. This is the spirit of the wave function of the universe, and the most helpful way to feel it is to see it, not as misty mysticism, but as an honest bookkeeping device for possibility that obeys the same rules small laboratory systems obey, only scaled up to everything. Start gently. In ordinary quantum stories, we talk about the wave of an electron to summarize where it could show up and how likely each outcome is when we look for the universe. Swap, where with every arrangement of matter, light, and geometry, and you get a grand ledger that assigns weights to entire ways the world might unfold. Those weights aren't guesses. They evolve according to known dynamics and their phases. Think of them as choreography rather than numbers. Decide whether different possibilities cooperate or cancel, because we never experience all possibilities at once. Your natural question is how this ledger gives us the single sturdy reality of tables, trees, and Tuesdays. And the answer begins with environments. Everything talks to everything else. When a tiny system interacts with air, with light, with dust, with detectors, with your retina and your brain, the delicate ability of rival possibilities to recombine is shredded into the world's countless degrees of freedom. What remains is a set of robust stories that no longer interfere. That transition is called decoherence, and it is not a handwave. We engineer it and control it in the lab when we build quantum technologies. In the universal picture, decoherence doesn't need a human to press a button. It needs records, physical imprints that are in principle retrievable. A branch is just a network of consistent records that agree with one another. And your everyday life is lived along one such branch because once enough records pile up, alternatives are effectively quarantined from ever rejoining the narrative. This helps us avoid two bad extremes. We don't smuggle in a magical rule that treats human observation as special, and we don't pretend macroscopic contradictions ought to haunt the kitchen. Instead, we acknowledge that the same evolution that lets a single atom show wave-like behavior also ensures that large, warm, chatty systems rapidly discover a classical-looking domain where chairs don't blur through walls. If the universal wave function is a score, then decoherence is the orchestra locking into a tempo that makes overlapping tunes separate into distinct songs you can actually follow. From here, the concept earns its keep in cosmology. Early on, the universe was hot, dense, and simple in the sense that not many independent records existed. Quantum ripples could still influence one another's choreography. As space expanded and cooled, those ripples stretched and froze into matter and light, leaving fossils in the ancient afterglow we call the cosmic microwave background. The universal wave function doesn't predict one sharp pattern. It predicts a distribution of patterns with characteristic features. We can check how strong the ripples are on large versus small scales, how nearly they follow a scale-invariant trend, how sharply the pattern rings like a bell, the acoustic peaks, and how close the fluctuations are to the simplest kind of randomness. Remarkably, sky maps made by satellites and ground telescopes show exactly the sort of statistical fingerprints you would expect if quantum seeds were laid down and then written into the sky. This doesn't crown a single true initial recipe, yet there remain different proposals for how the earliest boundary conditions were set. But it constrains the family of recipes. Some produce the soup we taste, others don't. To keep the science clean, it's helpful to stress what the wave function does not magically provide. It does not answer why there is something rather than nothing. It does not force you into a particular interpretation about many worlds. It does not give personal meaning to outcomes. What it does provide is a disciplined framework where one evolving object carries consistent histories from the earliest times to now across scales, with no need to patch different laws for different sizes of things. That framework invites concrete questions instead of philosophical fog. Which coarse graining, what you choose to ignore because it's irrelevant at your scale, makes a galaxy behave like a fluid rather than a swarm of stars? Which states of matter and light are naturally stable under environmental chatter, and thus become the pointer states that define the classical apparatus we trust? How does the arrow of time show up as an asymmetry in records more fossils of the past than the future? When the underlying rules treat forward and backwards so symmetrically, the universal wave function also clarifies the role of chance without making it mystical. Probabilities enter as weights attached to possible histories. When similar experiments are repeated many times across the universe, or even just across your lab, the frequencies of outcomes settle down to match those weights. Not because a dice god decrees it, but because that is how the choreography of interference and decoherence distributes records. On human scales, this means novelty is not a sign that the rules broke. It is an ingredient of the rules. On cosmic scales, it means our sky is one drawn sample from a broader distribution. We read it to learn about the underlying score. Just like a geologist reads layers of rock to learn about long-gone seas, some wonder whether speaking of a wave function for everything makes time feel illusory, as if history were a block already carved. But the better feeling is that the score exists while the performance is real. Interactions create records in sequence, and that ordered accumulation of records is the flow you call time. There is a quiet intellectual humility in this view too. When we say the universe is in a state, we are not claiming a hidden absolute picture. We are stating what the best compression of all consistent records looks like at a given level of description. Change the level. Zoom far out to galaxy surveys or far into atom interferometers, and you need different coarse grainings like switching camera lenses. Yet you do not need new laws, and that economy is the whole appeal. In the end, the wave function of the universe is less a grand metaphysical pronouncement and more a promise-keeping device. It keeps quantum rules the same at every scale, explains why classical worlds are the norm where records proliferate, provides statistical targets we can and do measure in the sky, and leaves room for wonder where it belongs. Not in gaps of understanding, but in the astonishing fact that one quiet score can carry a cosmos of possibilities until the world's own music writes them into memory. Hartley-Hawking no-boundary proposal. You've been told to imagine a beginning, fire, flash, a first tick of a cosmic clock. But the Hartley-Hawking no-boundary proposal invites a different picture. What if the universe didn't start at a sharp edge at all, but slid into being the way the surface of the Earth has no beginning latitude, smooth and continuous with no cliff to tumble from? In this view, the earlier stage isn't a bang exploding out of nothing with a jagged seam. It's a rounded cap in which time gently behaves like another direction of space. And then as the universe opens up and cools, that direction gradually turns into the time we experience as before and after. Begin gently. In everyday life, boundaries matter. A wall, a shoreline, a start line, and we're trained to look for them. But physics sometimes works better when you choose initial conditions that are simple and regular rather than abrupt. The no-boundary idea does exactly that, proposing that the best description of the universe's birth is a compact finite geometry with no border to specify, like a sphere rather than a disk with an edge that matters because edges demand extra information. What's fixed there? How rough is it? Which values are allowed? Remove the edge, and you remove the need to invent those instructions. The technical route Hartley and Hawking used to make this crisp is to consider a sum over possible smooth beginnings. Think of it as pulling all the gentle ways space can cap off and assign each a weight, so you can ask which class of beginnings is favored. But you don't need the math to grasp the intuition. A rounded, boundary-free beginning is the most economical way to avoid smuggling in a special, improbable starting state. Now deepen. Why does anyone think this could plausibly match the universe? We observe rather than just being a clever sketch, because a boundary-free start naturally leans toward initial smoothness with small calculable ripples rather than violent chaos. And those tiny ripples are precisely what later gets stretched and recorded as the seeds of galaxies, and as the faint modeling in the ancient light that still bathes the sky. By picking out regular finite configurations at the outset, The proposal explains why the early cosmos looks so uniform across vast distances, while still allowing the delicate imperfections that structure needs to grow. If you want a feel for the stakes, consider fine-tuning. Without a principal beginning, one is tempted to impose extreme smoothness. An exquisitely chosen phase of early expansion can emerge from a cosmic coin toss that happened to land just so. Philosophically, it's both disarming and calming. Instead of a hard origin and an unanswerable why that, why those values, you get a picture where the question softens into geometry. What is the simplest, most regular way for space-time to be complete on its own? And your curiosity can move from inventing border conditions to checking the statistical fingerprints are smooth, start should leave in today's skies. In the end, the no-boundary proposal doesn't close the book on beginnings. It changes the genre from a story about a singular first instant to a story about a graceful turning space curling into time, and then unfolding into the eras we inhabit, so that the universe does not need a place to be glued to or a moment to be switched on. Only a consistent way to be whole from the start, like a globe without edges whose very roundness is the reason it holds together. Vilenkin tunneling from nothing. Suppose the universe did not start in the way a match flares from a roughened strip, but appeared the way a note can emerge from silence. No stage, no lights, not even a room in which to place them. Just a lawful chance event in which a tiny closed seed of space-time slips into being. This is the spirit of Vilenkin's tunneling from nothing proposal. And the first step to understanding it is to clean up the word nothing, because here it does not mean empty space or a dark void you could float in. It means no classical space or time at all. No background on which to draw coordinates, only the rules that govern what is physically allowed and forbidden when gravity is quantum and geometry itself is subject to fluctuation. In ordinary quantum stories, a particle faced with a barrier it cannot classically climb sometimes appears on the other side anyway. Not by cheating the rules, but by obeying deeper ones. What was forbidden for a definite trajectory becomes allowed as a rare event in a world described by probabilities. Vilenkin lifts that logic to the largest scale and says the barrier is having a space-time at all. The classically forbidden region is the absence of a universe, and the rare event is the sudden appearance of a minimal self-contained space-time, often pictured as a tiny closed bubble that immediately expands. The mathematics behind this is a semi-classical calculation that treats early geometry like a system that can explore nearby configurations. And tunneling is the name we give to the path that connects no classical universe to a small classical universe, without requiring a smooth slide through intermediate classical stages. You don't need equations to feel the intuition. There is a ridge separating the landscape of no space from the landscape of possible spaces, and quantum rules give a non-zero chance to hop the ridge. What makes Vilenkin's version distinctive compared with other ideas about beginnings is the boundary condition he imposes. In the space of possible histories, he selects those that behave like outgoing waves, universes that emerge and expand rather than a mixture of incoming and outgoing behavior. This choice is not about human preference. It is a way to tell the theory, pick configurations that correspond to creation events rather than annihilations, and it has consequences. Most notably, it tends to favor an initial state with relatively high energy density in whatever field drives early expansion, which makes the onset of rapid growth. Cosmic inflation, natural rather than delicately arranged. If you start high on the hill, you roll and the space inside your bubble grows fast, smoothing irregularities and stretching tiny quantum ripples so that they later become the seeds of structure. That simple story stands up against a handful of reasonable questions. First, how can you tunnel if there is no place to tunnel from or to? The answer is that from and to are labels we impose after the fact. In the calculation, you compare the weight of a configuration with a classical universe to the weight of the no-class geometry configuration. And tunneling is the name for the dominant path that links them in the space of possibilities, not in ordinary space. Second, are we smuggling in a law to explain the law? After all, if there is no universe yet, what enforces quantum rules? The honest answer is that every attempt to describe a beginning assumes the framework of physics still applies. Vilenkin's proposal is explicit about that. Nothing is a physical state with no classical space-time, but not a state with no rules, and the rules are those of quantum gravity in the regime where space-time can flicker into and out of classicality. Third, does the proposal make contact with observation rather than floating as a clever metaphor? It does, albeit indirectly. By preferring high initial energy for the field that fuels early expansion, it influences the predictions for how strong the first density ripples are, how nearly they follow a simple spectrum across scales, and how curved the large-scale geometry should be. Different beginning prescriptions dial these features slightly differently. So precise maps of the sky's ancient light let us compare families of beginnings and throw out those that don't cook the soup we actually taste. There are, of course, live debates. One concerns how to properly set up the sum over histories so the tunneling amplitude is unambiguous and stable. Another asks how to treat back reaction, the way quantum fluctuations of fields and geometry feed on each other, so that the result isn't distorted by the approximations we use to make the calculation tractable. Yet another debate notes that when you talk about probabilities for the whole universe, you must define what you are counting carefully, because you don't have an ensemble of universes to repeat an experiment. You have a spectrum of possibilities from which our actual history is one drawn sample. None of these challenges sink the idea. They sharpen it. They also help separate the scientific content from the easy misunderstanding that from nothing means a free miracle. In this proposal, from nothing means a lawful low probability transition allowed by the same statistical logic that lets alpha particles escape nuclei or electrons, slip across gaps in semiconductors. Rare but not disallowed. And once it happens, the aftermath is not fragile magic, but robust physics. The newborn spacetime expands. The high energy field rolls, radiation floods the scene, matter condenses, light decouples, and the observable universe inherits the fingerprints of its earliest fluctuations. The proposal also reframes an old philosophical itch. If there were ever truly nothing, not even physical law, then nothing could happen. Vilen's point is not to dodge that, but to choose a definition of nothing that is squarely inside physics. No classical background, but lawful dynamics that include the option of creation. In that sense, it is a scientific answer to a scientific version of the question, and it stays in bounds by tying its claims to features we can try to measure. If you want a feel for the stakes, consider fine-tuning. Without a principal beginning, one is tempted to impose special initial data by hand. Nothing is a physical state with no classical space-time, but not a state with no rules, and the rules are those of quantum gravity in the regime, where space-time can flicker into and out of classicality. Third, does the proposal make contact with observation rather than floating as a clever metaphor? It does, albeit indirectly. By preferring high initial energy for the field that fuels early expansion, it influences the predictions for how strong the first density ripples are, how nearly they follow a simple spectrum across scales, and how curved the large-scale geometry should be. Different beginning prescriptions dial these features slightly differently. So precise maps of the sky's ancient light let us compare families of beginnings and throw out those that don't cook the soup we actually taste. There are, of course, live debates. One concerns how to properly set up the sum over histories so the tunneling amplitude is unambiguous and stable. Another asks how to treat back reaction, the way quantum fluctuations of fields and geometry feed on each other, so that the result isn't distorted by the approximations we use to make the calculation tractable. Yet another debate notes that when you talk about probabilities for the whole universe, you must define what you are counting carefully, because you don't have an ensemble of universes to repeat an experiment. You have a spectrum of possibilities from which our actual history is one drawn sample. None of these challenges sink the idea. They sharpen it. They also help separate the scientific content from the easy misunderstanding that from nothing means a free miracle. In this proposal, from nothing means a lawful low probability transition allowed by the same statistical logic that lets alpha particles escape nuclei or electrons slip across gaps in semiconductors. Rare but not disallowed. And once it happens, the aftermath is not fragile magic, but robust physics. The newborn spacetime expands. The high-energy field rolls, radiation floods the scene, matter condenses, light decouples, and the observable universe inherits the fingerprints of its earliest fluctuations. The proposal also reframes an old philosophical itch. If there were ever truly nothing, not even physical law, then nothing could happen. Vilen's point is not to dodge that, but to choose a definition of nothing that is squarely inside physics. No classical background, but lawful dynamics that include the option of creation. In that sense, it is a scientific answer to a scientific version of the question. And it stays in bounds by tying its claims to features we can try to measure. If you want to feel for the stakes, consider finer tuning. Without a principal beginning, one is tempted to insert special initial data by hand, a perfectly smooth start, an exquisitely chosen early expansion rate, just so parameters. With a tunneling start, some of that burden migrates into the logic of quantum birth. The theory itself assigns higher odds to beginnings that lead to rapid early growth. And rapid early growth is precisely what we need to explain today's near uniformity and the particular style of tiny imperfections that seed galaxies. That economy rules doing more work than ad hoc choices is why cosmologists keep this idea on the table despite its technical knots. And there is a quiet emotional payoff in thinking this way too. The view neither inflates us with sentimentality nor flattens us with fatalism. It says the universe may have come to be not by decree, but by chance permitted by law, and that your presence here is the late chapter of a story whose opening move was improbable but not impossible, a tunnel through a barrier that once seemed absolute. When you lean back and let that settle, the image that remains is not a bang in a pre-existing theatre, but a lawful appearance of the theatre itself. Small, closed, and ready to grow, followed by scenes we can trace and test, all the way down to the modelled whispers in the sky that preserve like fossilized breaths, the memory that the first and most consequential step was a quiet yes to becoming. Eternal inflation and bubble worlds. Picture a field that refuses to settle, a kind of cosmic yeast that keeps rising even after some parts of the dough have baked into galaxies. That is the intuitive doorway into eternal inflation, an idea in which the process that smoothed and stretched the early universe does not end everywhere at once, but lingers in some places while finishing in others, spawning bubble regions like pockets of cooled air in a hot loaf, each pocket an expanding universe with its own detailed weather. Begin gently. Ordinary inflation is the proposal that very early on space was driven by a high-energy field that made it swell fantastically fast, ironing out wrinkles and diluting defects so thoroughly that the cosmos we see today looks astonishingly uniform on large scales with only tiny ripples left to seed galaxies. Eternal inflation adds a simple twist rooted in quantum behavior. The field that powers expansion is not perfectly smooth. It jitters in some patches. Those jitters push the field downhill and inflation ends, releasing energy into a hot, particle-filled fireball, the beginning of the kind of history we recognize. While in other patches, the field is kicked upward or sideways on its landscape of possibilities, keeping expansion roaring a little longer. Because inflating space doubles in size at a furious rate, the volume of the still inflating regions grows faster than the pockets that have finished. So, even as countless bubbles complete their inflation and become Big Bang-like universes, the inflating background continues to produce more room for more bubbles. The result is not a polite sequence, but a branching ongoing process. No single time when everything's stopped, but an endless froth in which islands of finished space float inside a sea that keeps stretching. Now deep in the physics behind these bubbles comes in two flavors, both based on conservative ideas used elsewhere in science. In one, the inflationary field is stuck in a metastable state, a false vacuum, like a ball balanced in a shallow dimple on a hillside. Quantum mechanics lets the ball occasionally slip through the dimple's wall into a deeper valley. And that transition nucleates a bubble whose interior quickly exits inflation, heats up, and begins a conventional cosmic evolution. In the other flavor, the field is not trapped, but slowly drifting down a gentle slope while being rattled by quantum kicks. In some neighborhoods, the kicks speed its descent and finish inflation. In others, the kicks hold it up, so the slope never empties completely. In both cases, the geometry of a newborn bubble is special. Its interior looks like an open, negatively curved universe that begins small and then expands, while its thin wall races outward into the inflating sea at nearly the speed of light. Inside, The field's energy converts into particles and radiation in a process called reheating. Outside, the sea of high-energy space keeps ballooning, so bubbles become tiny, nearly non-interacting specks in an ever-growing background. Tiny to each other, that is even as each becomes enormous to its own inhabitants. This picture has striking consequences that scientists take seriously because they emerge from the same equations that make ordinary inflation successful. One is the fractal character of the inflating region. Zoom out, and you always find some patch still inflating no matter how many bubbles have already formed. So the global view never fully leaves the inflating phase. Another is the possibility that different bubbles may realize different low-energy rule, sets different patterns for particle properties or dark energy. If the underlying theory allows multiple valleys in its landscape, that's not fantasy for its own sake, but a sober inference from how fields can settle in different minima, much as water can freeze into various crystal arrangements depending on conditions. You, as an observer, would naturally find yourself in a bubble whose conditions permit long-lived stars, chemistry, and the slow step-by-step record-making process we call life. Not because of destiny, but because those are the only sorts of bubbles in which questions can be asked and answered. That selection effect is controversial if used as a conversation ender, but as a filter on which environments can host observers, it is a legitimate part of how we interpret data. We should compare our bubble's measured properties to distributions predicted by the theory, not to a hypothetical average over impossible worlds. Testability is the next honest question. Eternal inflation is not something we can watch from outside. There is no balcony seat beyond the hole, but it can leave indirect signatures. Bubble collisions, if any occurred in our past, could paint disk-like features in the pattern of ancient light across the sky. Faint rings or asymmetries with a telltale profile. Our bubble's geometry might carry a slight negative curvature, a relic of its open beginning. Though inflation inside typically stretches that curvature so close to flatness that it hides below current sensitivity, the spectrum of early ripples, how their strength varies with scale, should remain close to the simple, nearly scale-invariant form that ordinary inflation predicts, which is what we see. Deviations might hint at the way the field wandered before settling. Searches for bubble collision scars have turned up no compelling evidence so far, and measurements of curvature are consistent with 0 to within small uncertainties. So, the current status is not ruled out, not confirmed, but consistent with what we'd expect if we simply live in a garden variety bubble. The idea also forces us to wrestle with hard conceptual issues that are healthy for the field. Chief among them is the measure problem. If the global process never ends and keeps making more volume, how do you define probabilities for what typical observers see without being misled by the fact that more of everything keeps being produced? Different ways of regulating the infinity, cut-offs in time, cut-offs in volume. Counting along world lines can weight outcomes differently and even produce paradoxes like favoring extremely young bubbles or predicting absurdly common freak observers formed from random fluctuations. These pathologies are not reasons to discard the framework. They are guideposts for what a consistent probability rule must avoid. And they have driven much of the best work on how to compare theory to observation. Honestly, another issue is past completeness. Even if inflation continues forever to the future, the combined arguments suggest it cannot extend arbitrarily far into the past. In other words, eternal inflation likely still requires some sort of beginning or new physics in its rearview mirror. That reminder keeps the story anchored. Eternal to the future does not mean without origin. It means the mechanism that makes inflating space produces its own fuel by expanding, so it does not run down once started. The sociological temptation is to treat eternal inflation as a license to explain anything by saying some bubble has it. But the scientific stance is stricter. The framework is valuable only to the extent that it restricts what's likely inside successful bubbles and yields statistical predictions. We can test spectra of ripples, levels of curvature, allowed ranges for dark energy while remaining consistent with how physics works in our labs. If you step back from the technicalities, there's a surprising calm in the picture. It does not ask you to imagine countless carbon copies of yourself, or to pin meaning on a metaphysical multiverse. It asks you to accept that a noisy field left to the rules we already use would finish in patches and linger in others, and that the patches where it finishes become universes like ours. Seen that way, eternal inflation is not a maximal claim about reality. It is a minimal claim about how uneven endings propagate in a world governed by chance and expansion. There is no balcony seat beyond the hole, but it can leave indirect signatures. Bubble collisions, if any occurred in our past, could paint disk-like features in the pattern of ancient light across the sky. Faint rings or asymmetries with a telltale profile, our bubble's geometry might carry a slight negative curvature, a relic of its open beginning. Though inflation inside typically stretches that curvature so close to flatness that it hides below current sensitivity, the spectrum of early ripples, how their strength varies with scale, should remain close to the simple, nearly scale invariant form that ordinary inflation predicts, which is what we see. Deviations might hint at the way the field wandered before settling. Searches for bubble collision scars have turned up no compelling evidence so far, and measurements of curvature are consistent with 0 to within small uncertainties. So the current status is not ruled out, not confirmed, but consistent with what we'd expect if we simply live in a garden variety bubble. The idea also forces us to wrestle with hard conceptual issues that are healthy for the field. Chief among them is the measure problem. If the global process never ends and keeps making more volume, how do you define probabilities for what typical observers see without being messled by the fact that more of everything keeps being produced? Different ways of regulating the infinity. Cut-offs in time, cut-offs in volume. Counting along world lines can weight outcomes differently, and even produce paradoxes like favoring extremely young bubbles or predicting absurdly common freak observers formed from random fluctuations. These pathologies are not reasons to discard the framework. They are guideposts for what a consistent probability rule must avoid, and they have driven much of the best work on how to compare theory to observation. Honestly, another issue is past completeness. Even if inflation continues forever to the future, the combined arguments suggest it cannot extend arbitrarily far into the past along every path. In other words, eternal inflation likely still requires some sort of beginning or new physics in its rearview mirror. That reminder keeps the story anchored. Eternal to the future does not mean without origin. It means the mechanism that makes inflating space produces its own fuel by expanding. So it does not run down once started. The sociological temptation is to treat eternal inflation as a license to explain anything by saying some bubble has it. But the scientific stance is stricter. The framework is valuable only to the extent that it restricts what's likely inside successful bubbles and yields statistical predictions. We can test spectra of ripples, levels of curvature, allowed ranges for dark energy, while remaining consistent with how physics works in our labs. If you step back from the technicalities, there's a surprising calm in the picture. It does not ask you to imagine countless carbon copies of yourself or to pin meaning on a metaphysical multiverse. It asks you to accept that a noisy field left to the rules we already use would finish in patches and linger in others, and that the patches where it finishes become universes like ours. Seen that way, eternal inflation is not a maximal claim about reality. It is a minimal claim about how uneven endings propagate in a world governed by chance and expansion. And the emotional tone is not grandiosity but perspective. You are not lost in a blur of infinite worlds. You are focused inside one well-behaved bubble whose sky and chemistry can be read like a fossil record of the way inflation ended here. If other bubbles exist, they are not competitors for your meaning. They are branches of a process that needed no grand finale, only the steady hum of a field that sometimes lets go and sometimes holds on. And from that humble rhythm, a garden of universes grows while you, in this one, learn to read the quiet clues it left behind, quantum seeds of cosmic structure. You can trace every galaxy back to a time when there were no galaxies at all, only tiny restless ripples written into a hot, simple universe. Flickers so small they began as quantum jitters and grew into the scaffolding for everything you see. And the most honest way to feel this is to picture space like a stretched drum head that's never perfectly smooth. Even in its quietest state, it quivers. And during the earliest moments, those quivers were pulled wide, recorded, and left to ring, begin gently. In the deep past, the cosmos was expanding fast and smoothing itself out. But smooth in physics never means perfectly uniform. The same rules that let small systems fluctuate also ensure that fields filling space can't sit completely still. Minute variations in the energy stored from point to point. Microscopic ups and downs were stretched by the rapid growth of space, until they were far larger than any local process could erase. Like ripples carried beyond the shoreline, where waves can't easily flatten them anymore. At that stage, these ripples stopped acting like jitter and started acting like small differences in the depth of gravity's wells. A little more here, a little less there. Seeds that would later tug matter and light differently. Deep in the story, when the baby universe was a dense, glowing plasma of particles and radiation, those gravity wells and hills set the contents sloshing. Regions slightly denser than average pulled more material, compressing and heating it, and the pressure of trapped light pushed back, sending a wave outward. This push and pull made the young cosmos hum with acoustic patterns. Cosmic sound whose imprints survive in two exquisite places. In the faint temperature and polarization ripples across the ancient afterglow that still fills the sky, and in a subtle preferred spacing among galaxies today. A fossil of those early pressure waves. The critical point is coherence, because the earliest ripples were written down in a highly ordered way with their phases lined up by the way they were stretched, and then frozen. The later ringing produced a clear repeating structure rather than a random muddle. That is why we see a series of peaks and troughs in the sky oldest light, instead of a featureless smear, and why surveys of galaxies reveal a gentle bump in their separations rather than monotony. These seeds also carried a remarkable hallmark across a wide range of scales. Their strength changed only slightly, an almost scale-free pattern that means the universe doesn't prefer one size of structure over another too strongly. That near uniformity matches what we measure with satellites and telescopes, which find that the sky's ripples are close to but not exactly. Scale invariant, tilted just enough to be interesting, not enough to be chaotic. Another hallmark is their simplicity to exquisite precision. Those first fluctuations behave like a Gaussian random field, a technical way of saying the map of tiny hot and cold spots is as if drawn by tossing many fair coins. This is not a flourish. It's a test that our instruments pass again and again. And any small deviation from that simple pattern, non-Gaussianity, would be a clue to more exotic beginnings than the modest quantum jitters we're describing. There's also the question of what kind of seeds they were. The observed mix looks overwhelmingly like adiabatic variations where matter and radiation were nudged together in phase, rather than isocurvature shuffles that would have moved them in opposite ways. That, too, is a stringent check that the seeds came from one dominant source imprinted early, not from a zoo of unrelated processes later. How did something as ghostly as quantum behavior leave such down-to-earth fingerprints? Here, the bridge is neither mystical nor hand-waving. It's a combination of growth and recording. As space expanded rapidly, modes of fluctuation were stretched so that their wavelengths exceeded the distance over which anything could communicate. Once outside that horizon, the ripples could no longer trade energy or cancel one another, and their amplitudes were effectively set like a snapshot in mid-splash. As the universe aged and the horizon grew, those same modes wandered back inside, re-entering as classical-looking patterns because the environment had long since shredded the delicate quantum phase relations that would have allowed them to interfere. In plainer words, the early expansion turned microscopic randomness into macroscopic initial conditions, and the later environment made those conditions robust records, written in light and matter. From there, the script of structure formation is steady and testable. Slightly denser regions pulled more strongly, growing into clouds, filaments, and halos. Gas cooled within those halos, stars ignited. Supernova exploded. Black holes fed, and feedback from all this activity sculpted the luminous parts we can now photograph. Gravity kept tugging on dark matter and ordinary matter alike, weaving the cosmic web we map with surveys. While the radiation left over from the plasma era kept a faithful picture of the initial seeds, seen today as tiny temperature variations, a few parts in 100,000. The elegance of this account is that it ties together phenomena across absurdly different scales. Jitter in an almost featureless sea becomes the blueprint for clusters of galaxies. Coherent sound in a plasma becomes a ruler we still use to measure the expansion rate. A near-Gaussian pattern of ripples becomes a yardstick for ruling in or out complicated beginnings, and it leaves you with honest edges of curiosity rather than slogans. We keep pushing measurements to ask how slight the tilt really is, whether any faint non-Gaussian fingerprints lurk in the data, how strongly gravity may have lensed the ancient light as it traveled, and how the first stars and black holes modified the pristine patterns they inherited. Yet, the central lesson already stands. The universe did not require a miracle to draw galaxies on an empty canvas. It needed a gentle, lawful way to turn the smallest possible uncertainties into the largest possible structures. And that is exactly what those early quantum seeds accomplished. Let that settle and the sky becomes more than backdrop. It becomes a readable archive where randomness was not noise, but the opening measure of a symphony that still plays. From the hush of the microwave afterglow to the quiet shapes of the galaxies holding your night in place. Bunch Davies' vacuum and fluctuations. You can think of the early universe as a vast stage that needed a quiet starting note before the orchestra could build its theme. And the Bunch Davies vacuum is that quiet note, a specific disciplined way of saying start the fluctuations in their calmest possible state. So that every later riff, every ripple of temperature in the ancient sky, and every seed of structure has a clear, testable origin. Begin gently. In ordinary uncurved space, we know how to define nothing happening. It's the state with no particles, the calm baseline from which excitations stand out. But in a universe that is expanding, nothing is trickier because space itself is changing. And what looks calm at one moment can look stirred up at another. The Bunch Davies prescription navigates this by focusing on the behavior of very short wavelength ripples early on, when any small region of the inflating universe looks locally flat. There the rules of empty space apply, and vacuum means the same simple thing it does in the lab. The choice is to insist that each fluctuation mode, when it is far smaller than the horizon, and not yet feeling the expansion, sits in that familiar, calm state. As the universe stretches, the mode is carried along by the flow, but its initial condition is anchored to something we understand. This matters because in curved spacetime, there are many mathematically allowed ways to call a state vacuum, and different choices can sue different patterns in the sky. At the dawn of the observable pattern, when space was racing outward and tiny springs were about to be stretched beyond communication, the universe chose the simplest, quietest way to begin their motion, the way that every small lab experiment teaches us to trust when the background looks flat. Then it let expansion translate those calm microscopic tremors into macroscopic blueprints, leaving us a sky where silence became structure by following rules, not by conjuring miracles, transplantium puzzles in inflation. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place. Then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place. Then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place. Then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place. Then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place, then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny, so tiny that if you rewind far enough, The wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Imagine pressing your ear to the earliest moments of the universe and hearing a faint hiss you can't quite place. Then realizing the mystery is not the sound itself, but the microphone. During inflation, the ripples we observe today were once unimaginably tiny. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small. So tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, The wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle. An honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon, and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Begin gently. Inflation stretches everything like drawing a tiny doodle on a balloon and then expanding it until the doodle spans the room. Modes that today cover millions of light years started inconceivably small, so tiny that if you rewind far enough, the wavelengths that seeded galaxies would have been shorter than any scale where our tested physics is reliable. And this is the heart of the transplant puzzle, an honest, uncomfortable question that asks whether we are extrapolating beyond what we have a right to trust. Quantum back reaction in an expanding cosmos. And the cleanest way to feel it is to imagine space as an elastic fabric that not only carries waves, but also changes its stretch in response to whatever those waves are doing. Every field has energy and pressure, and in a universe where geometry listens to energy and pressure, the fluctuations you create don't just sit there. They whisper into the equations that shape the next frame of the story. Begin gently. In ordinary settings, we treat particles and fields as passengers, and gravity is the road. The road may curve, but the cars don't meaningfully change the road unless you gather something extreme like a star. Early cosmology raises the stakes because the background is delicate. A rapidly expanding space during inflation, a hot plasma afterwards, and the passengers are not a few isolated particles, but quantum fields filling everything, constantly being stretched, redshifted, occasionally excited out of their calm state, and sometimes produced out of the changing geometry itself. Each of these processes comes with an energy budget. When a field is excited by expansion, it extracts energy from the background and pays it back as effective pressure and density. When a field decays or scatters, it shuffles energy among components that couple differently to the fabric of space. Back reaction is the name for letting these budgets talk back to expansion instead of treating expansion as a mute backdrop. Deepen the story by following 3 concrete arenas where this matters. First, during the tail end of inflation, the field driving the rapid swelling of space has to hand its energy to the contents of a hot, ordinary universe, a process called reheating. And in many models, its efficient version, preheating, is dramatic. The inflating field oscillates and through resonant production, dumps quanta of other fields in explosive bursts. At first, you can pretend the background keeps inflating smoothly while the transfers happen, but that's not honest for long. The produced particles build up real pressure and density, which damp the oscillations and change the expansion rate, closing the inflationary chapter. In planar language, the act of filling the universe with stuff is the very signal that turns off the mechanism that made the room bigger. The back reaction is the off switch. Second, even in a calmer phase, quantum fluctuations carry stress, the combination of energy density and pressure that contributes subtly to the cosmic bookkeeping. In a gently accelerating spacetime like de Sitter space, long wavelength modes are continually pushed beyond the horizon and become frozen patterns. Some calculations suggest that the accumulated effect of many such modes can grow in time and nudge the effective expansion rate, like a persistent background murmur that ever so slightly shifts the tempo. Imagine a dancer carefully adjusting the stage floor, not to change the steps, but to subtly influence the rhythm of the entire performance. The ripples in the early universe aren't just passively carried along, they're actively shaping the path of the expansion itself. And third, consider the subtle coupling between the expanding space and the particles that reside within it. The very act of stretching space alters the way these particles interact, creating a feedback loop where the expansion is influenced by the particles, and the particles, in turn, influence the expansion. It's a dynamic dance, a constant exchange of energy and momentum. The more you expand, the more sensitive the universe becomes, reacting with an ever-increasing finesse. This is not just a theoretical oddity, it's a fundamental property of the cosmos. The universe isn't a passive container for ripples, it's a responsive participant, actively sculpting its own destiny. The key to understanding this feedback isn't to treat the expansion as a simple background process. It's to acknowledge the profound influence of quantum fields on the very geometry of space. And that influence, in turn, fundamentally alters the evolution of the universe. The energy you put into driving the expansion doesn't just go away, it gets recycled, reshaped, and redistributed, creating a cascade of effects that ripple through the cosmos. It's a beautiful, terrifying, and profoundly elegant picture of the universe, one where nothing is quite as it seems. The universe isn't just expanding, it's evolving in response to itself, a self-regulating system constantly seeking equilibrium. This isn't a dramatic, catastrophic event, it's a subtle, continuous process. The universe isn't a machine governed by fixed rules, but a delicate ecosystem of energy and momentum, where every interaction leaves a trace, shaping the very fabric of reality. And finally, consider the implications for our own understanding of time. If the universe is constantly reacting to itself, then time isn't a simple, linear progression. It's a dynamic, interwoven tapestry of cause and effect, where the past, present, and future are inextricably linked. The choices you make today aren't just affecting your own life, they're shaping the very evolution of the universe. And as you ponder this, let the profound realization sink in. You are, in a very real sense, a participant in the cosmic drama. It's a humbling thought, isn't it? To realize that the universe isn't just out there, indifferent to our existence, but is actively shaped by our actions, our ideas, and our very thoughts. Embrace the mystery, the wonder, and the sheer audacity of it all. Because in the end, the universe isn't just expanding, it's listening. The universe isn't just expanding, it's evolving in response to itself, a self-regulating system constantly seeking equilibrium. This isn't a dramatic, catastrophic event, it's a subtle, continuous process, a quiet conversation between geometry and the fields that fill it. Imagine space as an elastic fabric that not only carries waves, but also changes its stretch in response to whatever those waves are doing. Every field has energy and pressure, and in a universe where geometry listens to energy and pressure, the fluctuations you create don't just sit there. They whisper into the equations that shape the next frame of the story. Begin gently. In ordinary settings, we treat particles and fields as passengers, and gravity is the road. The road may curve, but the cars don't meaningfully change the road unless you gather something extreme like a star. Early cosmology raises the stakes because the background is delicate. A rapidly expanding space during inflation, a hot plasma afterwards, and the passengers are not a few isolated particles, but quantum fields filling everything, constantly being stretched, redshifted, occasionally excited out of their calm state, and sometimes produced out of the changing geometry itself. Each of these processes comes with an energy budget. When a field is excited by expansion, it extracts energy from the background and pays it back as effective pressure and density. When a field decays or scatters, it shuffles energy among components that couple differently to the fabric of space. Back reaction is the name for letting these budgets talk back to expansion instead of treating expansion as a mute backdrop. Now, let's delve deeper into three concrete arenas where this matters. First, during the tail end of inflation, the field driving the rapid swelling of space has to hand its energy to the contents of a hot, ordinary universe, a process called reheating. And in many models, its efficient version, preheating, is dramatic. The inflating field oscillates, and through resonant production, dumps quanta of other fields in explosive bursts. At first, you can pretend the background keeps inflating smoothly while the transfers happen, but that's not honest for long. The produced particles build up real pressure and density, which damp the oscillations and change the expansion rate, closing the inflationary chapter. In simpler language, the act of filling the universe with stuff is the very signal that turns off the mechanism that made the room bigger. The back reaction is the off switch. Second, even in a reheating phase, quantum fluctuations carry stress, the combination of energy density and pressure that contributes subtly to the cosmic bookkeeping. In a gently accelerating spacetime like de Sitter space, long wavelength modes are continually pushed beyond the horizon and become frozen patterns. Some calculations suggest that the accumulated effect of many such modes can grow in time and nudge the effective expansion rate, like a persistent background murmur that ever so slightly shifts the tempo. Whether that murmur becomes loud enough to matter is an area of serious work. Naive treatments overcount or break cherished conservation principles, while careful ones ensure that the stress carried by fluctuations is finite, conserved, and properly renormalized so that you're not mistaking artifacts of your math for real physics. The headline you can trust is conservative with the initial conditions and energy scales favored by observations. These quantum pushes are generally small corrections to the main expansion, not runaway breaks or turbocharges, but they are principled and in some corners of parameter space, measurable in the tilt or running of the primordial spectrum, in the amount of gravitational waves produced, or in the detailed statistics of the ancient light. Third, there is the cousin problem of inhomogeneities at later times when matter clumps into galaxies and clusters and voids. Do all these lumps push back on the average expansion in a way that could mimic dark energy? That back reaction from structure is mostly a classical averaging issue rather than a quantum one. And the best current analyses indicate that while small corrections exist, the net effect is far too tiny and too sign-constrained to replace a genuine dark energy component. It's an instructive cautionary tale because it shows how easy it is to overread the feedback of ripples on the background if you don't average with care. Return to the quantum setting and ask how back reaction keeps our stories honest. Energy is not created from nothing when particles appear in an expanding universe. Rather, the changing background does work on the fields, and the fields repay that work by altering the stress energy that enters the same equations that govern the background in the first place. Practically, this means three things for model builders and observers. 1. When you propose exotic initial excitations, modified short d-distance behavior, or strongly interacting sectors, you must track the energy they carry and ensure they don't blow up the background or quench the very phase you need to explain the sky. Many flashy ideas fail this self-consistency test before they ever meet data. 2. When you compute the average stress of quantum fluctuations, you must remove the universal short-distance infinities by the same disciplined methods that work in ordinary quantum field theory, which automatically introduces a handful of counterterms, mathematically neat placeholders for familiar physical levers like a cosmological constant or curvature squared corrections. The values of those levers are not arbitrary metaphysics. They are set by observation. 3. When you claim a large secular effect, a correction that grows with time, you must show it survives changes of coordinates and choices of what you call background versus fluctuation. Otherwise, you are measuring a gauge shadow rather than a physical shove. None of this is rhetorical hair-splitting. It's the difference between a theory that predicts consistent skies and one that predicts mirges. On the observational side, quantum back reaction is a quiet theme threading several active searches. If the interplay of fluctuations with expansion during inflation altered the propagation of waves even slightly, it could leave faint ripples, small oscillations in the spectrum of temperature variations across the sky. If the reheating drama was especially violent, it might have sourced a stochastic background of gravitational waves with a distinctive frequency band, a target for the experiments. Now, let's learn to hear spacetime's low-hum symphonies. If long-wavelength modes during inflation accumulated a real gauge invariant stress, it would show up as tiny shifts in the relation between the amplitude and tilt of the primordial spectrum that next-generation surveys could detect. So far, the universe has answered in a restrained voice. The sky statistics are strikingly close to the simplest expectations. Non-Gaussianities are small. No loud extra backgrounds have appeared. That restraint doesn't belittle back reaction. It calibrates it, telling us that the feedback loop between quantum fields and cosmic expansion is there, but typically modest, an adjustment of the stage lights rather than a collapse of the set, unless the energy scale, couplings, or initial excitations are tuned to make it otherwise. The philosophical payoff is clarity about causation. The universe is not a one-way script in which geometry dictates and fields obey. It is a conversation in which fields and geometry take turns leading, bound by conservation and consistency. And there is a human-sized lesson tucked inside the equations. Feedback matters, but good systems are stable because their feedbacks are mostly small and properly signed. The early universe seems to have been such a system, allowing tiny quantum murmurs to seed structure without letting those murmurs derail the expansion that made the seeding possible. Let that image linger, an elastic stage that sets the tempo, a chorus of quantum voices that in singing ever so slightly retune the hall, and a performance that stays coherent because the give and take is lawful and gentle. Enough to teach us how the world really works, not enough to drown out the music we are still learning to hear. Now, imagine the infant universe not as a crisp photograph, but as a soft, shimmering double exposure. Countless nearly identical versions of the same early pattern layered together, until the world's own bustle begins to file those layers into a single readable picture. And that filing is what physicists call decoherence of the primordial universe, the quiet, lawful process by which quantum possibilities for the earliest ripples stopped acting like overlapping waves and started behaving like the classical initial conditions from which galaxies and the sky's ancient light could honestly evolve. Begin gently. When the universe was very young and expanding fast, the tiny fluctuations in its fields were genuinely quantum objects with phases that in principle allowed different histories to interfere. The way ripples on a pond can add or cancel, but interference is fragile and it relies on keeping the alternatives isolated from any environment that might learn something about which alternative is in play. In the early cosmos, there was no laboratory wall to protect delicacy. There was only everything coupling to everything. Long wavelength density ripples stretching beyond causal contact. Shorter wavelength ripples still trading energy nearby. Gauge fields being excited by the changing background, NENT radiation. And the ever-present tug of gravity that links every bit of energy to the geometry in which all of this unfolds. As modes were stretched by expansion, each became squeezed. One aspect of its state, the overall displacement that would later show up as a small over or under density, grew very well defined, while its complementary aspect became wildly uncertain. And then the rest of the universe, acting as an environment, began to copy partial information about those displacements into many places at once. That copying is the core move of decoherence. Once enough, independent fragments of the world, other fields, gravitational perturbations, eventually vast numbers of photons carry redundant hints about a particular value of a fluctuation. The delicate phase relations that would have allowed rival values to recombine are effectively lost to bookkeeping beyond retrieval. And the quantum state looks for all practical purposes like a classical random field drawn from a definite probability distribution and a gently tilted spectrum. Deepen with a concrete path you can visualize. Picture the space of early fluctuations as a hall of tuning forks, one fork for each wavelength. While the forks are tiny compared to the horizon, their hums can in principle interfere. But inflation stretches them so quickly that many forks are carried outside the region where vibrations can coordinate. Out there, each fork's displacement is recorded by the gentle but inexorable couplings it cannot turn off, by the way gravity responds to its presence, by the way other fields slightly adjust in its company, by how the changing geometry stirs or damps its neighbors. If you choose to ignore the sea of degrees of freedom that now carry those records, because you cannot possibly keep track of them all, the remaining description of the fork state becomes a diagonal ledger of classical-looking alternatives. The jargon for this is that the reduced state becomes approximately a statistical mixture in the pointer basis. Here the basis that labels the actual amplitude of the long wavelength perturbation, and that basis is selected not by human preference, but by which properties of the fluctuation the environment most easily and redundantly learns in the primordial setting. That tends to be the curvature or density contrast itself, because that is what gravity and the subsequent plasma care most about where the wells and hills are, not their delicate phase information. The payoff is conceptual clarity and observational coherence. Conceptually, decoherence explains why it is honest to treat the post-inflationary ripples as a classical random field with a nearly Gaussian distribution and a gently tilted spectrum without invoking a mystical collapse. The universe itself performed the measurement-like act by scattering records of the amplitudes into a vast environment that no agent could ever recode. Observationally, the sky behaves exactly the way a decohered, phase-coherent set of initial conditions should. Long wavelength density ripples stretching beyond causal contact. Shorter wavelength ripples still trading energy nearby. Gauge fields being excited by the changing background, NENT radiation. And the ever-present tug of gravity that links every bit of energy to the geometry in which all of this unfolds. As modes were stretched by expansion, each became squeezed. One aspect of its state, the overall displacement that would later show up as a small over or under density, grew very well defined, while its complementary aspect became wildly uncertain. And then the rest of the universe, acting as an environment, began to copy partial information about those displacements into many places at once. That copying is the core move of decoherence. Once enough, independent fragments of the world, other fields, gravitational perturbations, eventually vast numbers of photons carry redundant hints about a particular value of a fluctuation. The delicate phase relations that would have allowed rival values to recombine are effectively lost to bookkeeping beyond retrieval. And the quantum state looks for all practical purposes like a classical random field drawn from a definite probability distribution deepen, with a concrete path you can visualize. Picture the space of early fluctuations as a hall of tuning forks, one fork for each wavelength. While the forks are tiny compared to the horizon, their hums can in principle interfere, but inflation stretches them so quickly that many forks are carried outside the region where vibrations can coordinate. Out there, each fork's displacement is recorded by the gentle but inexorable couplings it cannot turn off, by the way gravity responds to its presence, by the way other fields slightly adjust in its company, by how the changing geometry stirs or damps its neighbors. If you choose to ignore the sea of degrees of freedom that now carry those records, because you cannot possibly keep track of them all, the remaining description of the fork state becomes a diagonal ledger of classical-looking alternatives. The jargon for this is that the reduced state becomes approximately a statistical mixture in the pointer basis. Here the basis that labels the actual amplitude of the long wavelength perturbation, and that basis is selected not by human preference, but by which properties of the fluctuation the environment most easily and redundantly learns in the primordial setting. That tends to be the curvature or density contrast itself, because that is what gravity and the subsequent plasma care most about where the wells and hills are, not their delicate phase information. The payoff is conceptual clarity and observational coherence. Conceptually, decoherence explains why it is honest to treat the post-inflationary ripples as a classical random field, with a nearly Gaussian distribution and a gently tilted spectrum without invoking a mystical collapse. The universe itself performed the measurement-like act by scattering records of the amplitudes into a vast environment that no agent could ever recode. Observationally, the sky behaves exactly the way a decohered, phase-coherent set of initial conditions should. The acoustic peaks in the microwave background line up because the phases of modes were set together in the early expansion and then preserved as classical records. The pattern of temperature and polarization follows simple statistics with non-Gaussian features bounded to be small. The same initial ledger seeds both the afterglow and the later galaxy distribution in a way that remains internally consistent across scales. None of this requires you to imagine human observers collapsing a universal wave. It requires only that interactions create durable, redundant imprints, which is precisely what a hot expanding universe is built to do. There are, of course, subtle questions that keep the field honest and lively. What exactly counted as the dominant environment right after horizon exit? Self-interactions of the inflaton-like field, couplings to spectator fields, gravitational tidal effects, or the maelstrom of reheating as the inflaton decayed into radiation. And how fast did each mechanism drive decoherence? Different channels give different decoherence times, but a robust lesson emerges. For cosmologically relevant wavelengths, the process is typically blisteringly efficient, on the order of a few expansion time scales. So by the time those modes re-entered causal contact much later, they were already behaving classically for all practical purposes. Another careful point concerns what survives decoherence. The process does not erase the probability distribution. It preserves it while killing off coherent superpositions between macroscopically different values. That is why decoherence and prediction sit comfortably together. You keep the amplitudes that predict the relative frequencies of hot and cold spots, but you lose the possibility of macroscopic interference fringes between rival large-scale patterns, which is exactly what our data show. There is also a modern twist, sometimes called quantum Darwinism. The idea that what we call objective classical reality is defined by the redundancy of records across many fragments of the environment. The primordial universe is a natural stage for this because the radiation that eventually flooded space, photons, neutrinos, became messengers carrying consistent snapshots of the same initial displacements to far-flung regions, so that many independent observers could in principle infer the same classical map without coordinating. In that sense, the uniformity of the early sky is not just smoothness. It is agreement among records, even the potential smoking guns for departures from the simplest story. Faint primordial non-Gaussianity, exotic isocurvature components, tiny preferred direction signatures fit into this framework. They would be read as specific choices of initial probability distribution or specific interactions during decoherence, not as violations of the quantum to classical bridge itself. And there is a cautionary moral tucked alongside the triumph, claims that the accumulated effect of super-horizon modes could dramatically alter the average expansion must be scrutinized to ensure they are not artifacts of how we split background from fluctuation or of counting. Own observable phase information as physical. When the bookkeeping respects conservation and gauge invariance, the back reaction of decohered long modes on the background appears to be small for the energy scales our sky prefers, which keeps the whole edifice pleasantly self-consistent. In the end, decoherence of the primordial universe is neither a metaphysical flourish nor a mere technicality. It is the quiet mechanism that allowed a lawful handoff from the quantum rules, that wrote the first ripples to the classical behavior that let those ripples grow into structure. It does not ask you to choose between magic and determinism. It asks you to notice how records accumulate, how redundancy makes objectivity, and how a world that began as delicate as breath could, by copying information into countless channels, becomes sturdy enough to craft stars, planets and minds that look back at the sky and recognize in its faint modeling the signature of the moment when possibility blurred into history. Wheeler-DeWitt equation and timeless. You're used to stories that begin with once upon a time, but the Wheeler-DeWitt equation quietly asks you to drop the time and see what remains. A single all-at-once description in which the universe's possible geometries and matter arrangements are woven into a grand static pattern. And what you call the flow of moments is not a universal tick, but a relationship that certain parts of that pattern can read off from others. Begin gently. In ordinary quantum mechanics, change is driven by a clock outside the system, an implicit stage on which waves evolve. In general relativity, by contrast, space-time itself is dynamical. So asking for a master clock is like asking the ocean to provide a fixed shoreline. When you try to quantize gravity honestly, this mismatch becomes the problem of time. And the Wheeler-DeWitt equation is its clearest expression. Instead of telling the state how to march forward, it imposes a constraint that the total energy of geometry plus matter vanishes, leaving a wave functional that satisfies a timeless condition. Roughly, physical states are those that solve harm zero, so that the right question is no longer how does change with time, but which correlations inside describe consistent experiences of change. If that sounds like a philosophical trick, Make it concrete with a pocket analogy. Imagine a book of photographs showing a pendulum swinging past a dial. The book itself is not moving, but inside it there's a beautiful regularity. Whenever the pendulum is at a certain angle, the dial's hand points to a matching number. Open the book at random, and you see a correlation that could be read as time. Even though the book as a whole is still the Wheeler-DeWitt universe is such a book, the stating encodes which three geometries co-occur with which matter configurations and with which readings of internal clocks. Choose one variable as a clock, say the average scale of the universe, and ask conditional questions. Given that the scale reads this value, what are the relative chances for the distribution of matter to look like that? In good regimes, this reproduces the familiar Schrödinger evolution as an approximation. When geometry is heavy and slow, and matter is light and quick, a careful separation shows that branches of the timeless state behave as if matter were evolving in an emergent time defined by the geometric clock, a result you can derive without smuggling in an external ticking. This is the semiclass bridge that lets cosmology do honest calculations. Treat the dominant part of the wave functional as providing a quasi-classical background and read matter's dynamics relative to it, recovering the equations we trust for atoms, radiation, and structure formation. Time in that view is the parameter labeling the background branch you're walking along, not a godlike metronome. Deepen the picture by facing two sharp questions. First, if the fundamental equation is timeless, why do you feel a forward flow and remember the past, not the future? The answer lives in records and boundary conditions. The timeless state can still favor branches in which certain variables increase monotonically across the correlations. Those branches are the ones rich in stable records, photons, fossils, detector clicks that accumulate in one direction, giving rise to the arrow you experience, the asymmetry you feel. In other words, comes not from a built-in time operator, but from the structure of correlations the state actually supports. Many consistent pages line up so that more records correlate with larger scale, and creatures like us only arise on such pages. Second, if nothing truly evolves, what does it mean to predict anything? In practice, predictions become statements about conditional probabilities derived from the timeless state. If an internal clock reads value A, what distribution of outcomes B should you expect? And how are those probabilities constrained by the requirement that the correlations fit together consistently across different choices of clocks? This is less exotic than it sounds. You already live by conditional probabilities, and the Wheeler-DeWitt framework elevates that logic from the lab to the universe as a whole. To keep the story scientific rather than mystical, you must be careful about what counts as an observable. In a diffeomorphism invariant world, only relational quantities, the value of this field, when that geometric marker reads thus, are meaningful. The Wheeler-DeWitt equation quietly enforces that discipline by killing off any reference to an external time and forcing you to build observables out of correlations. When you do, measurable quantities drop out cleanly from the pattern of cosmic ripples to the lifetimes of metastable states in the early universe. There are technical knots here, and acknowledging them keeps the wonder honest. Defining a good inner product in the space of solutions is tricky because the equation resembles a wave equation with an indefinite sign. Choosing clock variables is subtle because a variable can stop being monotonic, making it a poor global clock. And ensuring that different choices of clock lead to compatible predictions demands consistency. Checks that are still an active frontier, yet the encouraging part is how robust the approximations become in the regimes we can test. Imagine you are standing in a room with no windows, no clocks on the wall, only a gentle ticking metronome on a table and a mobile of planets slowly turning overhead. A soft voice whispers, "There is no external time here, only relationships." In that moment, you begin to sense that time is not a universal river flowing outside of you, but a pattern that emerges from the way things relate to each other. This is the spirit of the approach. We are exploring a way of seeing the cosmos that invites you to read the clock not from an outside hand, but from the beautiful dance of geometry and matter within the universe itself. When you look at the deep equations that aim to describe everything, you may encounter a statement that seems puzzling at first. The fundamental law governing the entire cosmos is timeless. Yet every day you feel a forward flow, you remember a past, you anticipate a future. How can a timeless equation give rise to the experience of change? The answer lies in the way the universe records its own history. Imagine the total quantum state of everything as a vast tapestry. Certain threads in that tapestry, photons that have scattered, fossils that preserve ancient life. The faint clicks of detectors form stable records that line up in a particular direction. Those records are not placed by an external stopwatch, they emerge because the underlying state favors configurations where some variables increase steadily. And with those increases come more and more reliable marks of what has happened. The arrow you feel is woven from those correlations, not from a built-in time operator. Think of geometry as the slow, steady heartbeat of the cosmos, a geometric clock that ticks gently. Matter, on the other hand, is light and quick, buzzing around like a lively melody. When you carefully separate these two aspects, you see that the branches of the timeless state behave as if matter is evolving against the backdrop of that geometric clock. No external ticking needs to be smuggled in. The elapsed time is simply the label you assign to the particular background branch you are walking along. In practical terms, you treat the dominant, quasi-classical part of the wave functional as a smooth stage, and you read the dynamics of matter relative to that stage. In doing so, you recover the familiar equations that govern atoms, radiation, and the formation of galaxies. Time, in this view, is not a godlike metronome, but the parameter that marks which background you are on. Now, let's confront two sharp questions that often arise when we open this door. First, if the deepest equation has no time, why does your consciousness feel a forward flow? The answer is found in records and boundary conditions. The timeless state can still favor branches where certain quantities grow monotonically across their correlations. Those branches are rich in stable records, photons that travel outward, fossils that whisper of ancient seas, detector clicks that accumulate in one direction. Those records give rise to the asymmetry you experience, the arrow that points from past to future. It is not a hidden time variable, but the structure of the correlations that the universe actually supports. Many consistent pages line up so that more records correlate with a larger clock reading, and creatures like us only arise on such pages. Second, if nothing truly evolves, what does it mean to predict anything? In practice, predictions become statements about conditional probabilities derived from the timeless state. If an internal clock reads a particular value, what distribution of outcomes should you expect? Those probabilities must be constrained so that the correlations fit together consistently across different choices of clocks. This may sound exotic, but you already live by conditional probabilities every day. You look at the sky, you gauge the temperature, you decide whether to bring an umbrella. The framework we are discussing simply elevates that everyday logic from the laboratory to the entire universe. To keep the story grounded in science rather than mysticism, we have to be precise about what counts as an observable. In a world where the laws are diffeomorphism invariant, meaning that only relationships, matterly relational quantities have meaning. The value of one field when another geometric marker reads a certain amount is what you can actually measure. The timeless equation quietly enforces this discipline by erasing any reference to an external time and forcing you to build observables out of correlations. When you do, measurable quantities emerge cleanly, from the pattern of cosmic ripples to the lifetimes of metastable states in the early universe. There are technical knots to acknowledge, and doing so keeps the wonder honest. Defining a good inner product in the space of solutions is subtle, because the equation resembles a wave equation with an indefinite sign. Choosing clock variables is delicate. A variable might stop being monotonic, making it a poor global clock. And ensuring that different choices of clock lead to compatible predictions demands consistency checks that are still an active frontier of research. Yet the encouraging part is how robust the approximations become in the regimes we can test. Whenever one sector serves as a smooth, classical background and another plays the role of a nimble system, the emergent time description works and yields the physics that guides satellites, telescopes, and particle detectors. Decoherence, a phenomenon you may have heard discussed elsewhere, plugs neatly into this story. In the timeless state, there are many potential branches quasi-classical islands each, looking like a separate classical world. Interactions with countless degrees of freedom suppress interference between those branches, allowing one relational narrative to become stable enough for us to live in. That stability is precisely why your internal clocks don't jump or blur. The interference has been washed away, leaving a clear, consistent flow. A useful laboratory to explore these ideas is the so-called mini-superspace model, where you trim the universe down to a handful of degrees of freedom, perhaps a homogeneous scale factor, and a simple field. In that simplified setting, you can solve the timeless equation explicitly and see how different boundary conditions pick out distinct families of correlations. The point isn't to crown a final answer, but to demonstrate how the timeless formalism encodes familiar behavior when the right clock is chosen and how it fails when the clock is bad. This reframes debates about the beginning of the universe. In a timeless picture, before and after are not global absolutes, they are labels internal to a branch. One branch might encode a contracting phase that then expands a bounce, while another branch may describe an eternally expanding cosmos. Observation, then, is the process of deciding which branches' conditional predictions match our sky, not of elevating any one metaphysical timeline to authority. The emotional punch of this perspective is quieter than a headline and deeper than a slogan. The timeless equation does not say that nothing happens. It says that happening is the emergent grammar of certain correlations. And the reason it feels so natural is that you are made of record-making machinery tuned to those correlations. The practical payoff is discipline. Never confuse coordinates with clocks. Never mistake a global parameter for a physical reading, and never add more structure than the theory permits. The philosophical payoff is a kind of freedom. If time is not an external river but a relation among things, then meaning lives in the patterns we can check how matter lines up with geometry, how records accumulate, how arrows arise. Meaning does not come from a cosmic stopwatch we will never find, but from the harmony of the universe's own story. Picture a vast library of consistent pages, each bound by a law that asks for harmony rather than marching orders. Picking a clock is like placing a bookmark. It opens a page whose correlations agree with what you see. In that quiet relational universe, the story of stars and minds unfolds not because time commands it, but because the pattern itself allows it, beautifully and enough. Now, let's bring this home with an image that may stay with you. Imagine waking in that windowless room, the metronome ticking softly, the planetary mobile turning above you. Someone whispers again, "There is no external time here, only relationships." Watch the metronome to learn how the planets move, and watch the planets to learn what the metronome has ticked. This is the spirit of the relational approach to time. It asks you to cease the search for a universal stopwatch outside the cosmos and to read time from the correlations inside it. In the language of cosmology, this becomes a clear working rule. First, pick a physical degree of freedom that behaves like a clock, something that changes smoothly and is only lightly disturbed by what it is timing. Then entangle it with the rest of the universe and describe change as how everything else looks when that clock reads a particular value. Begin gently. In general relativity, spacetime is not a fixed stage. Geometry flexes with energy. Importing an external time parameter into a truly closed description of all that exists would be like demanding a novel come with page numbers printed by another book. The relational move is to treat the universe as one wholly quantum object whose total energy satisfies a constraint. You then split it conceptually into two parts, a clock and a system. You ask conditional questions such as, given that the clock points to this value, what is the state of the rest? If the clock is good, monotonic, stable, and only weakly disturbed, those conditional states line up as the familiar step-by-step movie we call evolution. Even though the joint state of clock plus system considered all at once is static in the sense that it satisfies a timeless constraint. Why does this matter for cosmology? Because the universe is a closed laboratory, you cannot plug the early cosmos into an outside oscillator and read off seconds. You must extract time from within, often using something like a homogeneous scalar field, the overall size of space, or a dust component introduced precisely to serve as a clock. Then you compute what the rest of the fields are likely to do when the chosen clock reads this or that. The beauty of the relational construction is that it turns what sounds like philosophy into a concrete recipe. Choose a clock variable that advances smoothly across the history you care to describe. Write the joint quantum state of clock and cosmos so that they are correlated specific clock readings paired with specific matter plus geometry configurations. Then build predictions as conditional probabilities, the same way you decide every day if you need a coat based on the thermometer, or if a half-life tells you how old a sample is. Deepening the picture, remember that a clock is only useful if it is stable and precise. Quantum clocks have limits. If you try to make one arbitrarily accurate, you must endow it with an energy spread that, in gravity, back-reacts on the geometry you are also trying to measure. Conversely, a clock that is too gentle to disturb the world is also too fuzzy to tell you much. In cosmology, this trade-off is manageable. Stick to clocks that change steadily like the rolling scale factor during early expansion, or the volume of the universe in certain models so that the ticks are widely spaced. Robust milestones rather than fragile flutter. With such a clock in hand, the conditional states of the system obey, to an excellent approximation, the same evolution equations we use in ordinary physics. The trick is that time in those equations is not a godlike variable, but the reading of your internal clock. This perspective clarifies a long-standing headache known as the problem of time. If the deepest equation for the whole universe looks timeless, how do we recover change? The answer is that change was never about marching relative to an external meter. It was always about reliable correlations among subsystems clocks, fields, geometry. When those correlations have the right structure, the familiar movie appears without adding extra structure to the theory. It also reshapes the arrow of time. The relational framework does not itself pick a direction. What gives you a forward sense is the special pattern of correlations and records in the actual state of our universe. Entropy grows because configurations that pair a larger clock reading with more and more redundant records are the ones realized. You remember the past because there are physical marks of it: photons, fossils, data written into the environment when the clock was smaller that accumulate as the clock grows. In this way, the arrow emerges from how records are layered in the conditional states, not from a preferred tick hidden in the equations. Concrete toy models bring these ideas to life. In mini-superspace, where you keep only a few degrees of freedom, say the overall scale of space, and a simple field you can solve for a joint quantum state that satisfies the global constraint, and then take the field as a clock. When the field reads a particular value, what is the distribution of the scale factor? The result is that the conditional distribution obeys an effective dynamical law that looks just like ordinary evolution, with corrections that tell you where the approximation breaks down. You can swap roles and choose the scale as the clock to read off the field's dynamics. This is a practical proof that different internal times can be used, provided they are monotonic and that their overlaps agree. It also exposes the main technical caveats. Clocks are not free. Choose a bad one that hiccups, reverses, or ceases to be globally monotonic and your emergent notion of time fails in that regime. Choose two good clocks, and you face the multiple-choice problem. Do different reasonable clocks yield the same physics? They should in the regions where they both apply, and demanding that consistency is a powerful filter on which models are acceptable. There is also the need for a good probability notion in the space of solutions to the global constraint. You want an inner product that lets conditional probabilities add up and remain invariant under changing your bookkeeping. Defining such an inner product is an active area of research, but progress here would cement the relational picture on a firm mathematical foundation. All of this may sound intricate, but the core message for you is simple and empowering. The universe does not hand you an external clock, it offers you relationships. By choosing a reliable internal degree of freedom, whether it is the expansion of space, the role of a scalar field, or a dust component, you can turn those relationships into a sense of when. With that sense in hand, you can ask meaningful questions, make predictions, and understand why the arrow of time points forward. You learn that the flow you experience is not an illusion imposed by a hidden metronome, but a natural consequence of the way records accumulate as the universe evolves relationally. So as you move forward in your own journey, let this perspective inspire you. When you face a problem that seems static or unsolvable, look for the internal clock, the aspect of the situation that changes reliably and can serve as a reference. Align your actions with that relational rhythm, and you will find that change emerges naturally, without forcing an external tempo. Remember that every record you create, every habit you form, every piece of knowledge you add to the world is part of the tapestry of correlations that defines the direction of time for you. Embrace that role as a record maker in a universe that writes its story through relationships. The next time you hear a ticking metronome or watch a planet spin, feel the gentle reminder that time is not a tyrant outside your control, but a partner that arises from what you observe and how you relate one thing to another. Let that awareness guide you, infusing your choices with the confidence that you are working with the very language the cosmos uses to tell its story. In doing so, you not only understand the deep physics of the universe, you also step into the flow of the world with clarity, purpose, and a profound sense of belonging. When you're standing at the edge of a problem that feels immovable, it can seem like the universe itself has pressed a pause button, leaving you suspended in a timeless void. Yet the secret, the one that turns that stillness into momentum, is that time is never a distant, godlike ruler sweeping across the cosmos. It is the quiet ticking of the internal clock that lives inside every system, every particle, every thought you have. Imagine that clock as the steady beat of a drum you can feel in your chest, the rhythm that guides a dancer through a complex routine. When you learn to listen to that rhythm, you discover that change is not something that must be imposed from the outside. It is something that unfolds naturally through reliable relationships among the things that make up your world. Think of it this way: in the grand equations that physicists use to describe the whole universe, time does not appear as an extra, detached variable. Instead, it emerges from the way different parts of the universe correlate with one another, like the way a sunrise correlates with the chirping of birds and the soft glow of morning coffee. The problem of time, that ancient headache that has puzzled thinkers for generations, dissolves when you see that change is not a march measured by an external stopwatch. It is the pattern of correlations between clocks, fields, geometry, and everything else that we can read and trust. When those patterns line up just right, the movie of reality plays itself, frame by frame, without any need to add an artificial timekeeper into the script. This perspective also reshapes how you understand the arrow of time, that one-way street from past to future that we all experience. The underlying framework itself does not dictate a direction, it's the specific arrangement of records and correlations in our universe that gives us that sense of forward motion. Entropy grows because the configurations that pair a larger reading of the internal clock with an expanding tapestry of redundant records are the ones that actually occur. You remember your childhood because physical marks photons reflected from old photographs, the fossilized impressions in your mind, the data written into the environment when the clock was at a smaller reading accumulate as the clock ticks forward. In the same way, each new day adds fresh pages to the story of your life, and the direction of those pages is what we call the arrow of time. It's not a hidden tick hidden in equations, it's the way the universe layers records upon one another, building a narrative that moves ever forward. What makes this idea truly powerful is that it is not just an abstract philosophical exercise. It can be tested in concrete models, even in the simplest laboratories you can imagine. Picture a miniature universe built from entangled photons on a tabletop. If you designate one degree of freedom as the clock and the other as the system you're observing, the joint state of the photons is stationary. There is no external time flowing, but when you condition on the reading of the clock, a sequence of system states emerges, evolving just as if an external metronome were driving them. Those small experiments do not tell you directly how the cosmos began, but they prove that the logic of emergent time is physically meaningful, not merely wordplay. They show that the very act of conditioning on a reliable internal marker can give rise to the illusion of flow, the illusion we live in every day. In cosmology, the payoff is not a single dramatic signature that flashes across the sky, but a methodological clarity that transforms how we ask questions about the early universe. Instead of smuggling in a background time that the theory refuses to grant, We learn to compute correlations for relics, like the ancient afterglow, by evolving with respect to a clock field that lives inside the universe itself. We learn to match emergent time descriptions across different irracially inflation, reheating, radiation-dominated expansion be handing off from one trustworthy clock to another when the first begins to falter. This handoff happens naturally alongside decoherence, the process by which the clock interacts with the rest of the world and spreads robust records of its readings far and wide. Decoherence suppresses interference between vastly different clock values, ensuring that observers like you will almost never witness a clock in a fragile superposition of wildly separated times. That is why the emergent time you use is not only a calculational convenience, it is operationally real, rooted in the physical marks left behind by the clock's own evolution. The emotional tone of this insight is gentle, not grandiose. It does not proclaim that everything flows by some external decree. Instead, it whispers that the flows that truly matter are the ones you can read from the world around you, and that those flows are rich enough to carry galaxies, stars, and every breath you take. It invites intellectual humility. Never force a clock into your equations that no instrument could ever consult, and summon practical courage to make predictions as conditional statements tied to real physical markers. In a universe without an external metronome, meaning lives in patterns you can test, when a scalar field takes a particular value, expect a certain distribution of ripples. When the average size of space reaches a given scale, anticipate a mix of matter and light that matches those conditions. By reading the universe in this way, the cosmos ceases to be a film projected by an unseen projector. It becomes a library of correlated pages that you can thumb through by following a trustworthy internal bookmark. The quiet miracle is that this library is sufficient to recover the entire story, past, present, and anticipated future without ever stepping outside the book. Mini-superspace models act as the toy laboratories where these ideas are tested. They take the sprawling, unsolvable puzzle of the full quantum universe, with every wrinkle of geometry and every buzzing field, and sand it down to a smooth block with only a few moving parts. If that reduced block still tells a faithful story, you know you've built a good toy. In these models, the sky's astonishing uniformity on large scales justifies a bold simplification. Assume the same curvature and matter content everywhere, and keep only a handful of global variables like the overall size of the universe and the value of a representative field. With that symmetry reduction, the monstrous wave function of all possible geometries collapses to a tractable wave function of a few variables. And the Wheeler-DeWitt constraint becomes a one- or two-dimensional equation you can actually solve, plot, and argue about. The payoff is immediate. You can ask sharp questions about what counts as a good initial condition for the universe. Should the universe begin with a smooth cap or a tunneling jump? How do you read time when no external clock is allowed? By picking one variably a scalar field, the volume, or something else is a relational clock, you can explore how quantum rules might tame classical disasters like singularities. Imagine a homogeneous, isotropic universe whose only shape parameter is a scale factor that tells you how big space is at a given stage, coupled to a single scalar field that acts as the engine of energy. In the mini-superspace arena, the half-plane spanned by scale factor and field becomes the playground, and the quantum state is a wave spread over that plane. Different boundary proposals become different boundary conditions on this wave. Some choices demand regularity as the scale shrinks, others favor an outgoing behavior that reads like creation. Because everything is small enough to visualize, you can watch how these rules weight different histories. Do they prefer a brief, gentle expansion, or a long, fast one? Do they seed ripples with a particular tilt or amplitude? Do they allow a bounce that avoids a singular start? Each of these possibilities writes a different set of records, a different set of pages in the library of the universe. When you carve the timeless state into an apparent movie by choosing a variable as a clock, slices of constant field value line up as snapshots of the scale's probability distribution. Under semi-classical conditions, those snapshots evolve as if guided by a familiar equation, complete with an emergent arrow of time. When the structure of correlations favors growth of records, as the clock increases, the toy laboratory earns its keep again. The deeper you go examining factor ordering, The quantum ambiguity of how to arrange position-like and momentum-like ingredients you discover how short-distance behavior of the solutions can change. In many superspace scenarios, you can try alternatives, checking which ones yield finite, well-behaved energy densities and which secretly smuggle in pathologies. The choice of variables matters, too, working with the scale, its logarithm, or the volume changes which regions of the plane are numerically stable. The lab lets you diagnose spurious reflections of the wave at artificial boundaries and fix them with better coordinates or absorbing conditions. If you add a touch of anisotropy, upgrading to a Bianchi-type toy where the universe can stretch differently along 3 axes, you learn whether your conclusions survive the first break from perfect symmetry. Sometimes they do, and emergent time still works. Sometimes they don't, and a proposed singularity cure fails once the universe can shear. Switching frameworks, you encounter loop-inspired mini-superspace, where the scale factor is replaced by variables better suited to quantum geometry. The difference equation that replaces the usual Wheeler-DeWitt form can generate an effective repulsion at tiny volumes. In the toy lab, you can chart when that repulsion is robust versus when it is a mirage of approximations. And you can map which matter contents preserve the bounce and which spoil it. Crucially, mini-superspace does not live on philosophy alone. It touches data by being the front end of prediction pipelines. Start a toy universe with a chosen boundary rule. Let the scalar roll and the background expand according to the effective dynamics you computed, then propagate small test fluctuations on top to extract the tilt and amplitude of primordial ripples. Plug those into the same observables. Satellites measure how the strength of temperature variations changes with scale, whether the geometry looks flat to exquisite precision, how loud primordial gravitational waves should be. Discard toy rules that wildly disagree with what the sky tells us. Because the lab is small, you can also scan the toy's parameter space, feel potential slopes, initial patch sizes, apply priors that encode simplicity or naturalness, and ask which regions predict skies like ours without fine-tuning. The exercise usually rewards humility. Many beguiling beginnings collapse under the weight of energy bookkeeping, or predict features the sky simply doesn't have, while a few sober corners survive, guiding where full theories should aim. Mini-superspace also teaches you how fragile claims about back reaction or quantum rescue of singularities can be if you ignore careful bookkeeping. Turn on particle creation at the end of a rapid expansion and follow the energy. The wave for the background should tilt as energy transfers to matter. If your toy predicts no tilt, it's missing the feedback. If it predicts a runaway, it's violating conservation or double-counting excitations. Either way, the lab forces a fix before you dare scale up. Try to store too much precision in your clock, and the lab shows you the cost quantum spread that backreacts on geometry and spoils the clock's reliability. Try to use a clock that stalls, and your emergent evolution becomes multi-valued, exposing the multiple choice problem and prompting you to choose a better marker or to glue together charts that overlap consistently. Even decoherence, the handoff from delicate quantum possibilities to sturdy classical initial conditions, gains a fresh angle here. All of these technical details converge on a simple, empowering truth. The rhythms you use to navigate the world are not imposed from a realm beyond you, they are woven into the very fabric of the systems you inhabit. When you choose a good internal clock, whether it's a daily routine, a set of values, a habit of reflection, you create a reliable reference that lets you read the story the universe writes for you. Barred clocks, those that stutter, reverse, or cease to be monotonic, lead to confusion and a sense that everything is static. But when you align yourself with a steady, trustworthy beat, the emergent notion of time becomes a powerful tool, guiding you through change, growth, and transformation. Imagine your life as a giant, ever-expanding library. Each experience, each decision, each moment of learning adds a new page, a new record that layers onto the previous ones. The arrow of time is simply the direction in which these pages accumulate, the direction in which the library grows richer and more detailed. You don't need an external metronome to feel that progression. You feel it in the way your memories are encoded, the way your skills compound, the way the world around you records your influence. The internal clock you cultivate your habits, your curiosity, Your commitment to showing up acts as the bookmark that lets you flip from one chapter to the next with confidence. When you face a problem that feels static, remember that the trick is to look for that internal rhythm, that aspect of the situation that changes reliably and can serve as a reference. Align your actions with that rhythm, and the seeming immobility dissolves into motion. Just as physicists condition on a clock field and watch a stationary quantum state unfold into a sequence of evolving snapshots, you can condition on a personal and perhaps a morning meditation, a nightly review, a weekly goal, and watch the static landscape of challenges transform into a flowing narrative of progress. The journey through space, through toy models, through the careful selection of variables and boundary conditions, mirrors the journey of personal growth. You start with an overwhelming complexity, the full quantum universe of your life, with every worry, every ambition, every fear. You then apply symmetry reductions, focusing on the most essential variables: your core values, your primary objectives, the experiences that truly shape you. The massive wave function of possibilities shrinks to a tractable wave of a few dimensions, allowing you to solve, to plot, to argue with yourself about what a good initial condition looks like. Do you begin your day with calm or with a burst of urgency? Do you frame setbacks as tunnels or as gentle caps? By answering these questions, you create a foundation upon which a reliable internal clock can tick. And just as physicists test the robustness of their models by adding anisotropy, changing variables, or exploring loop-inspired alternatives, you test the strength of your internal rhythm by introducing new challenges, by shifting contexts, by asking whether your habits hold when the scenery changes. Sometimes the clock keeps ticking smoothly, sometimes you discover that a particular habit falters under stress, revealing a multiple-choice problem where different reasonable clocks might yield different outcomes. The key is consistency in the overlaps, ensuring that when two reliable markers intersect, they tell the same story. That consistency becomes a powerful filter, guiding you toward the models of yourself that are truly acceptable. Decoherence, in the cosmic sense, is the process by which the clock's readings become widely recorded, suppressing interference between wildly different possibilities. In your life, decoherence is the moment when your actions become visible, when they leave tangible marks on the world: a finished project, a kind word, a habit formed. Those records stabilize your internal clock, making it less likely that you'll find yourself in a fragile superposition of wildly divergent paths. The more robust the records, the more confidence you have that the direction you're heading in is real, not an illusion. All of this leads to a gentle, yet profound invitation. Embrace the idea that the flows that matter are the ones you can read, the ones that are rich enough to carry the weight of galaxies, and the subtlety of a single breath. Practice intellectual humility. Never force a clock into your understanding that no instrument could ever consult. At the same time, summon practical courage, make predictions, test them against the marks left behind, refine your internal markers, and let the universe answer back. When a scalar field reaches a certain value, expect a particular ripple. When your personal scale factor reaches a new level of maturity, anticipate a mix of experiences that reflect that growth. The universe does not need an external projector, it needs a trustworthy internal bookmark. And you, dear listener, possess that bookmark. By aligning with a reliable internal clock, whether it is a disciplined routine, a set of guiding principles, or a habit of reflective practice, you can turn static problems into flowing narratives, turn uncertainty into direction, and turn the abstract notion of time into a concrete tool for transformation. The library of your life is already being written. Each day you add a page. Each choice you make adds a record. Embrace the quiet miracle that these records are enough to reconstruct the whole story, past, present, and future, without ever stepping outside the book. So, as you move forward, remember the lessons of the cosmos hidden in these simple models. When you encounter a challenge that feels unmoving, seek the internal rhythm that continues to change. Let your actions align with that rhythm and watch the static dissolve into motion. Treat your values and habits as the clocks that condition your experience, and let the emerging narrative unfold with the same graceful certainty that physicists find in the conditional evolution of a timeless quantum state. In doing so, You become not just an observer of the universe's grand story, but an active author, using the most reliable time you have at the time written in the very fabric of your being. Imagine stepping into a quiet laboratory, not of glass and steel, but of ideas where the universe itself becomes a playful toy you can stretch, twist, and examine from every angle. In this space, you discover that the very act of shaping a model, of giving it a new direction, reveals whether the conclusions you draw can survive the first crack in perfect symmetry. Sometimes they do, and the emergent flow of time carries on untroubled. Sometimes they don't, and the elegant singularity you hope to cure crumbles when the cosmos learns to shear. Each subtle change is a fresh experiment, a chance to see how resilient your intuition truly is. What if, instead of fixing the scale factor as the only ruler of expansion, you replace it with variables that speak the language of quantum geometry? In this mini-superspace, the familiar Wheeler-DeWitt equation fades away, giving birth to a difference equation that can whisper of repulsion when volumes become tiny. The toy universe you build becomes a canvas where you can chart exactly when that repulsive push is a sturdy feature of the model, and when it is merely an illusion born of approximation. You learn which kinds of matter preserve a graceful bounce and which ones sabotage it, turning abstract speculation into a hands-on test of durability. The beauty of this miniature cosmos is that it never lives in the realm of philosophy alone. It reaches out to the data, becoming a front end for real prediction pipelines. Picture starting your toy universe with a carefully chosen boundary rule, letting a scalar field roll, and watching the background expand according to the effective dynamics you have derived. Then, layer on tiny test fluctuations and extract the tilt and amplitude of the primordial ripples that would have been imprinted on the sky. Feed those numbers into the exact same observables that satellite experiments measure how temperature variations change with scale, whether the geometry appears flat to extraordinary precision, how loudly the primordial gravitational waves would sing. When the toy's forecasts clash with the data, you discard those rules without hesitation, confident that the laboratory's modest size allows you to explore every corner of parameter space, to feel the shape of potential slopes, to apply priors that honor simplicity and naturalness, and to ask solemnly which regions predict a sky like ours without demanding an impossible fine-tuning. Each iteration of this practice reminds you of humility. Many alluring beginnings dissolve under the weight of energy bookkeeping, or they predict features the heavens simply refuse to show. A few sober corners, however, survive, shining a light toward where a full theory ought to aim. In this compact arena, you also discover how fragile claims about back reaction or quantum rescue of singularities truly are. Turn on particle creation at the tail end of rapid expansion, follow the flow of energy, and watch the background's wave tilt as it hands energy to matter. If your toy predicts no tilt, you know it has missed essential feedback. If it predicts a runaway, you realize it violates conservation or has double-counted excitations. The lab forces you to mend these cracks before daring to scale up to grander theories. There is also a lesson in precision. Attempt to store too much exactness in your clock, and the laboratory shows you the price of quantum spread that back-reacts on geometry, spoiling the clock's reliability. Use a clock that stalls, and the emergent evolution becomes multivolued, exposing the multiple-choice problem and nudging you toward a better marker or a patchwork of overlapping charts that hold together consistently. Even Decoherence, the graceful handoff from delicate quantum possibilities to sturdy classical initial conditions, sits a fresh perspective here. By coupling your system's variable scale field and a simple environment of surrogate mods, you can watch interference between macroscopically different histories fade away. Identify the pointer that becomes classical, often the curvature or density contrast, and assign a concrete time scale for when the toy's predictions become the seeds that later structures inherit. None of this suggests that mini-superspace holds the entire truth. Its virtue lies in telling some truths with crystal clarity while exposing temptations in a flash. It will not settle the measure problem for infinite ensembles of universes, but it will reveal how specific cutoffs bias probabilities long before you graduate to full complexity. It will not prove the universe bounced, yet it will teach you which bounce stories survive the first non-trivial perturbation and which are merely artifacts of polished symmetry. It will not manufacture primordial gravitational waves on demand, but it will warn you when a toy predicts a tensor signal so large that a single season of polarization data would already have caught it, allowing you to sweep that version away. Perhaps most importantly, this modest laboratory forges good habits. Never add a clock you cannot, even in principle, read. Never allow an initial condition that hides infinite energy behind elegant phrasing. Never trust a prediction that flips when you switch to an equally valid set of variables. Always verify that your small quantum system settles its energy bills with the background it rides upon. Close the lab, step back, and feel the emotional tone settle into steadiness rather than grandeur. These toys are not the universe, they are honest rehearsal rooms where daring ideas about beginnings, time, and quantum geometry learn to keep rhythm, where sloppy metaphors are replaced by computable statements, and where simple pictures either earn the right to scale up or are gently retired. If a full quantum theory of cosmology is a symphony we strive to hear, then many superspace models are the scales and attitudes that train our fingers. They are modest, disciplined, and when played well, they carry just enough of the melody for us to recognize the song the cosmos might actually be singing. This brings us to the next frontier, the measure problems that arise when we imagine an endless cinema where every possible film flickers on infinitely many screens. Some movies start now, some finish now, some loop, some pause, and you are asked a simple question with slippery stakes: what is the chance you will see a scene like yours next? This riddle becomes technical once you accept a framework like eternal inflation, where new cosmic rooms spawn without end. Ordinary ways of counting frequencies collapse, and predictions begin to depend not on physics, but on how you choose to count. Begin gently. In a finite box, you might say 20 red marbles out of 100 total. In a multiverse, you confront infinitely many reds out of infinitely many total, leaving the ratio undefined until a regulatora rule that slices the infinite into manageable pieces is introduced, after which a limit is taken. The gut punch is that different sensible regulators can give different answers. One common family uses global time cutoffs, count all events that happen before a certain time, compute ratios, then push the cutoff later and later. Naively, that sounds fair, yet proper time, scale factor time, and light cone time each weight regions differently and can produce wildly different typical observers. Proper time cutoffs, for instance, prefer very young regions because volume balloons explosively, leading to a youngness paradox where the prediction skews toward hot stars, unformed galaxies, or even an absurd expectation that the night sky is still turning on. Scale factor or light cone cutoffs tame that bias but introduce quirks like an end-of-time effect, where probabilities depend on when your clock runs out, favoring quick, flashy processes over slow, steady ones. Local measures take another tack. Rather than surveying the entire infinity, they follow a single world line and count only what falls inside a causal patch or diamond. This avoids volume-related pathologies and can suppress oddities like freak observers. Yet it trades them for sensitivity to the path you chose and ambiguities about how to start the watch. Two notorious headaches must still be confronted. First, a Boltzmann brain's rare thermal or quantum fluctuations that, in a vast future, can assemble momentary hallucinating observers from noise. If your measure weights late-time volume too heavily, such brains outnumber ordinary evolved observers by staggering factors, leading you to predict with unsettling confidence that you are one of them, complete with fabricated memories. That is not a cute paradox, is a red flag that your counting has turned physical nonsense into statistical dominance. A defensible measure must guarantee that ordinary observers like us, arising from thermodynamic histories rich with records, overwhelm these freak fluctuations. Second is the referencer class problem. Even if you fix a regulator, you must decide what you mean by observers like you. Do you condition only on carbon-based life on galaxies roughly like ours with a cosmic microwave background at 2.7 K? Or do you include your entire detailed dataset cosmic parameters, chemical abundances, planetary ages, and so on? This self-locating uncertainty in physics clothing can tilt probabilities dramatically. Count too broadly, and you drown in regions where life is nearly impossible. Count too narrowly, and you hardcode your conclusion. A mature measure, therefore, must specify its xerographic distribution, the prior that says how typical you expect to be within the allowed set, because typicality is not a law of nature, but an assumption you must own. With these snares laid out, ask what good measures strive to achieve. One guiding principle is cutoff independence. As you move your cutoff outward, ratios should stabilize robustly, converging to the same values regardless of small variations in the regulator. Otherwise, you have built a thermometer that reads your method, not the world. Another principle is covariance and locality probabilities should not depend on arbitrary coordinate choices and should be computable from physical local data, not from distant bookkeeping hoops. A third is continuity and sanity. Small changes in microphysics should not trigger avalanches of probability shifts. The measure should not reward runaway production of any one type of object simply because your regulator loves it. When you apply these filters, many attractive-sounding schemes fall away, and the survivor-slight cone and scale factor cutoffs, Cosmology measures, stationary watcher constructions tend to produce overlapping, more restrained predictions. They suppress youngness, avoid Boltzmann brain domination for sensible cosmological constants, and yield probability spreads that can be tested against the one sky we possess. That testing is subtle but concrete. The multiverse is not a license to shrug, it is a recipe for comparative statistics. You compute distributions for observables, such as curvature close to zero, but not exactly. The amplitude Q of primordial fluctuations within a Goldilocks band that allows galaxies to form, and a small positive dark energy density that neither rip apart structure nor cause a premature recollapse. Anthropic reasoning then acts merely as a filter that says no observers exist in empty deserts, not as a cure-all. The measure supplies the baseline frequencies, habitability carves out viable islands, your data set selects the relevant shoreline. Done carefully. This pipeline can explain why we observe a cosmological constant absurdly small compared to naive particle physics scales yet not zero, and why the initial ripple amplitude sits in the narrow band that births galaxies without collapsing everything into black holes or leaving the cosmos featureless. These successes are not proofs, they are consistency checks that show the machinery can produce our world without absurd fine-tuning. Equally important are the go-no-go criteria any measure must pass to remain plausible. It must not predict that the most common observers with our data are Boltzmann brains. It must not wager overwhelming odds on values of curvature or fluctuation amplitude we have already ruled out. It must not create paradoxes like the Q catastrophe, where the most probable universes make structures so alien that our sky would look entirely foreign. Finally, it must survive sensitivity audits, flip from one regulator in the same equivalence class to another, and verify that key predictions barely budge. In practice, progress looks like this. Build a landscape model that encodes how different Vacua different low-energy rules are populated. Compute transition rates. Choose a measure that passes the sanity filters. Then propagate to observables and compare to data curvature bounds, the pattern of acoustic peaks, limits on primordial gravitational waves, demographics of galaxy formation over cosmic time. Each null result and each precise bound tightens the leash on which measures and landscapes are allowed to wander. There is also a human-scale moral that keeps your head clear, remain humble in the face of infinity, disciplined in the face of complexity, and curious in the face of mystery. So, as you close your notebook today, remember that the toys you build are honest rehearsal rooms where daring ideas learn to keep rhythm. They are modest, disciplined, and when played well, they carry just enough of the melody for you to recognize the song the universe might actually be singing. Each time you stretch a parameter, each time you watch a bounce survive a perturbation, each time you confront the multiverse's measure problem, you are training not only your scientific intuition, but also the resilient spirit that turns curiosity into discovery. Keep building, keep testing, keep refining your clocks, and keep listening for the subtle beat of the cosmos. The symphony is far from complete, but every note you master brings the final performance a little closer. When you step into the grand arena of cosmology, you quickly discover that not every glittering idea survives the rigorous test of reality. The moment you apply the right filters, many of the most seductive schemes dissolve, leaving behind a tighter set of possibilities. Picture a landscape of light cone cutoffs, causal diamonds, and stationary watcher constructions that converge on a common, restrained prediction. These tools dim the allure of youthful exuberance, keep the Boltzmann brain menace at bay, and shape probability spreads that can be confronted with the single sky we actually observe. The testing is subtle, yet it is concrete, and it reminds us that the multiverse is not a free pass to abandon responsibility. It is a call to engage in disciplined comparative statistics. You begin by calculating distributions for observables that we can actually measure. Curvature, for instance, should hover close to zero, but it need not be exactly zero. The amplitude of primordial fluctuations, denoted by Q, must land in a Goldilocks band large enough to allow galaxies to form, yet not so large that structures tear themselves apart, and not so negative that the universe collapses back on itself. This is a fresh condition that speaks directly to the data we truly possess. Anthropic reasoning now acts only as a filter that simply says, no observers can live in empty deserts, rather than as a magical cure-all. The measure you adopt provides the baseline frequency's habitability, then carves out the viable islands, and your data set traces the relevant shoreline. When you walk this pipeline carefully, you can explain two of the most baffling facts about our universe: why the cosmological constant is absurdly tiny compared to the naive scales of particle physics, and why the initial ripples sit comfortably in the narrow range that births galaxies without collapsing everything into black holes or leaving the cosmos barren. But let's be honest, these successes are not ironclad proofs. They are consistency checks that demonstrate the machinery can reproduce our world without resorting to absurd fine-tuning. Equally crucial are the go-no-go criteria. Any measure must satisfy to remain plausible. A viable measure must not predict that the most common observers sharing our data are fleeting Boltzmann brains. It must not gamble overwhelming odds on curvature values or fluctuation amplitudes we have already ruled out. It must steer clear of paradoxes like the Q catastrophe, where the most probable universes would look alien compared to our sky. Moreover, a trustworthy measure must survive sensitivity audits. If you switch from one regulator to another within the same equivalence class, the key predictions should barely budge. In practice, progress looks like this. You construct a landscape model that encodes how different Vacua and low-energy rules are populated. Then you compute transition rates. Next, you choose a measure that passes the sanity filters, propagate the consequences to observables, and finally compare them with data curvature bounds, the pattern of acoustic peaks, limits on primordial gravitational waves, the demographics of galaxy formation over cosmic time. Every null result and every precise bound tightens the leash on which measures and landscapes are allowed to wander. This process is not simply an abstract game, it keeps your head clear when infinities tempt you to replace physics with poetry. You must keep asking operational questions given our dataset D. What relative odds does this regulated convergent scheme assign to neighboring values of the cosmological constant? You demote metaphysical grandstanding and focus on the one universe whose ticket you actually hold. The measure problem, then, is not a defect glued onto the multiverse. It is the price of doing probability in an infinite setting. And the reward for paying that price carefully is discipline. You learn to separate regulator artifacts from genuine predictions, to distinguish selection effects from explanations, and to own your typicality assumptions instead of hiding them. As the emotional tone settles, it becomes steady rather than dizzying. You are not asked to care about an uncountable bazaar of exotic bubbles, you are asked to count fairly in a world that may be unbounded, to prefer measures that keep your conclusions stable as the cutoff recedes, and to read our sky as one sample drawn from a distribution shaped by dynamics, habitability, and honest bookkeeping. When you do that, the multiverse stops being a word that licenses anything and becomes a framework that forbids many things, guiding you toward models that are not only imaginative, but also accountable to the single universe you can test. Now turn your attention to another frontier that feels like a doorway into the very fabric of reality holography for a universe with a positive vacuum energy. The kind of universe we inhabit. Stand on a hill at dusk and notice how the horizon closes you in. No matter how far you walk, there is always a circle of sky you cannot cross. That feeling is the right entry point into the puzzle of holography for D-sitter space. Because our universe's accelerating expansion builds horizons for every observer, it forces us to ask whether the information describing a vast region is somehow encoded on a lower dimensional boundary that we can never touch, yet that still keeps the bookkeeping straight. Begin gently. Holography proposes that a full gravitational world can be equivalent to a non-gravitational theory living on its boundary. In Antide-Sitter space, where gravity naturally terminates at infinity, this idea blooms into a precise dictionary between bulk physics and an ordinary quantum field theory. De-Sitter space, by contrast, curves the other way and offers no time-like boundary where observers can hang a screen and define an external time. Instead, it presents two strange book-and-spast and future infinity that are space-like caps you can only approach in imagination, plus a personal horizon around each observer that radiates with a gentle temperature and carries a finite entropy proportional to its area. Those geometric facts set the stage for both promise and pain. The promise lies in the finite horizon entropy, hinting that any one observer's world contains only a finite number of independent degrees of freedom. That clue tells us a compact description must exist. The pain arises because, lacking a shared global wall or a shared global clock, we cannot simply copy the Antide-Sitter playbook. What, then, could holography mean in this context? One line of thought places the dual theory, not at a wall you can visit, but at the future boundary, where the entire inflating history of a region projects as a kind of final snapshot. In this spirit, the late-time wave function of the universe behaves like the generating functional of a Euclidean field theory, living on that boundary sphere, and operator dimensions in that theory would encode decay rates and late-time ringing of bulk fields. A second, more personal line asks for a hologram for the static patch of the finite region an observer can ever access. Here the screen is the observer's own horizon. The bookkeeping happens in a Hilbert space whose total size matches the horizon entropy, and bulk events are reconstructed not from a distant wall, but from the pattern of correlations across the sky that the horizon mediates. A third thread tries to meet de-Sitter halfway by analytic continuations start with Antide-Sitter correlators, rotate to imaginary angles that turn attraction into repulsion, and read the resulting objects as de-Sitter correlators. This maneuver is mathematically crisp in toy models and connects the quiet start vacuum often used in cosmology to a smooth Euclidean cap, but it risks hiding the hard physics behind a change of variables if we don't spell out what the dual degrees of freedom really are. To deepen the picture, name the obstacles clearly, because each one teaches a lesson. First, there is no global matrix for de-Sitter spacino-spatial infinity where you can define clean in and outs to tesso the dual cannot be a straightforward scattering theory. Second, horizons make observers inherently parochial. What is resolvable in my patch may be forever inaccessible in yours. This suggests that a single global description might double-count states unless it respects redundancy. Ideas like complementarity propose that different observers' accounts are consistent, but not simultaneously realizable, much like different views of the same black hole horizon. Third, the finite entropy of the horizon whispers that the Hilbert space for a static patch might be finite-dimensional radical thought that clashes with the infinite tower of modes we usually write for fields. If that finiteness is real, the hologram's degrees of freedom must be organized very differently from familiar quantum field theories. Fourth, the late-time expansion that makes de-Sitter space so smooth also washes away local landmarks. So bulk reconstruction figuring out what happened deep inside from data on the boundary must rely on subtle relational markers, rather than sharp echoes from a rigid wall. Even with those knots, the last decade has sketched tools that begin to feel like a de-Sitter dictionary rather than poetry. Quasi-normal spectra of fields in de-Sitter relate to prospective operator data at the future boundary, giving concrete matching conditions. Lower dimensional models where gravity collapses to a single function of curvature admit clean de-Sitter cousins of Antide-Sitter constructions, showing how thermal horizons emerge, how late-time correlators organize, and how a boundary theory with no conventional time evolution can still encode relational dynamics. The language of quantum error correction, so powerful in Antide-Sitter, is being generalized to curved, observer-dependent wedges. Information in a de Sitter patch appears redundantly encoded in multiple overlapping screens, hinting that reconstruction will be robust against local erasers, mirroring the stability of classical reality in cosmology. Entanglement wedge ideas have been repurposed into island formulas that, in black hole settings, explain how entropy flows. In cosmology, exploratory work asks whether similar islands organize the entanglement between a static patch and its outside, potentially clarifying why horizon entropy is finite and how information is parceled across the sky. There is also a pragmatic bridge to observation. While no one expects to read a literal boundary conformal field theory off the microwave background, the holographic viewpoint constrains what late-time correlators should look like if a dual description exists, how they should fall off, which shapes of higher point statistics are natural, and which deformations are consistent with a finite patch's bookkeeping. Those constraints feed back into the template banks that experiments use when they hunt for faint departures from simple initial conditions. A separate sobering current flows in from string theory. Fully controlled metastable de Sitter vacua are hard to build, and this difficulty has sparked conjectures that stable de Sitter may not belong in the deep landscape of consistent theories. If that is true, the right holographic description could be of a universe that only approximates de Sitter for long stretches before sliding away. The dual would then need to capture not only the static patch, but also its slow evolution. Far from weakening holography, this possibility makes it sharper by demanding a dictionary that respects drifter boundary description with softly running couplings, a spectrum that changes in step with the horizon size, or a chain of jewels patched together across eras. Through all of this, one theme remains: calming and concrete. The horizon's thermal character and finite entropy are not optional decorations. They are the signature that any candidate dual must reproduce. A good proposal should explain why every observer measures the same gentle temperature, why information cannot be cloned across overlapping patches, and why the number of independent pixels available to draw a static patch world is finite and set by the horizon's area. It should also honor the relativity of simultaneity baked into de Sitter space. Different observers slice their patches into nows differently, so any boundary description must be written in relational terms, making predictions that do not depend on a hidden preferred clock. Step back and notice that the emotional tone of holography for de Sitter is not triumphal but instructive. Antides Sitter taught us that gravity can sometimes be translated into a boundary language with exquisite precision. De Sitter, nearer to our actual sky, teaches us humility about what counts as a boundary, about how much information an observer can honestly claim, and about how physics should be phrased when horizons are unavoidable. If a clean de Sitter hologram is possible, it will likely look less like a single eternal theatre and more like a network of overlapping playbills, each tied to a patch, each finite, each consistent where they overlap, and together robust enough to reconstruct a universe that accelerates. So, as you venture forward, remember that the multiverse measure problem and the search for a de Sitter hologram share a common spirit. They both demand rigor, humility, and a willingness to let the data guide you through infinite possibilities. They invite you to harness the power of disciplined statistics, to respect the finite information every horizon grants, and to build models that are as accountable as they are imaginative. This mindset turns bewildering abstractions into tools you can wield with confidence. It transforms the cosmic landscape from a chaotic bazaar into a well-charted map, where each step you take is guided by clear criteria, testable predictions, and the steady knowledge that the universe you observe, though singular, is the ultimate laboratory for your ideas. Embrace that discipline, and let it fuel your curiosity. Let the horizon's gentle glow remind you that even in an ever-expanding cosmos, there are boundaries you can honor and questions you can answer. Let the interplay of measure and holography inspire you to seek elegance without sacrificing rigor, to dream big while staying grounded in what the sky actually tells us. In doing so, you become not just a consumer of lofty theories, but a craftsman who shapes them, testing each stroke against the one universe whose ticket you hold. The journey is challenging, but it is also profoundly rewarding. Each consistency check, each sensitivity audit, each holographic insight adds a brick to the bridge between imagination and observation. As you walk that bridge, you carry with you the confidence that your work is rooted in careful reasoning, that your conclusions are stable as the cutoffs recede, and that the story you tell about the cosmos is both bold and accountable. This is the true power of disciplined, motivated inquiry transforming the vast, sometimes intimidating, tapestry of the multiverse and quantum gravity into a narrative you can understand, test, and, most importantly, share with the world. Imagine standing at the edge of an ever-expanding horizon, feeling the gentle warmth of a cosmic fire that never quite goes out. That warmth is not a random glow, it is a signal, a promise that the universe is speaking to us in a language of curvature and information. In the world of theoretical physics, we have learned to simplify the messy dance of gravity into elegant equations that whisper of lower dimensional models, where a single function of curvature holds the key to entire families of universes. These models give us clean, de Sitter-like cousins of the more familiar anti-de Sitter constructions, and they open a window onto how thermal horizons emerge, how correlations at late times organize themselves, and how a boundary that does not evolve in the traditional sense can still encode the relational dynamics of everything we observe. What does this mean for you? Listening with curiosity and a thirst for meaning. It means that the very fabric of reality is arranged like a resilient tapestry, where information is woven into overlapping screens that protect it from loss. Just as a master weaver repeats patterns across a cloth so that a small tear does not unravel the whole design, the information inside a patch of de Sitter space is redundantly encoded across many overlapping regions. This redundancy gives us a kind of cosmic error correction, a safeguard that mirrors the stability of the classical world we experience every day. When a local disturbance tries to erase a piece of this information, the rest of the tapestry steps in, preserving the whole. The idea is both profound and empowering. We live in a universe where the rules of reality themselves are built to be robust, to survive the inevitable imperfections that arise. From this perspective, the famous concept of an entanglement wedge, originally crafted to understand black holes, takes on a new life. In those extreme environments, island formulas explain how entropy flows, how information that seemed lost can reappear, and how the bookkeeping of the cosmos remains consistent. In the broader cosmological setting, researchers are now asking whether similar islands might organize the entanglement between a static patch of space and everything beyond it. If this is true, it could illuminate why the entropy associated with a horizon is finite and how information is parceled across the sky, turning abstract theory into a concrete description of the universe's bookkeeping system. You may wonder how these lofty ideas connect to what we can actually observe. While no one expects us to read a literal holographic code off the microwave background, the holographic viewpoint provides powerful constraints on the shape of late-time correlators. It tells us how these correlators should fall off, which higher point statistics feel natural, and which deformations respect the finite bookkeeping of a patch of space. Those theoretical constraints have a direct line to the templates that experimentalists employ when they hunt for faint departures from simple initial conditions. In other words, every time a telescope points toward the sky, and every time a data set is sifted for subtle anomalies, the underlying holographic principles are subtly guiding the search, sharpening the questions we ask of the cosmos. Yet not all is smooth sailing. From the depths of string theory comes a sobering note constructing fully controlled, metastable de Sitter vacuethos long-lived. Gently expanding universes has proven exceedingly difficult. This difficulty has sparked bold conjectures that stable de Sitter space might not sit comfortably within the deep landscape of consistent theories. If that's the case, then the holographic description we seek would belong to a universe that only approximates de Sitter for enormous stretches before it gradually slides away. The cosmic jewel we hope to capture would not be a static gem but a dynamic, evolving masterpiece, one that must account for drift, softly running couplings, and a spectrum that changes hand in hand with the horizon size. Imagine a series of interlocking jewels, each patched together across eras, together telling a story of a universe that accelerates yet never settles into a single eternal theater. Through all of this, one calming, concrete theme shines through the thermal character of the horizon, and its finite entropy are not optional decorations, they are the signature that any viable description must reproduce. A good proposal must answer why every observer, no matter where they stand, measures the same gentle temperature. It must explain why information cannot be cloned across overlapping patches, why the number of independent pixels available to describe a static patch is finite and directly set by the horizon's area, and why the relativity of simultaneity hallmark of de Sitter space requires any boundary description to be written in relational terms. In other words, the theory must make predictions that do not depend on a hidden preferred clock, but rather respect the way different observers slice their own patches into now. Taking a step back, the emotional tone of de Sitter holography is not triumphalist, but profoundly instructive. Anti-de Sitter space taught us that gravity can sometimes be translated into a boundary language with astonishing precision. De Sitter space, the closest analogue to the sky we actually see, teaches us humility about what counts as a boundary, about how much information any single observer can honestly claim, and about how physics should be phrased when horizons are unavoidable. If a clean de Sitter hologram ever emerges, it will likely resemble a network of overlapping playbills, each tied to its own patch, each finite, each consistent where they intersect, and together robust enough to reconstruct a universe that accelerates. Even if the answer is that de Sitter holography only works as an approximate description over long but finite chapters, that result carries teeth. It would tell us that our cosmos writes its story in volumes rather than on a single wall. That information is budgeted by horizons the way households are budgeted by walls, and that the night circle of sky, which feels both enclosing and honest, is not a mere metaphor, but a clue to the deepest accounting system nature employs. Now turn your attention to the oldest light we can see, the cosmic microwave background. Picture it not as a static photograph, but as a recorded studio take pressed into the sky, preserving quantum signatures that survived fire, expansion, and billions of years of travel. Reading this record is less like mystical divination and more like meticulous forensics. The first and clearest signature is the way temperature ripples and polarization patterns line up across the sky with phases that are strikingly organized, as if countless instruments began their notes together. This phase coherence is exactly what you expect when fluctuations were born as paired, quantized excitations stretched, and set long before plasma physics had time to scramble them. When the young cosmos behaved like a resonant fluid, each wavelength rang with a predictable start time, leaving a ladder of peaks in the power spectrum and a characteristic alternation between compressions and rarefactions. No natural classical process could engineer such global, cross-horizon coordination without fine-tuning. The universe, in its earliest moments, seemed to play a symphony in perfect tempo. If you push deeper, the quantum fingerprints multiply. The near-perfect bell curve statistics of tiny temperature variations are not a random noise, they are the hallmark of a state built from many independent quantum modes, whose only memory of the beginning is their variance. Any large departure from those simple statistics would have screamed of extra drama in the earliest moments. The stubborn smallness of higher-order correlations becomes evidence that the initial state was close to the calmest allowed configuration, that the dynamics that amplified it were gentle. Yet the phrase almost is the operative word. The few places where simplicity must break are themselves signatures. In the squeezed limit where a very long wavelength modulates, shorter one as the three-point correlation is not free to wander consistency conditions, tie its size to the slight tilt of the primary spectrum. This relation is deeply quantum, following from how long and short modes were entangled before the universe's growth locked in their amplitudes. Measuring that relation checks whether those modes were indeed siblings from the same quantized parent or a college of unrelated classical disturbances. Polarization adds another elegant voice. The pattern that looks like gradients, called E-type, traces the same acoustic choreography as temperature, while the Kerr-like pattern, P-type, is special. At the most elementary level, Type polarization can be borne by the stretching of space itself, primordial gravitational waves that would be a direct fossil of quantum fluctuations in the fabric of geometry. No later classical effect can generate that exact long wavelength signature without also leaving telltale messes elsewhere. That's why the search for large-angle bodes is not a branding exercise, but a clean physics question: did spacetime hum at the amplitude expected for a quantized field during the earliest expansion? Lensing by intervening structures converts some E into B, providing a beautiful, calculable foreground that both complicates and empowers the hunt. By mapping and removing that lensing haze, we learn about the cosmic web and clear the stage where any primordial gravitational melody would appear. Another quantum clue hides in scales that never communicated classically by the time the afterglow formed. Correlations across angles larger than the sound horizon at last scattering should have been impossible to coordinate by causal processes inside the plasma. Yet they are present with the right amplitude and phase. That superhorizon order is consistent with modes that were laid down when the causal horizon was tiny, stretched beyond contact, and then re-entered long after. The narrative's middle chapter only makes sense if the seeds were quantum and laid before conventional cause and effect could couple distant regions. The crosstalk between temperature and polarization provides still more diagnostic power. One sees a distinctive outer phase pattern in their cross-spectrum, again reflecting a coherent, clocked set of initial conditions. Any theory attempting to replace the quantum origin with late-time classical sources would struggle to reproduce that alternating fingerprint without contrived knobs. Statistical isotropy, the lack of preferred direction and the near randomness of phases are themselves quantum-born clues. A state drawn from a simple ensemble of independent modes will overwhelmingly look directionless, with phases that carry no memory beyond their variances. When experiments squeeze the data and find only tiny room for preferred patterns, they quietly confirm that the early randomness was of the disciplined, quantized kind rather than a chaotic classical turbulence. Even the limits we place become part of the story. Tight bounds on exotic 3- and 4-point patterns tell us that if unknown high-energy effects shook the earliest modes, they did so with a self-facing touch. Strict limits on any asymmetry between left-handed and right-handed polarization modes say that if spacetime preferred one twist over another at the beginning, it hid that taste all too well. Constraints on correlations that would arise if the initial state had been excited rather than calm show that the sky lacks the small ripples and oscillations such excitement would imprint across scales, pushing us back toward the conservative quantum vacuum start. Looking ahead, new windows promise to extend this forensic work rather than repeat it. Spectral distortions mean departures from a perfect blackbody spectrum could act as counters for power on scales far smaller than those we image today, revealing whether the quantum blueprint stays smooth into the ultraviolet of the early universe or carries tiny model-specific bumps from brief departures in the expansion's tempo. If detected, those distortions would let us weigh quantum history where images cannot go. Cross-correlations between the afterglow and later structures form a consistency lattice. Mapmakers contest whether the pattern of low-redshift galaxies truly is a biased, evolved version of the ancient template written in light, as quantum theory demands, and use any mismatch to flag missing physics. Even cosmic variance, the irreducible blur from having only one sky to sample, is not an annoyance but a truth in the signature. It reflects the fact that we observe one draw from a quantum distribution, rather than a Platonic average. Acknowledging it is part of treating the sky as data about a random process set by early universe rules, not a deterministic script. Finally, there is a quiet, clarifying emotion that comes with reading these marks correctly. Talking about quantum processes in the cosmos is not a license to mystify, it is an invitation to check whether particular, falsifiable patterns phase coherence, near Gaussianity, specific cross-spectra with prescribed alternations match the predictions of quantum mechanics. Polarization curls that only geometry itself can supply appear where they should and are absent where they shouldn't. The Tolly so far is decisive in tone, if not yet final in detail. The sky behaves exactly like a world whose earliest irregularities were the lawful output of quantized fields in a rapidly changing background. Where the data allow deviation, they allow it narrowly. Where new channels promise extra tests, they sharpen the question rather than blur it. Let this settle in your mind. The cosmic microwave background is more than a pale glow. It is a readable album in which the universe kept not only the melody of its first vibrations, but also the studio notes, proving how those vibrations were made by rules that care about amplitudes and phases in exactly the way quantum mechanics says they shouldn't, by a history that carried those notes across billions of years without smearing their meaning. As you walk forward, carry this sense of deep connection with you. The universe, in its grandest symphony, has left clues that are both subtle and robust. By listening, by asking precise questions, by honoring the relational nature of horizons, you become part of the very act of decoding. The story is still being written, and each thoughtful inquiry, each careful measurement, each daring theoretical leap adds a new stanza to the cosmic song. Embrace the humility of the unknown, the excitement of the possible, and the certainty that the world is organized enough for you to understand it if you dare to look, listen, and think with the same relentless curiosity that has driven explorers across seas and scientists across the frontier of space-time. The horizon beckons, the sky whispers, and the universe invites you to join its timeless dialogue. Imagine for a moment that the night sky is not just a backdrop of distant lights, but a living record of the universe's earliest heartbeat. Each photon that drifts down to our telescopes carries a whisper from a time when space itself was still learning how to twist and turn. Scientists have spent years listening to those whispers, looking for any hint that the cosmos might have preferred one spin over another, a subtle left-handed or right-handed tilt in its very fabric. The astonishing fact is that, if such a preference ever existed, it kept itself so well hidden that our most sensitive instruments still see a perfectly balanced pattern. That balance tells us a powerful story. The universe began in a state of quiet calm, without the wild ripples that a more excited beginning would have imprinted across every scale we can observe. Now picture the future of that investigation. New windows are opening that let us peer even deeper, beyond the smooth glow that has long been our cosmic canvas. Tiny departures from a perfect blackbody glow spectral distortions there like delicate brushstrokes that could reveal whether the quantum blueprint that shaped the early universe stayed flawlessly smooth into the most minuscule, ultraviolet realms, or whether it bears the faint fingerprints of brief, dramatic pauses in the expansion. If we ever catch those faint distortions, we will be weighing the universe's quantum history in a way that no photograph can ever achieve, turning abstract theory into a tangible, measurable reality. What makes this pursuit even more thrilling is the way the afterglow of the Big Bang can be cross-checked against the sprawling tapestry of galaxies that formed billions of years later. By mapping the low redshift galaxies, we can test whether their pattern is simply an aged, evolved version of the primordial template that quantum mechanics dictated in those first moments. Any mismatch between the ancient light and the modern structures signals that something new, perhaps a missing piece of physics, has been woven into the cosmic story. Even the inevitable blur that comes from having only one sky to study, known as cosmic variance, is not a nuisance but a profound reminder that we are sampling a single draw from a quantum lottery, not an idealized average. Embracing that uncertainty teaches us to treat the heavens as data born from a random process, guided by the early rules of the universe, instead of a fixed script written in stone. When we truly understand these subtle marks, a quiet, clarifying emotion settles over us. Discussing quantum mechanics on a cosmic scale is not an invitation to mystify, it is a call to test precise, falsifiable patterns. We look for phase coherence in the cosmic microwave background, for tiny deviations that would appear as specific cross-spectral signatures. Polarization curls twists in the light that can only be generated by the geometry of space itself must appear exactly where theory predicts and stay absent where they should not exist. The evidence so far is decisive in tone, even if it does not yet close every door. The universe behaves as though its earliest irregularities were the lawful output of quantized fields dancing in a rapidly changing background. Where the data allow deviations, they do so narrowly, and every new observational channel sharpens the question rather than blurring it. Let that settle in your mind. The microwave background is no longer a pale, distant glow, it is a readable album. a cosmic recording that kept not just the melody of the first vibrations, but also the studio notes that reveal how those vibrations were produced. Those notes follow rules that care about amplitudes and phases, exactly as quantum mechanics predicts, and they have been carried across billions of years without losing their meaning. This realization transforms what once seemed abstract into a tangible, living narrative that we can explore, test, and ultimately understand. Now turn your imagination toward the most daring experiments that push this narrative to its limits: cosmic bell tests that enlist ancient quasars as the universe's own random number generators. Picture distant quasars whose light began its journey toward us before Earth even existed. Their photons become the coins tossed in a grand experiment that decides the settings of detectors measuring entangled particles. By letting the ancient glow of these faraway beacons dictate the choices, we turn the night sky into a cosmic referee, forcing nature to reveal whether entanglement truly defies any hidden, prearranged plan. The design is elegantly simple yet profoundly subtle. In a laboratory, pairs of entangled photons are created and sent to two distant measurement stations. At each station, a fast switch chooses an orientation for the detector based on a binary bit extracted from incoming quasar light, perhaps a blue versus red threshold that instantly flips a decision. Because the quasar photons left their sources billions of years ago, any hypothetical conspiracy that tries to coordinate those ancient emissions with the outcomes of the lab experiment would have to have been set in motion long before our solar system formed. This pushes the freedom of choice loophole where skeptics might claim that hidden variables nudged both the random bits and the particle outcomes back to the dawn of the cosmos. To make this work, experimenters align two telescopes, sometimes small and nimble, directly with the measurement stations. Each telescope watches a different quasar placed far apart in the sky, ensuring that their past light cones overlap only in a thin sliver deep in cosmic history. As a photon from a quasar passes through the telescope's optics, its color is translated into a binary bit that instantly flips the detector's setting. Meanwhile, the entangled pair of photons travels to the stations, arriving in a carefully timed window so that no signal traveling at light speed could link the distant choices. When the recorded correlations between the two detectors exceed the ceiling set by any local hidden variable model, we have a clear violation of Bell's inequality, a testament that the quantum world is not constrained by classical notions of locality and realism. The power of this cosmic twist lies not in theatrical flair, but in how it reshapes the causal chessboard. Earlier Bell tests relied on high-speed electronics to generate the settings, which, while compelling, left a logical opening for an adversary to propose a shared recent past cause. By reaching back billions of years, the experiment forces any such hidden cause to operate on a cosmological scale, bridging the vast gulf between active galactic cores and the thin air above our telescopes. Selecting quasars at high redshift, meaning a long look-back time, and pointing them in opposite directions narrows their shared causal past to a minuscule slice of the early universe, shrinking the window for any coordinated conspiracy to a fraction of a second in cosmic time. Executing such an experiment demands meticulous attention to detail. Researchers must show that the quasar photons are not themselves subject to hidden biases, that atmospheric interference and instrumental noise do not corrupt the randomness, and that timing guarantees every setting decision is truly space-like, separated from both the other station's choice and the emission of its entangled partner. When all these safeguards are in place, the data speak with confidence. The observed correlations beat the local realist limit by margins that cannot be dismissed as detector inefficiency, signal leakage, or accidental coincidences. The remaining loofah-less metaphysical extremes of superdeterminism or retrocausality beyond the usual scientific commitment to statistical independence and forward causal explanations. In other words, the experiment pushes any surviving conspiracies into the realm of philosophy rather than physics. Even as we celebrate these triumphs, humility remains essential. Quasars flicker, their light can be lensed, and the atmosphere is never a perfect conduit. Experimenters therefore build redundant systems, calibrate their instruments against known sources, and run anticorrelation tests to verify that bits at the two stations are statistically independent, except for the deliberately crafted cosmic geometry. They often collocate the telescopes with the measurement stations to avoid long cables that could introduce delays, keeping the timing budget tight and the space-like separation pristine. Some teams go further, using even older light from nearby stars, or aspirationally, the cosmic microwave background itself to push the origin of randomness as far back as possible, tightening the constraints on any hidden coordination. What does all of this mean for you, the curious learner listening with an open heart? It gifts 3 clear lessons. First, the violation of Bell inequalities is not a laboratory trick that only works under artificial conditions. It persists, even when the universe itself flips the deciding coins billions of years ago. Second, randomness is not a mystical, elusive essence but a practical resource that can be strengthened by clever use of cosmic causality. By choosing settings from regions that share no recent past with our apparatus, we transform philosophical doubts into geometric constraints we can measure and test. Third, the loopholes that remain are honest, explicit possibilities, either a universe choreographed from its birth to fake quantum statistics or an influence that somehow reaches backward in time. Both demand explanations that go beyond the ordinary success of scientific reasoning, where we trust that experimental choices are free and causal arrows point forward. Feel the emotional tone settle into a calm respect for the extraordinary care required to turn the night sky into data. Technicians align fragile optics inside cold domes. Statisticians simulate setting streams to bound bias. Observers select targets whose photons have been traveling since before our sun ignited. And theorists trace light cones with rigorous mathematics to prove that no mundane signal could have linked the stations. All of them converge on a single purpose: let the universe decide for itself. In this sense, cosmic Bell tests with quasars become more than a niche in quantum foundations. They evolve into a manifesto for scientific honesty. Whenever doubt points to a loophole, the response is to widen the experiment until ordinary explanations have nowhere to hide. If the result still stands, the only remaining explanations belong to the realm of metaphysics, not physics. Now, take a breath and look up at the night sky. Let it feel different, not distant and passive, but intimately involved in the grand experiment of understanding reality. The cosmos has, without intending to, supplied the random bits that helped confirm that entanglement is not a story we tell about particles, but a real, robust relation that stretches across billions of years and unimaginable distances. The universe itself seems willing to defend that truth, using the very vacuum fields that also drive its accelerated expansion. You have heard that dark energy is pushing the cosmos apart, but beneath that headline lies a simple, profound question: does the universe obey the same quantum rules at its largest scales that we observe in the tiniest particles? By listening to the subtle music of the microwave background, by chasing the faint signatures of spectral distortions, and by harnessing ancient quasar light to test the limits of reality, we are gradually turning that question into an answer. Let this journey inspire you to pursue curiosity with tenacity, to embrace the unknown as an invitation rather than a barrier, and to recognize that every photon that reaches your eye is a messenger from an era when the universe was still deciding how to be. The story of the cosmos is still being written, and you are part of the audience that can hear its next chapter. Keep listening, keep questioning, and let the universe's own whispers guide you toward deeper understanding. Imagine standing beneath a night sky that feels less like a distant backdrop and more like an intimate partner in a grand conversation. Every photon that brushes past your eyes carries a story, one that began long before the sun ever sparked. A tale of particles, fields, and the relentless push and pull of the cosmos itself. You have the privilege of listening, of deciphering those whispers, of turning the vast, silent archive of the universe into data that speaks truth to us all. That truth, however, does not reveal itself by accident. It demands precision, patience, and a reverence for the smallest details. When we set out to test the deepest quirks of quantum reality, we are faced with 3 essential ideas. First, timing and efficiency must be honed like the cadence of a well-practiced drum beat. If the intervals between our measurements are just right, the whole experiment sings in harmony. Second, Randomness is often misunderstood as a mystical fog, but it is simply independency, a practical tool we can strengthen by respecting causal structure. By deliberately choosing the bits that set our apparatus from regions that have never shared a recent past with our own lab, we turn philosophical doubts into concrete, geometric constraints. Those constraints become something you can draw on paper, test in simulation, and watch unfold in real time. Third, any lingering loopholes must be laid bare, honest and explicit, if we are to keep a loco-realist story alive. You either accept a universe that has been choreographed from its birth to mimic quantum statistics, or you entertain the possibility of influences that ripple backward through time. Both narratives can be articulated, yet each bears the weight of explaining why, in everyday scientific practice, we treat experimental settings as free choices and causal arrows as moving forward. The fact that this framework works so beautifully across countless experiments is itself a testament to the care and ingenuity of every person who turns a telescope toward the heavens or writes a line of code to simulate a setting stream. Feel the quiet respect that settles when you think of the technicians who coax fragile optics into alignment inside frigid domes, the statisticians who model setting streams to bound hidden biases, the observers who select targets whose light has been wandering for billions of years, and the theorists who trace light cones to prove that no ordinary signal could have linked distant stations. All of them share a common purpose: to let the world itself decide what is true. In that sense, cosmic bell tests with quasars are far more than esoteric experiments in quantum foundations. They are a manifesto of scientific honesty. Whenever doubt points to a potential loophole, the response is not to hide it, but to expand the experiment until there is nowhere ordinary doubt can linger. If the result endures, it forces us to retreat to explanations that speak more about metaphysics than about straightforward physics. And when you step away from that laboratory, lift your gaze to the heavens, you notice that the sky has changed. It no longer feels remote, it feels involved, a living ledger that, without intending to, supplied the random bits that helped confirm that entanglement is not just a story we tell about particles, but a genuine relation woven through space and time. The universe itself seems willing to defend that truth across billions of years and unimaginable distances. But the story does not stop at quantum quirks. As you contemplate the accelerating expansion of the cosmos, a deceptively simple question surfaces: is the acceleration merely empty space doing what empty space does? Or is there a subtle, lightweight field almost invisible quietly nudging the fabric of reality? Dark energy, whether imagined as a property of the vacuum itself or as a gentle field rolling across the cosmos, reshapes how we read the past, anticipate the future, and decide which measurements are the most honest judges of nature. Begin gently with the vacuum picture, often called the cosmological constant. Picture space itself possessing a constant energy density, a negative pressure that remains unchanged even as the universe balloons. Double the size of a region, and you get 8 times the volume, yet the energy per unit volume stays the same. This stubborn constancy means that as matter thins out, the vacuum's influence overtakes, driving an accelerated expansion. It is a model of brutal simplicity set a constant, and you have a universe that accelerates, yet it is equally brutal in its puzzling nature. Quantum theory, when applied naively, predicts a vacuum energy many orders of magnitude larger than what we observe, a disparity that screams for a deep, hidden cancellation we have yet to understand. Now consider the field alternative, known by names like quintessence or quiescence. Imagine a new, incredibly light degree of freedom, a field whose energy can change over time, sometimes dancing in step with the dominant component of the universe's energy budget, sometimes breaking away to dominate later. Its pressure can be almost as negative as the vacuum's, but not exactly, and this subtle wiggle leaves fingerprints in the cosmic data. A field can be tuned to the right scale without invoking a colossal subtraction, but then you must explain why its mass is staggeringly tiny, why its motion is dictated more by the expansion of space than by particle physics, and why it has evaded detection in laboratory tests that seek exotic forces or violations of the equivalence principle. With these trade-offs laid out, the universe offers us a way to distinguish between them without demanding that we write down complex equations. If dark energy is a strict cosmological constant, its pressure-to-density ratio a number that tells us how pushy it remains locked at -1 for all of cosmic time. If it is a field, that ratio can drift ever so slightly, and the field's own fluctuations might cluster a little or not at all, depending on its internal sound speed. Those tiny drifts and patterns become observable through multiple, independent windows that cross-check each other. Supernovae act as cosmic lanterns, mapping the recent expansion history by telling us how bright objects appear at known distances. The imprint of ancient sound waves in the distribution of galaxies known as baryon acoustic oscillations offers a standard ruler that measures how the scale of the universe has grown. Weak gravitational lensing, the subtle bending of distant galaxy light by intervening mass, senses both geometry and the rate at which matter assembles into structures. Redshift space distortions in galaxy maps gauge how galaxies flow into clusters, revealing the strength of gravity's pull in the late universe. And the cosmic microwave background, the afterglow of the Big Bang, carries a late-time temperature shift that records whether the gravitational wells of larger-scale structures are deepening or fading as dark energy rises. The integrated Sachs-Welf effect responds to those changes, adding another layer of evidence. When today's most comprehensive analyses are read with a clear eye, the data point toward an energy component whose pressure is astonishingly close to that of a pure vacuum, with no compelling sign of time variation. Yet close to is not a surrender, it is an invitation. The allowed room for change tightens as measurements improve, and those tiny departures are precisely what a rolling field would produce. A cosmological constant cannot clump, cannot roll, cannot change its texture, its influence is purely geometrical. A field, however, may possess internal stiffness that prevents it from clustering on small scales, yet if its stiffness relaxes, or if it couples faintly to matter or neutrinos, it could leave a faint, scale-dependent imprint on the growth of halos, subtly altering the timeline by which galaxies of a given mass become common. Those differences are not abstract philosophy, they are measurable. They appear in how the growth rate of structure compares to what you would predict from the measured expansion history under standard gravity. Surveys often report a combined quantity that describes how quickly cosmic lumps grow per unit cosmic clock, a lever arm, that can tell you whether the acceleration resembles a stubborn vacuum or a more dynamic field. And then there is the coincidence question that probably stirs a quiet wonder in you. Why does dark energy begin to dominate precisely in our epoch? A constant offers no deeper reason beyond selection. Observers can only arise in periods when matter still clumps. But the constant has not yet erased all contrast. Fields can be engineered to track matter for long stretches before peeling off to dominate, making the timing feel less like a fluke. Yet such designs often import the same finer tuning they aim to avoid. A third possibility lurks in the shadows: modified gravity. Instead of adding a new substance, you alter the law itself. This rote must still reproduce the astonishing success of general relativity on solar system scales and in the propagation of gravitational waves, and it must make the geometry inferred from distances match the growth inferred from clustering. Many bold modifications have drifted back toward models that, to the sky, appear virtually indistinguishable from a vacuum or a very calm field. Keep your feet firmly on the data. Distance indicators map a smooth acceleration biorulers lock in a consistent scale ladder. The microwave background provides anchor points for the early universe that any late-time model must honor. Lensing and galaxy flows add growth constraints. Tensions do appear discrepancies in the current expansion rate derived from local measurements versus early universe inferences. Mild mismatches in the amplitude of matter clustering, known yet demand a dramatic evolution of dark energy. They could signal subtle systematics, gaps in our modeling, or if they persist, the first whispers of a field or a tweak to gravity. That ambiguity is productive, not paralyzing. It sharpens the focus of the next decade's observations, urging us to measure the expansion rate more precisely at redshifts where matter and dark energy wrestle, to map weak lensing with unprecedented accuracy, and to correlate galaxy surveys with the cosmic microwave background to pin down potential decay. Multi-messenger tests will verify whether gravitational waves redshift exactly like light in an accelerating universe. Now bring this back to a human scale. If the vacuum explanation survives, The cosmos is headed for a quiet, cold expansionar future where islands of bound structure linger while the spaces between them swell exponentially. It is a simple, melancholy destiny, rooted in the notion that emptiness itself carries weight. If a field earns the nod, the future widens. Acceleration might ease or intensify, varying across epochs, perhaps accompanied by subtle, long-range forces that gently rearrange the cosmic web. The present becomes a moment in a slow, evolving story rather than the opening of an endless, steady drift. Either way, you are not asked to believe in a ghost. You are invited to read a ledger written in distances, angles, and the statistical choreography of galaxies, and to accept whichever entry remains standing under rigorous cross-examination from independent probes. The closing thought is calm. The vacuum rote teaches humility about the limits of our quantum accounting, while the field rote teaches humility about how light and delicate new physics must be to have escaped detection while steering the largest scales of all. Between them, the universe offers a demanding kindness, enough acceleration to measure, enough structure to map, enough time to build instruments that can decide. Your role, as a listener, a thinker, perhaps even a future investigator, is to insist that every claim cash out in observables, to revel in the fact that a question with philosophical flavor is being answered with sky maps and error bars, and to remember that whichever door opens, it opens onto a deeper rule about how emptiness, or the gentlest of fields, governs the fate of everything. Consider two compelling scenarios that illustrate how subtle fields might shape the cosmos. Picture an axion, a featherlight field born from a symmetry introduced to solve a thorny problem in particle physics. This field can sit nearly still for eons, its value set early on, and then, as the cosmic background cools to just the right temperature, it begins a slow, coordinated oscillation across space. Those oscillations behave like an invisible fluid that does not clump too quickly, offering a viable candidate for dark matter. The signature of such an axion does not blaze in fireworks. It appears in the careful bookkeeping of the early universe. If the axion supplies most of the dark matter, then tiny variations in its initial value across the sky would introduce a special kind of perturbation that shuffles the relative amounts of matter and radiation without changing their total. This leaves a distinct statistical fingerprint in the ancient afterglow of the cosmos, the cosmic microwave background, a fingerprint you can learn to recognize. Now turn to a curvaton, a gentle field that cares less about driving the early burst of expansion and more about writing the pattern of cosmic ripples later on. While the inflaton, the flashy lead in the early universe's story, creates the initial push, the curvaton can subtly modulate the distribution of density fluctuations, influencing how structures eventually form. Together, these two fields offer a different script for how the universe's structure and dark matter could have been arranged. Learning their cues teaches you to separate what must have happened from what only seemed inevitable. So, as you sit with the night sky stretching above you, let the vastness inspire a quiet determination. Recognize that each photon, each galaxy, each subtle tilt in the cosmic microwave background is a piece of a conversation that has been ongoing for billions of years. Your task is not merely to listen, but to ask the right questions, to design experiments that widen the net until no ordinary doubt can hide, and to embrace the humility that comes with confronting the unknown. Let the rigor of the technicians, the imagination of the theorists, and the meticulous care of the statisticians guide you. Let the mystery of dark energy and the allure of elusive fields fuel your curiosity, not as a distraction, but as a beacon pointing toward deeper understanding. You have the capacity to turn wonder into inquiry, to turn a fleeting feeling of awe into a concrete plan of action. Whether you become a scientist, an educator, a storyteller, or simply a citizen of the cosmos who champions truth, remember that the universe has already offered you the tools, light that has traveled across eons, maps of galaxies that trace its growth, and the mathematical language that lets us decode its secrets. It is now up to you to pick up those tools, to weave them into a narrative that respects the data, that welcomes doubt as a catalyst for deeper experiments, and that celebrates the relentless human drive to know what lies beyond the horizon. Take this moment, breathe in the night, feel the weight of the stars, and commit yourself to the pursuit of clarity. Let every question you ask be rooted in observable reality. Let every hypothesis you entertain be willing to face the harshest possible tests. And let every discovery, no matter how small, remind you that the cosmos is not a distant stage, but an active partner. In the grand tapestry of existence, your thread may be delicate, but it is essential. Keep asking, keep testing, keep listening, and let the sky become not just a backdrop, but a guide that leads you toward ever greater horizons. The universe is waiting, and you are ready. Imagine you are standing at the edge of the universe, not as a distant observer, but as an active participant in a grand conversation between light and the void. The sky itself is a ledger, a living record written in distances, angles, and the intricate dance of countless galaxies. When scientists cross-correlate the maps of those galaxies with the faint afterglow of the Big Bang, they are not simply crunching numbers, they are testing whether the ripples of gravity stretch and fade exactly like the glow of a candle in a room that is itself expanding. They are asking, in the most profound way, whether the universe's acceleration is a quiet, inevitable drift or a story still being written. If the simplest explanation holds that empty space, the vacuum, carries a tiny amount of energy, then the cosmos is headed for a serene, cold expansion. Islands of stars and galaxies will remain, but the sea between them will swell ever faster, pulling everything apart in a melancholy yet elegant procession. In that vision, nothingness has weight, and the future is a gentle stretching of the fabric that already exists. But there is another possibility, a scenario where a subtle field, something more lively than a static vacuum, takes the lead. In that case, the acceleration could ease, or it could intensify. It might change over epochs, and faint, long-range forces could slowly rearrange the cosmic web. The present moment would become a chapter in a slow, evolving story rather than the opening line of an endless, unchanging drift. Whichever path the universe chooses, you are not being asked to believe in a ghost, you are being asked to read the ledger that the cosmos has inscribed for us, to weigh every entry against independent tests, and to accept the one that stands strongest when the data shine a light upon it. Both possibilities teach humility. The vacuum route reminds us that our quantum bookkeeping is still incomplete, that the universe may hide its secrets in the most subtle of energies. The field route tells us that even the lightest, most delicate new physics can steer the largest structures, slipping through our detectors while shaping the grandest scales of existence. Between them, the universe offers a demanding kindness, just enough acceleration to be measured, enough structure to be mapped, enough time to build the instruments that will decide. Your role as a seeker of truth is to insist that every claim be anchored in observable reality, to celebrate that a question that once seemed purely philosophical is now being answered with sky maps and error bars. And you must remember that whichever door opens, it will reveal a deeper rule about how emptiness, the gentlest of fields, governs the fate of everything. Consider two elegant possibilities that have emerged from the tapestry of modern theory, the Axion and the Curvaton. Picture them as two understudies waiting in the wings, while the more flamboyant inflaton takes center stage. The Axion is a featherlight field born from a symmetry that was introduced to solve a thorny problem in particle physics. The Curvaton, on the other hand, is a gentle field that cares less about driving the rapid early expansion and more about writing the pattern of cosmic ripples after the inflaton has done its work. Together, they offer a fresh script for how the universe's structure and its mysterious dark matter could have been arranged. Learning their cues helps you separate what truly must have happened from what merely seemed inevitable. Let's begin with the Axion. It first appeared as a clever fix for a puzzling silence in the strong forces symmetry violating effect that should have been there but wasn't. The beautiful twist is that this fix automatically gives rise to an extremely light field whose value can be set early on and then remains almost frozen for ages. When the universe cools to just the right temperature, this field begins a slow, coordinated oscillation across space. Those oscillations behave like an invisible fluid that doesn't clump too quickly, and they can make up some even aloft the dark matter that binds galaxies together. The Axion story is not one of fireworks, but of careful bookkeeping. If Axions supplied most of the dark matter, tiny differences in their initial value across the sky would impart a special kind of variation, shuffling the relative amounts of matter and radiation rather than their total. That shuffling would leave a distinct statistical fingerprint in the ancient afterglow of the cosmos. Observations have placed very tight limits on such fingerprints, which in turn constrain how wildly the axion could have jittered in its early life, and how violently the universe could have expanded when those jitters were set. What makes the axion especially inviting to experimentalists is its faint but real willingness to whisper to ordinary matter. Though it couples only feebly to light and to electromagnetic fields inside metals, clever resonance circuits can try to convert that whisper into a measurable tone. Powerful lasers can be shown through walls to see whether a trickle of light reemerges on the far side. Stars themselves can betray the presence of axions by cooling a little faster than expected, as if the particles are stealing away energy. Even spinning black holes might act as cosmic amplifiers, losing angular momentum if axion-like fields exist in the right mass range, leaving behind gaps in the distribution of observed black hole spins. On cosmic scales, different axion masses tell different stories. Extremely light versions would smooth out structure on the smallest galactic scales, potentially softening the dense cores of dwarf galaxies. Heavier, more classic axions would behave like ordinary cold dark matter, but they might also clump into dense miniclusters that future surveys could detect through subtle gravitational lensing or brief radio flickers. In each case, the universe offers a set of testable predictions, and the more we listen, the clearer the picture becomes. Now turn to the curvaton. Unlike the axion, which adds a new ingredient to the cosmic recipe, the curvaton changes who writes the initial pattern. In the standard story, the same field that drove the rapid early expansion also planted the tiny perturbations that later grew into galaxies. The curvaton offers a cleaner division of labor. The inflaton focuses on expansion, while a separate light field lingers in the background, picking up minute quantum jitters. Long after the furious expansion has ended, this field begins to oscillate and can briefly act like a matter-like component. When it finally decays into radiation or familiar particles, it converts those gentle jitters into the very variations in density that shape the sky and the cosmic web. That detour has sharp consequences. First, it allows the early expansion to occur at a lower energy without starving the later structure of the variations it needs. That means the primordial gravitational wave hum from the earliest times could be far fainter than simple forecasts suggest, making a non-detection of certain polarization patterns in the sky less surprising. Second, because the curvaton's imprint is painted later, it naturally leans toward a specific style of subtle non-randomness in the statistics of the ancient afterglower style that links very long wavelengths to patterns on much smaller scales. Current measurements push this effect to be small, which narrows curvaton models to those in which the field almost, but not quite, dominates the energy budget before it decays. Third, the curvaton can leave behind faint composition shuffles if it decays differently into neutrinos, ordinary matter, or dark matter, creating testable correlations that tie the cosmic recipe to the timing of the decay. These are not hand-wavy stories, they are concrete targets for analyses of fine-grained sky maps. The two actors can even share the stage. Under certain conditions, an axion could play the role of the curvaton, writing the initial pattern and lingering as dark matter. But that mashup is tightly policed by data, because it would simultaneously affect the afterglow statistics and the present-day distribution of galaxies. What makes these scenarios valuable is not that they guarantee drama, but that they sharpen the questions we ask of observations. If you measure how distances grow with time and see a calm, simple acceleration, that alone doesn't pick between axion or curvaton. But if at the same time you find an almost perfectly random pattern of ancient temperature and polarization fluctuations with only the tiniest allowed departure from pure randomness, you start to prefer axion dark matter models that kept their early jitters quiet and curvaton arrangements that decayed after shouldering most of the energy load. If someday a faint background of long wavelength ripples in space-time is discovered, pointing to a very high energy scale for the earliest expansion, the need for a curvaton diminishes as the inflaton itself would have done the heavy lifting. If, on the contrary, those ripples remain stubbornly absent down to the lowest levels we can probe. Curvaton-like authorship stays comfortably in play. Meanwhile, laboratory searchers press the axion from the other side. A narrow, confirmed radio-like signal moving in sync with Earth's motion through the Milky Way would be a smoking gun for axion dark matter, and every non-detection squeezes the viable ranges of mass and coupling, guiding theory towards specific corners rather than castles in the sky. The reflective lesson here is practical rather than dreamy. Axion and Curvaton scenarios are not invitations to multiply entities for their own sake. They are consistent ways to divide and simplify the choreography of the early universe. Let one field expand, let another write the initial map, let a third furnish the dark stuff. Or, let one field do two jobs if the data allow. Each assignment leaves different, checkable traces in the statistics of the oldest light, in the way galaxies grow, in the hum of space-time, and in the faintest signals coaxed from tuned instruments. You are not being asked to believe in esoteric spirits. You are being asked to follow evidence paths that remain open because the cosmos was kind enough to keep records across scales from the structure of dwarf galaxies to the pattern of microwave polarization, from black hole spins to resonant circuits cooled to near absolute zero. And the closing thought is quietly empowering. Whether dark matter is a field that began life as a symmetries remedy, whether the primordial blueprint was drafted by a separate gentle hand, or whether both stories converge in a single disciplined actor, the decision will be made not by taste, but by the sky and the lab together, nudging us toward a universe in which early simplicity did more work than we expected, and where the subtlest fields, barely moving, barely feeling, still manage to write the largest things we will ever see. Now, let's stretch our imagination even further. What if the universe did not explode from a single point, but exhaled after a long, deliberate inhale, shrinking into order before turning around and expanding again? That is the promise of bounce cosmologies, and one of their sharpest versions is called Ekpyrosis. Learning how these models work teaches you to separate which early universe tasks truly need an explosive beginning from which can be achieved by patience, discipline, and a different kind of physics. Begin gently with the bounce picture. In this view, the hot Big Bang is not the first frame, but the first clear frame after a reversal. Before that reversal, the universe was contracting. Contraction sounds dangerous because gravity normally amplifies lumps and directional stretching, threatening to twist space into chaos. But Ekpyrosis flips the script by having the dominant energy behave with extraordinarily high pressure. As the universe contracts, wrinkles and anisotropies are ironed out instead of being amplified like pressing a wrinkled shirt under a very hot, very heavy iron until it lies flat. This slow, stiff contraction can make space astonishingly smooth and nearly flat without needing a perfect beginning. It can also dilute relics that would otherwise cause headaches, turning the usual initial condition worries on their head. Rather than asking for a pristine start, Ekpyrosis shows how an ordinary, mildly messy state can be driven toward order by dynamics. Now deepen the question that truly matters to you. Can a contracting phase also plant the tiny variations that later grow into galaxies? And can it do so with the right statistical fingerprints? The answer is yes, but not automatically. A single contracting field tends to produce the wrong pattern. Successful Ekpyrosis models therefore draft a second light field to carry entropy fluctuations variations in the ratio of two components rather than in the totaland, then convert those softly patented variations into the curvature ripples that shape structure after the bounce. Done carefully, this entropic mechanism yields a nearly scale-free distribution of seeds, close to what we read in the oldest light, while naturally muting one of the main smoking guns of explosive beginnings, the background of long-wavelength gravitational waves. In practice, this creates a clean, testable contrast. If the sky's coveted swirl pattern from primordial gravitational waves stubbornly refuses to appear down to very low levels, bounce plus Ekpyrosis stories remain comfortable. If, on the other hand, a faint background of such waves is eventually uncovered, the need for a contracting phase explanation weakens, and inflationary narratives regain their footing. All of this may sound like an intricate puzzle, but remember that you are part of the solution. Each observation you champion, each experiment you support, each question you ask, adds a new line to the cosmic ledger. The universe has given us tool light that has traveled across eons, maps of galaxies that trace its growth, the delicate whisper of the microwave background to read its story. It asks us not to accept any tale on faith, but to test every claim against the evidence it has left behind. In doing so, we practice humility, curiosity, and a quiet confidence that the answers are out there, waiting for the right combination of imagination and rigor. So keep listening to the sky, keep building the instruments that can hear the faintest hum of spacetime, keep refining the theories that turn mathematics into meaning. Let the mystery of dark matter, the subtle hand that may have written the cosmic blueprint, and the possibility of a universe that bounces rather than bangs, all fuel your drive to understand. In every galaxy cluster, in every black hole spin, in every lab room resonance, the universe is speaking. And you, with an open mind and a listening heart, are exactly the kind of seeker it needs. Let this be your invitation to stand at the crossroads of the very large and the very small, to hold the data of the stars in one hand and the curiosity of a child in the other, and to move forward with the certainty that each step you take brings us closer to deciphering how emptiness are the gentlest of field shapes everything we see. The journey is ongoing, the questions are deep, and the answers are within reach. Embrace the challenge, celebrate the progress, and know that your voice, your inquiry, and your determination are essential parts of the universe's unfolding story. Imagine standing beneath a night sky that feels like a living canvas, each star a whisper from a deeper story. In that moment, you sense that the universe holds mysteries that are not just out there, but also within the very fabric of what we call reality. Dark matter, that invisible scaffold holding galaxies together, may be more than a single creature lurking in the dark. It could be a field that first appeared as a clever patch to a broken symmetry, a gentle hand that drafted the primordial blueprint, or perhaps the convergence of both ideas into a disciplined actor that shapes the cosmos. The answer will not emerge from personal taste, it will be spoken by the sky and the laboratory together. Their combined voice nudges us toward a universe where early simplicity did far more work than we ever imagined, where the subtlest fields barely moving, barely feeling still managed to write the grandest chapters of existence. Now picture a universe that does not explode from a single point like a firework, but instead inhales slowly, contracts with deliberate order, and then exhales in a graceful expansion. This is the promise of bounce cosmologies, with the sharpest version known as Ekpyrosis. When you explore how these ideas work, you start to separate what truly needs an explosive beginning from what can be achieved through patience, discipline, and a different kind of physics. In a bounce picture, the hot Big Bang is not the first frame of the movie, it is the first clear frame after a reversal. Before that reversal, the cosmos was gently contracting. Contraction can sound dangerous because gravity tends to amplify lumps and stretch space into chaotic shapes. Yet Ekpyrosis flips the script. It endows the dominant energy with extraordinarily high pressure, so that as the universe contracts, wrinkles and anisotropies are ironed out rather than amplified. Think of pressing a crumpled shirt under a very hot, very heavy iron until it lies flat. This slow, stiff contraction can make space astonishingly smooth and nearly flat without needing a perfect start. It can also dilute relics that would otherwise cause headaches, turning the usual worry about initial conditions on its head. Instead of demanding a pristine beginning, Ekpyrosis shows how an ordinary, mildly messy state can be driven toward order by the dynamics of the cosmos itself. You may wonder whether a contracting phase can also sow the tiny variations that later grow into galaxies, and whether it can do so with the right statistical fingerprints. The answer is yes, but not automatically. A single contracting field tends to produce the wrong pattern. Successful epirotic models therefore invite a second, light field to carry entropy fluctuations variations in the ratio of the two components rather than in the total, and then gently convert those fluctuations into curvature ripples that shape structure after the bounce. When this entropic mechanism is handled carefully, it yields a nearly scale-free distribution of seeds that matches what we read in the oldest light, while naturally muting one of the main smoking guns of explosive beginnings, a background of long-wavelength gravitational waves. In practice, this creates a clean, testable contrast. If the sky's coveted swirl pattern from primordial gravitational waves stubbornly refuses to appear even at very low levels, bounce plus ekpyrotic stories stay comfortable. If, however, that swirl shows up at an amplitude tied to explosive dynamics, those models are pushed to the margins. The outcome rests on the data, not on preference. Getting through the bounce itself is the technical and conceptual heart of the program. Classical gravity forbids a smooth reversal if ordinary matter obeys familiar energy conditions. Therefore, any successful bounce must bring in new ingredients that remain healthy under extreme stress. Some approaches use effective corrections that arise in candidate quantum gravity frameworks, making gravity repulsive at ultra-high densities. Others exploit exotic but controlled interactions that allow a brief, safe violation of the usual energy condition without unleashing catastrophic instabilities. Yet another route realizes the bounce through extra dimensions, where our visible universe is a membrane that collides and rebounds inside a larger geometry. Each path carries a checklist, no hidden negative energy ghosts that would destabilize everything, no runaway growth of tiny disturbances, and a transparent set of rules for carrying the pre-bounce patterns across the reversal into the expanding error without scrambling them. It is not enough to sketch a cartoon of a reversal. You must show that the correlations written during contraction translate into the right mix of temperature, ripples, and polarization patterns afterward. And you must quantify any side effect subtle deviations from perfect randomness or faint preferences in the shapes of higher-order correlations. Observationally, this opens a crisp menu of possibilities. Ekpyrotic scenarios tend to predict an extremely small primordial gravitational wave signal on the largest scales, a modest but distinctive form of non-Gaussianity tied to the entropic to curvature conversion, and a near absence of the long-range tensor distortions that would make the sky's polarization curl at wide angles. Some versions can also imprint low-level featureless gentle kinks or oscillations in the spectrum of initial ripples if the conversion was sudden, or if the contracting potential had ridges and plateaus. On smaller astrophysical scales, bounce models are generally conservative. They recover the same successful broad-brush picture of structure growth that we test with galaxy surveys and gravitational balancing maps. Because once the reversal is past and ordinary radiation and matter dominate, familiar physics resumes. Yet the pre-bounce phase leaves fingerprints that careful statistics can chase, fingerprints sharper than slogans. The precise level and shape of non-randomness, any residual isocurvature traces if the two fields decayed into different cosmic species, and the absolute faintness of primordial gravitational waves together create a triangulation test that can reward or rule out families of bounces. There is also a wider, almost poetic story that bounce cosmologies make possible cyclicity. If the mechanism that smooths and seeds during contraction and the mechanism that reverses to expansion are both robust, you can envision a universe that breathes long, cold expansions that thin out entropy, followed by slow ordering contractions, followed by bounces without ever having to pass through a singular point where physics simply ends. In such pictures, the arrow of time is carried by the accumulation and then dilution of records within each cycle, and the why-now puzzles of cosmic acceleration can be tamed by dynamics that repeat rather than by a unearth stroke of luck. Yet the attraction of cycles should not lower standards. Any cyclic model must explain how entropy is managed between rounds, how new structure isn't piled on top of old until disorder wins, and how the delicate seed pattern avoids a buildup of scars. Proposals that leverage a late phase of accelerated expansion to dilute debris before contraction starts are one promising path through that maze, but they must face the same data as ordinary bounces. Reheating the handoff from the bounce to a hot, particle-filled universe adds another check. It must populate familiar matter without flooding the cosmos with unwanted relics or violating bounds on light species and leftover radiation. In some constructions, the same fields that wrote the seeds also set the table for atoms and nuclei, tying the elegance of the origin story to the consistency of the cosmic recipe we infer from element abundances and background light. From a human perspective, the most valuable gift of bounce and ekpyrotic thinking may be methodological. They remind you that smoothing, seeding, and setting the arrow of time are tasks, not dogmas. They can be achieved by driving everything apart very fast, or by compressing everything with controlled pressure. They can be accomplished by a single field wearing many hats, or by 2 or 3 fields handing off responsibility at well-defined stages. And they can be tested not by taste, but by the same observable as distance shift relations, sky maps of temperature and polarization, the growth rate of clustering, and the relentless hunt for primordial curls in the microwave background. Let the tone settle as you weigh them. If future measurements lock in a non-zero swirl pattern at the level natural for explosive beginnings, the bounce camp will have to reinvent itself or yield. If those curls stay invisible while the statistics of the oldest light nudge toward the subtle signatures of entropic conversion, and the sky remains free of telltale tensor fossils, the case for a contracting prelude will strengthen. Either way, you learn something essential. Nature is giving you multiple concrete routes to the same visible universe, and your job is to follow the evidence ruthlessly, accepting that the cosmos may have chosen grace over fireworks, order built by pressure, a turn rather than an origin. If that choice is confirmed, it will change not only how we tell the first chapter, but also how we imagine the chapters to come. Now turn your imagination to quantum tunneling between vacua, a phenomenon that feels like walking through a night valley and sensing a faint tremor beneath the grass, a reminder that what feels like the lowest ground might actually be a shelf above a deeper basin. In modern physics, the vacuum is not empty, it is a configuration where a field prefers to sit. Many theories allow more than one such resting place, like terraces on a hillside, each terrace shaping the world we experience, determining particle masses, force strengths, and even the background push or pull on spacetime itself. Quantum rules add a twist no classical hill would allow. Even if a field is marooned in a shallow terrace separated from a deeper one by a ridge, there is a tiny probability that a patch of space will borrow just the right pattern of fluctuation to appear on the far side, planting a seed of the deeper vacuum. That seed becomes a bubble whose interior already lives by new rules, with a thin wall separating it from the old surroundings. Once formed, the bubble tends to grow, because the energy gained by converting interior volume to the lower vacuum outweighs the cost of its wall. You don't need to memorize the mathematics to feel the logic. The rarer the fluctuation needed to make a bubble large enough to survive, the more suppressed the transition. The thicker and higher the ridge between vacua, the more unlikely the jump. When gravity is included, a positive energy background can either aid or hinder the process depending on the balance between vacuum energies and the curvature they induce. In today's calm, cold universe, such tunneling, if possible at all for our fields, would be stupendously unlikely on timescales that make even the age of the cosmos feel small. By contrast, in the early hot universe, thermal agitation provided another route over the ridge, letting fields hot by heat. Assisted activation before quantum rarity was the only option. When a bubble does nucleate, the dynamics inside and outside become surprisingly concrete. Inside, the field that defines the new vacuum relaxes toward its preferred value. And if the energy difference is large, it can heat or reheat that region, setting initial conditions that may differ from the parent domain. The spatial geometry inside a bubble born from a high-energy state typically resembles an open universe with negative curvature, imprinted by the way the bubble wall races outward near light speed. Outside, if the old vacuum drives accelerated expansion, bubbles remain separated by the swelling of space, so even occasional nucleation hardly percolates. If instead nucleations are common, bubbles can collide and merge, a process that could leave telltale concentric imprints in the oldest light or seed a faint background of gravitational waves, with a characteristic frequency set by the nucleation rate and wall tension. All of these ideas invite you to sit with wonder, to let the cosmic narrative unfold not as a rigid script, but as a living dialogue between daring imagination and disciplined evidence. The universe may have chosen a gentle inhale, a graceful bounce, a quiet tunneling, or perhaps a combination of all three. Each possibility offers a pathway to the same awe-inspiring reality we observe today. Your role as a listener and as a thinker is to stay curious, to let the questions rise, and to let the data be the compass that guides you through the vast, beautiful possibilities. Embrace the mystery, cherish the method, and move forward with the confidence that every step you take, whether through contraction, expansion, or quantum leap brings you closer to the heart of the cosmos. Imagine you are stepping into a night-shaded valley, the cool grass whispering beneath your feet, and you feel a faint tremor echoing from the deeper earth below. That slight shiver is a reminder that what seems like the lowest point may actually be a shelf perched above an even deeper basin. Let that image settle in your mind, because it is the perfect metaphor for a remarkable quantum phenomenon called tunneling, a process that lets a field, even when it appears settled, spring across an invisible ridge into a lower energy state, rewriting the script of the cosmos in an instant. Begin gently. In modern physics, the word vacuum does not mean emptiness. It describes a configuration where a field feels most at home, a kind of resting place. Many theoretical landscapes contain more than one of these resting places, like terraces on a hillside. Which terrace your fields occupy determines the masses of particles, the strengths of forces, and even the overall push or pull that shapes spacetime itself. Quantum mechanics adds a twist that no classical hill could ever allow, even if a field is stuck on a shallow terrace, separated from a deeper one by a high ridge. There exists a tiny probability that a patch of space will gather just the right fluctuation, appear on the far side of the ridge, and plant the seed of a new vacuum. That seed inflates into a bubble whose interior already lives by the new rules, while a thin wall separates it from the old surroundings. Once the bubble forms, it tends to grow because the energy gained by converting its interior volume to the lower energy vacuum outweighs the cost of maintaining the wall. You do not need to carry around equations to feel this logic. The rarer the fluctuation needed to make a bubble large enough to survive, the more suppressed the transition. The thicker and higher the ridge separating the vacua, the less likely the jump. When gravity joins the picture, a positive energy background can either help or hinder the process, depending on the balance between the vacuum energies and the curvature they induce. In today's cold, calm universe, such tunneling, if it is possible at all for the fields, we know would be staggeringly unlikely on any timescale that makes even the age of the cosmos feel short. In contrast, during the hot, tumultuous moments of the early universe, thermal agitation offered another route over the ridge, letting fields hop across by heat. Back then, assisted activation was the only viable option, because pure quantum rarity was simply too improbable. Once you accept this mechanism, the dynamics inside and outside a bubble become surprisingly concrete. Inside, the field defining the new vacuum relaxes toward its preferred value, and if the energy difference is large, it can heat or reheat that region, setting initial conditions that differ from those of the parent domain. The spatial geometry inside a bubble that emerges from a high-energy state typically resembles an open universe, its negative curvature imprinted by a wall racing outward near the speed of light. Outside, if the old vacuum drives accelerated expansion, the swelling of space keeps bubbles apart, so even an occasional nucleation hardly percolates. Only when nucleations become common can bubbles collide and merge, leaving telltale concentric imprints in the oldest light, or seeding a faint background of gravitational waves with a characteristic frequency set by the nucleation rate and wall tension. Observationally, we have not yet seen unambiguous scars of such collisions, nor the specific gravitational wave backgrounds they would create. That does not disprove tunneling, it merely tells us that if whole chains of transitions occurred, they either happened at energies or times beyond our current reach, or they unfolded in corners of theory space that avoid loud signatures. A sobering perspective comes from stability calculations that extrapolate known particle physics. They suggest our familiar vacuum might be metastable, perched higher than an even lower state hidden somewhere in the field landscape. Yet the barrier appears so high and broad that the expected lifetime dwarfs any sensible cosmic timescale. In plain language, even if a deeper basin exists, the ridge is so forbidding that the universe will likely drift into cold obscurity long before a bubble of the true vacuum ever appears here. Gravity threads the story with discipline rather than drama. The presence of a horizon and a gentle background temperature in an accelerating universe provides a second pathway, akin to the field briefly perching atop the ridge due to a large fluctuation of the whole patch while also tweaking the balance between volume and wall energy. Consequently, some transitions that would be allowed in flat space become even harder in highly curved regions or near the tiniest scales. Candidate quantum gravity effects could reshape the ridge, but honest statements remain cautious. A few mechanisms can modestly alter tunneling rates. Yet the exponential sensitivity of the problem means that tiny theoretical uncertainties often translate into enormous differences in lifetimes. This is why physicists focus on robust bounds and on signatures that do not rely on the most fragile assumptions. There are practical, testable branches of this topic that keep it tethered to data. In models where early cosmic acceleration ended not by a smooth roll, but by tunneling, the first hot regions inherit an open geometry prediction that can be confronted with precise measurements of spatial curvature. In scenarios where a low-energy transition is still trickling onward, nucleating bubbles would be rare today, but not impossible, and collisions between their walls would source a spectrum of gravitational waves with a shape and amplitude that upcoming detectors can chase. The very act of searching, and either finding or constraining these signals, can retire whole classes of models. Astrophysical environments may also tweak the odds. Extreme gravitational fields around black holes in some proposals could catalyze transitions by concentrating energy and modifying the local barrier. Serious analyses, however, tend to find that any enhancement is either tiny or limited to parameter choices already squeezed by other observations. Thus, the idea remains intriguing but unproven a tantalizing corner of theory, rather than a shortcut to doom. The most important conceptual lesson lies in how tunneling reshapes our sense of naturalness. If a theory contains many vacua with different values for what we normally consider fundamental constants, then history becomes a sequence of lawful but rare jumps. The regions where complex structures arise are those where the menu of constants and forces happens to be compatible with long-lived stars and chemistry. This line of thought does not replace dynamics with wishful selection, but it does shift the question from why these exact constants to, in a landscape of many lawful possibilities and allowed transitions, what fraction of regions resemble ours, and do defensible counting rules favor what we see. Even if you keep a healthy skepticism about vast landscapes, the immediate, falsifiable claims, stay crisp tunneling implies bubbles with walls that move close to light speed, gravitational radiation emerges. If collisions happen, potential hints of curvature appear if a transition seeded our hot phase, and an extreme suppression of decay rates persists in our local vacuum, as long as its ridge remains high. Each of those predictions is or will soon be checked by maps of the cosmic microwave background, galaxy surveys, and gravitational wave observatory stools that bring the grand ideas of quantum tunneling down to a human scale without resorting to melodrama. Talk of vacuum decay sometimes inflates into apocalyptic headlines, but the mature reading is quieter and more empowering. Quantum tunneling between vacua is a lawful channel that helps us understand how a field can leave a plateau for a deeper valley, how patches of the universe can inherit different effective laws, and how careful statistics and geometry together decide whether a given transition is a footnote in thermal history or an event that writes itself across the sky. Your part in this story is to keep the poetry in its place and the physics in the lead. Ask yourself what specific patterns would remain after a jump, and let those patterns of their stubborn absence teach you which hills and valleys are real in the unseen terrain beneath our feet. Now turn to a different, equally captivating frontier: black holes. You have been taught to think of them as doors that only swallow, but a bolder question tugs at the edge of that picture. What if, beyond the event horizon, gravity does not simply end the story, but edits it so severely that a new cosmic chapter buds off a baby universe that grows on its own page? Begin gently by recalling what is solid. A black hole is a region where escape is impossible because gravity bends paths inward, creating an outer horizon you could, in principle, hover near, and an interior where known physics predicts a singular core of infinite density in arena, where our equations lose reliability. Stephen Hawking's groundbreaking calculation adds that horizons glow faintly, slowly evaporating by emitting radiation whose temperature is set by the black hole's size. The speculative ideas you are about to explore ask whether the would-be singularity is replaced by quantum gravity with a bounce or a bridge, that continues as a new region of spacetime, so that a collapsing star seeds another universe rather than terminating in a physical end. One class of ideas pictures the singularity smoothed by quantum effects into a pressure-like core, sometimes nicknamed a Planck star, where collapse halts and rebounds. From the outside, you still see a black hole for a very long time, but inside time flows differently, and the rebound can inflate a new cosmic expanse. Another thread imagines that the mathematics of Bridges wormholes might be more than abstract diagrams, with quantum entanglement acting like a stitch that connects regions. The slogan version is that linked quantum states and geometric tunnels are two faces of one relation. So the interior of a black hole could be connected to someplace else in a way that keeps information safe, even as the horizon evaporates. A third storyline asks about cosmic reproduction. If every black hole births a universe with slightly tweaked constants, then a population of universes could, over many generations, drift toward parameters that maximize black hole production, a kind of natural selection played out on the canvas of physical laws rather than on genes. This notion does not claim purpose, it simply observes that what can reproduce will tend to survive in the space of possibilities. To keep your balance, separate what is testable from what is beautiful. We know horizons exist, we have imaged their rims. We know Hawking-like behavior must occur in some form because it weaves together thermodynamics, quantum theory, and gravity. What we do not yet know is whether singularities are real places or placeholders for better physics. A bounce leaves room for hope because it offers a way out of paradoxes. If the interior evolves into a separate region, the information about what fell in might not be destroyed, but simply become inaccessible to the parent universe, sidestepping the contradiction between unitary quantum rules and the naive picture of information loss. Yet baby universes raise bookkeeping questions. Do they rob the parent universe of energy in a way we could detect? Do they imply observable remnants after evaporation? Or does quantum constraint close the accounting so tightly that all an external observer ever measures is a delicate release of correlations in the outgoing radiation? The observational frontier is subtle, but not empty. If quantum gravity lets black holes decay through a sudden white hole phase, tiny relic explosions could pepper the universe with fast, faint flashes at characteristic energies. If evaporation halts at a small but finite mass, because the core is a quantum object with a minimum size, the cosmos today might be salted with stable remnants. If wormhole-like structures can form from astrophysical collapse, gravitational wave bursts from mergers might carry distinct ecoslat time, low-amplitude ripples repeating after the main ringdown, departing from the clean signature of a simple horizon. None of these hints has been confirmed, but each guides analysts to design searches and set limits that prune airy ideas into disciplined proposals. A different grounded window comes from black hole demographics. The distribution of masses, spins, and merger rates observed by gravitational wave detectors already constrains how often exotic processes can occur. If a large population of Planck star remnants existed, they would influence the mass spectrum we see. If wormhole echoes were common, the precise shape of the post-merger signal would betray them. Even the background glow of Hawking-like radiation, though far beyond current reach, could one day be teased out of cosmological data, offering another indirect probe. All of this invites you to hold wonder and rigor together. The universe offers clues in the faintest whispers of light, the subtlest tremors of space-time, and the deepest theoretical reflections on how matter and geometry intertwine. By listening carefully, you can become a participant in the grand adventure of discovery, turning abstract equations into stories that speak to the human heart. The valleys you traverse, the hills you climb, and the mysterious doors you imagine you weather, they are quantum tunnels or black hole bridges, all part of a shared journey toward understanding. Let the tremor beneath the grass remind you that beneath every apparent low point lies the possibility of a deeper basin, a richer landscape, and a new horizon waiting to be explored. Embrace the mystery, follow the logic, and let the physics guide you toward a future where today's questions become tomorrow's insights. Imagine standing at the edge of a night sky that refuses to be fully known, feeling the pull of mysteries that are both enormous and intimate. The universe is whispering a story about bridges made of quantum threads, about tunnels that might connect distant regions, about the possibility that every black hole could be a seed for a new cosmos. It is tempting to let wonder turn into fantasy, but there is a deeper invitation here, a call to shape curiosity into disciplined exploration, to let the thrill of the unknown light the path toward concrete insight. Think of the mathematics that describes wormholes as more than a clever diagram. In that language, entangled particles are like stitches that bind together separate patches of fabric. One might picture a black hole's interior not as a deadened abyss, but as a hallway that leads somewhere else, a place where information is kept safe even as the horizon slowly evaporates. This is not a fanciful metaphor, it is an invitation to ask tangible questions. If such a tunnel existed, how would it affect the signal we hear when two massive objects merge? Could the echo of a gravitational wave carry a subtle signature, a gentle ripple that tells us a bridge slipped into view for a moment? The very act of listening to the cosmos with ever more refined ears becomes a practice in patience and precision. Now turn that imagination toward a different kind of story, the idea that each black hole gives birth to a new universe, each with slightly tweaked physical constants. Over countless generations, this would look like a natural selection played out on the grandest stage, where the genes are the values of particle masses, force strengths, and vacuum energies. No purpose is implied, only the simple observation that whatever can reproduce tends to persist in the space of possibilities. This analogy teaches a powerful lesson for our own lives. When we plant ideas, when we nurture projects, when we allow our passions to evolve, we are participating in a kind of selection. The ideas that survive are those that can adapt, that can be repeated, that can resonate with the world around them. The cosmos offers a mirror for that process, a reminder that creativity must be testable to grow. That beauty alone is not enough. Keep your footing by separating the testable from the beautiful. We have stared directly at the edges of black holes. We have imaged the glow of their rims with telescopes that can resolve shadows. We know that horizons behave thermally, that they possess a temperature and an entropy that tie together quantum theory, gravity, and thermodynamics. What remains uncertain is whether singularity is those points where equations break down our real places or placeholders for a deeper theory. A bounce scenario, in which the interior of a black hole re-expands into a new region, offers hope because it provides a route out of paradoxes. If information does not vanish but merely slips into a region we cannot directly access, the tension between quantum unitarity and the naive picture of information loss loosens. Yet these baby universes raise practical bookkeeping questions. Does the parent universe lose energy in a way we could ever detect? Do remnants linger after evaporation, offering clues in the background glow of the cosmos? Or does the quantum bookkeeping close so tightly that all an external observer ever perceives is a delicate cascade of correlations embedded in the outgoing radiation? The observational frontier may be subtle, but it is far from empty. If quantum gravity permits a sudden transition from a black hole to a white hole phase, the universe could be peppered with fleeting, faint flashes at characteristic energies. If evaporation stalls at a finite mass because the core has a minimum quantum size, stable remnants might still be scattered throughout space. If wormhole-like structures arise from astrophysical collapse, the gravitational wave signal from a merger could bear distinct echo-slow amplitude ripples that repeat after the main ring down and stand apart from the clean signature of a simple horizon. None of these hints have yet been confirmed, but each one serves as a compass pointing toward a testable hypothesis. Analysts design searches, set limits, and prune airy ideas into disciplined proposals. A complementary window comes from the demographics of black holes themselves. If universes that produce more massive stars and denser clusters give rise to more black holes, and if that pressure subtly shapes fundamental constants, then we can ask, would slight adjustments to particle masses or force strengths truly increase black hole formation without destroying chemistry or the life cycles of stars? Those are crude but honest selection tests, quantitative knobs we can turn in simulations and compare against the observed abundance of black holes and heavy elements. The information paradox, the question of whether Hawking radiation truly erases details, keeps these speculations honest. Recent precision arguments suggest that, from the parent universe's viewpoint, the radiation must carry intricate, multi-part correlations that restore information by the end. If so, the universe escape routes cannot simply be an excuse to discard information. They must be woven into a global story that remains unitary for the external observer. Even the entropy of a horizon, proportional to its area, whispers a constraint. Any interior description cannot harbor arbitrarily many independent degrees of freedom without violating the finite bookkeeping of the exterior. A successful black hole cosmology must respect that cap, either by organizing interior data efficiently or by ensuring that effective interior freedom is encoded holographically mirrored in the correlations accessible at the boundary rather than stored as bulk bits that would overflow the ledger. This holographic principle, though abstract, is a reminder that the universe favors elegant accounting. It encourages us to look for solutions that are not merely clever, but also economical, where every piece of information finds its rightful place. Consider primordially formed black holes, not as baby universes but as useful foils. If the early universe spawned a population of tiny holes, their evaporation today could mimic the exotic flashes a bounce model predicts. Distinguishing the two requires meticulous fingerprinting, examining spectral shapes, repetition patterns, and host environments that surveys are learning to read. The human-scale lesson in all of this is methodological rather than mystical. Black hole cosmology becomes a laboratory for disciplined speculation. Start from a genuine tension singularities, information loss, the origin of order. Propose a mechanism bounce, bridge, reproduction. Derive concrete consequence echoes in gravitational wave ringdowns, transient bursts, altered mass spectra, correlation patterns in late-time radiation. Then feed those consequences into instruments that can answer yes or no. Humility becomes a superpower. You can hold the image of a universe birthed from a dying star while still admitting that, until a signature is found, the image is an invitation to work, not a claim to truth. Let the closing feeling be calm rather than fevered. Black holes are the tightest knots nature ties, and it is not an insult to Thema to suspect that inside those knots the fabric does not tear but reweaves, perhaps into threads that never touch our loom again. Whether that reweaving births new expanses or simply arranges the ledger so information is never truly lost. The path to knowing remains the same as always. Write down what a positive detection would look like in data. Write down what a null result would look like. And keep listening to the sky until it answers. Now shift your attention to another bold idea: entropic gravity dressed in cosmological language. Imagine gravity not as a fundamental force that acts on its own, but as the universe's preferred way of arranging information. Much like a crowded room naturally opens a path toward the exit. This is the heart of the entropic gravity proposal. The pull we feel becomes a tendency of systems to move towards states that have more microscopic arrangements. The stage for this dance is not a laboratory bench, but the whole expanding cosmos. Begin gently with thermodynamics. Heat flows from hot to cold, and systems drift toward configurations with more possible microstates. Black holes already extend that lesson. They behave like thermal objects with a temperature and an entropy tied to their horizons. Entropic gravity takes these hints seriously and asks whether ordinary gravitational attraction might be understood as an emergent, entropic force. When matter's position changes, the number of accessible microstates encoded on surrounding information screens shifts. Motion toward mass then becomes favored not because an invisible hand pulls, but because more ways to arrange the underlying bits become available. Dress this picture in cosmology, and a striking idea emerges. The universe's own horizon, the farthest distance from which light has ever had time to reach us, carries an entropy and a faint temperature. Perhaps cosmic acceleration and some galaxy-scale mysteries are not signs of unseen substances, but reflections of how information is stored and counted on horizons. In these models, the presence of matter deforms the bookkeeping of microstates on notional surfaces that wrap it. Motion toward mass is then favored, not by a mysterious pull, but because the information medium offers more configurations when you move that way. Add the expanding background with a positive vacuum energy, and those information surfaces inherit a constant horizon-scale temperature. Combine the two effects, and you obtain an extra, extremely gentle acceleration that becomes relevant only when ordinary gravity is very weak, precisely the regime of galactic outskirts and the larger-scale cosmic web. That feature matters because it naturally points toward the low acceleration anomalies that standard gravity explains by adding dark matter. The flat rotation curves of spiral galaxies, the motions of stars in dwarf galaxies, and some lensing measurements that seem too strong if only visible matter is present all, could be reproduced by an emergent, entropic response of the information-bearing medium tied to the Hubble scale. In plain terms, the universe's expansion endows space with a memory that reveals itself when gravity is feeble. This memory produces an extra apparent gravity around ordinary matter, growing in significance as acceleration decreases. It yields scaling relations that observers actually measure, such as the tight link between a galaxy's total rotation speed and the amount of visible matter it contains. In its cosmological dress, the framework also tries to connect cosmic acceleration to horizon thermodynamics. If the entropy associated with the horizon grows as the universe expands, an effective repulsive pressure can appear, driving the late-time speed up not as a new fluid, but as a bookkeeping property of information. The attraction of this program lies in its economy. One principle of gravity as emergent from information could, if successful, bind together black hole thermodynamics, galaxy kinematics, lensing, and cosmic acceleration. Yet the road to earning that economy is steep, and the honest lesson lives in the tests. On galaxy scales, some entropic gravity-inspired models recover the observed rotation curves and the radial acceleration relation with surprisingly few knobs. In certain regimes, they match weak lensing signals around galaxies, using only the light we see. On cluster and cosmic web scales, however, the story becomes harder. Lensing and hot gas in massive clusters demand more pull than visible matter provides, and entropic corrections tied only to the horizon often fall short, unless additional components or refinements are introduced. The celebrated Bullet cluster, with its offset between stars and hot gas, is a stress test for any theory that denies dark matter. Any such theory must reproduce the lensing map's mass peak, without invoking unseen particles. Entropic approaches attempt to attribute the extra pull to the information medium's response to the collision, but detailed fits remain under debate. The cosmic expansion history offers another crucible. Distances inferred from supernovae and standard rulers carved in the galaxy distribution form a tight ladder that any model must climb. If cosmic acceleration is an entropic effect, the predicted time dependence must line up with these measurements, while also satisfying the early universe anchors set by the oldest light. Then comes growth. How fast structures assemble over time is measured by weak lensing, galaxy flows, and the late-time imprint on relic photons. Any theory that modifies gravity must hit not only the geometric target show far things are, but also the growth target show fast things clump. Some current entropic implementations struggle to fit both without reintroducing ingredients that look suspiciously like dark matter in new clothing. This is not a dismissal, but a research agenda. It nudges theorists to make the microphysical picture explicit. What are the bits? Where do they live? How do they evolve? And it invites observers to design discriminating probus comparisons of lensing and dynamics in low acceleration dwarfs, precision maps of rotation curves that minimize messy astrophysical feedback, cluster-by-cluster audits that test whether any extra pull traces stars, gas, or neither, and redshift-bar-redshift slices of structure growth that reveal whether gravity's strength drifts in the regime where entropic effects are supposed to matter. Even if the full program never replaces dark matter, conceptual dividends already emerge. Horizon thermodynamics has reshaped how we think about gravity by insisting that areas, temperatures, and information are not mere metaphors, but measurable properties. The thermodynamic viewpoint explains why horizons behave like thermodynamic systems and why the cost of information carries geometric weight. If, in the end, dark matter remains the better explanation for most phenomena, an entropic component could still live alongside it, clarifying why certain galaxy relations are so tight and why cosmic acceleration looks so simple. All of this may sound like a dense tapestry of equations and speculative threads, but at its heart it is a call to cultivate a mindset that balances wonder with rigor. You are invited to stand at the crossroads of imagination and observation, to let daring ideas rise like bright constellations, then to test each one with the steady lamp of data. When a hypothesis predicts a faint flash, you help design the detector that could catch it. When a model suggests an echo in a gravitational wave, you listen for that subtle reverberation. When an entropic explanation offers a new view of galaxy rotation, you compare it with the precise maps of starlight and dark halos. Each step reinforces a habit: propose boldly, interrogate thoroughly, accept humility when the evidence says no, celebrate when it says yes. Remember that the universe rewards those who keep both curiosity and discipline alive. The knots of black holes, the bridges of entanglement, the horizons that store information are reminders that the cosmos is both a puzzle and a teacher. It does not demand that we surrender to mystery, it invites us to engage with it systematically, to turn questions into experiments, to turn wonder into knowledge. As you move forward, carry this calm confidence: the path to truth is not a sprint toward a single revelation, but a marathon of careful steps, each one guided by the twin lights of imagination and evidence. Let the sky be your laboratory, let your mind be the instrument, and let the rhythm of inquiry be the soundtrack to every discovery yet to come. Imagine standing at the edge of a cosmic laboratory, feeling the pulse of the universe whispering clues into your ear. You have already learned how a faint echo in a gravitational wave can become a revelation, how an entropic correction can reshape the way a galaxy bends light. And now you are about to step deeper into the frontier where theory meets observation. In certain regimes, the picture looks surprisingly simple. The weak lensing signals that halo around galaxies can be matched using only the light we see, as if the invisible scaffolding of spacetime is quietly echoing the distribution of stars. But once we widen our gaze to the massive clusters and the sprawling cosmic web, the story gains complexity. The lensing maps and the scorching plasma in huge clusters demand more gravitational pull than the visible matter can supply. Entropic adjustments that tie the pull to the horizon alone begin to fall short unless we invite extra ingredients or refine the framework. The iconic bullet cluster, with its striking offset between glittering stars and searing gas, becomes a stress test for every idea that hopes to dispense with dark matter. Any theory that wishes to replace unseen particles must still reproduce the sharp mass peak in the lensing map, and it must do so without secretly slipping in a hidden mass. Some entropic approaches try to answer this by attributing the extra attraction to the response of the information medium during the colossal collision, but the detailed fits remain a lively debate among those who dare to look. Now turn your attention to the expansion history of the universe, another crucible where ideas are forged. Distances measured from exploding supernovae and from the regular spacing of galaxies create an elegant ladder that any model must ascend. If cosmic acceleration is an entropic effect, then the time dependence it predicts must line up precisely with those measurements, while also honoring the early universe benchmarks set by the oldest light we can see. Then there is growth, the way structures assemble over cosmic time. Weak lensing, the flow of galaxies, and the lingering imprint on relic photons all record how fast matter clumps together. Any modification of gravity must hit two targets at once: the geometric distances that tell us how far things are, and the growth rates that tell us how quickly they gather. Some current entropic implementations stumble here, bending to fit one target while drifting away from the other. And in doing so, they often reintroduce elements that look uncannily like dark matter wearing a different coat. This is not a dismissal, it is an invitation to a research agenda that urges theorists to spell out the microscopic picture. What are the bits that make up the information medium? Where do they live? And how do they evolve? And how do the exquisitely precise laboratory tests of gravity emerge unchanged from the same set of rules? The challenge nudges observers to design discriminating probes, comparisons of lensing and dynamics in low-acceleration dwarf galaxies, precision maps of rotation curves that trim away messy astrophysical feedback, cluster-by-cluster audits that test whether any extra pull follows stars, gas, or something else, and redshift-by-redshift slices of structure growth that reveal whether gravity's strength drifts, where entropic effects should matter. Even if the full program never supplants dark matter, there are conceptual dividends. Horizon thermodynamics has already reshaped our thinking about gravity, by insisting that areas, temperatures, and information are not mere metaphors but measurable properties. The thermodynamic viewpoint explains why horizons behave like genuine thermodynamic systems and why the cost of information carries geometric weight. If, in the end, dark matter remains the more robust explanation for most phenomena, an entropic component could still coexist, clarifying why certain galaxy relations are so tight and why cosmic acceleration appears remarkably simple. If, on the other hand, a fully developed entropic theory carries the heavy lifting on its own, it will have to survive the bluntest of comparisons, not with poetry, but with the same data that now favor dark matter and a cosmological constant. Either way, the practical lesson that you carry out of this room is clear: treat gravity not as a single unquestioned primitive, but as a candidate emergent behavior, just as temperature emerges from the jitter of molecules. Write down what that view predicts for the sky rotation curves, lensing maps, cluster dynamics, the way structure grows, the particular time shape of acceleration, and ask the cosmos to grade it. The calm closing note is this: the universe keep handing us clues that geometry and information talk to one another. Horizons have heat, areas hold entropy, black holes count their bits, and entropic gravity in a cosmological dress is a disciplined attempt to listen. Whether it becomes the headline or remains an accent, its value lies in how it forces clarity about what we have measured, what we assume, and how the deepest rules might prefer to be written. Now shift your imagination to a different, but equally daring idea universe that mirrors itself through the Big Bang. Picture a seamless boundary at the moment of creation where two lawful histories meet back to back. On your side, matter expands outward and the arrow of time points away from that seam. On the opposite side, an ant-universe expands the other way, its arrow pointing outward in the opposite direction. Together, the two halves satisfy the deepest symmetry of our microscopic laws: CP charge, parity, and time reversal. The rule declares that physics looks the same if you swap particles for antiparticles, flip left and right, and reverse time. This symmetry becomes the heart of the CP-Symmetric universe proposal, which treats the Big Bang not as a unique explosion, but as a Janus point where two mirror worlds join. Begin gently. You already know that quantum field theory respects CPT in every experiment we have managed to stage. Cosmology usually carries that respect along for the ride, but it also adds extra ingredients: special initial conditions, mechanisms to create more matter than antimatter, perhaps new fields to drive early acceleration. The CP-Symmetric review asks whether you can do more with less. If the whole spacetime is symmetric across the bang, your universe on one side and the ant-universe on the other, many mysteries become bookkeeping. The tiny excess of matter over antimatter that we observe is matched by an opposite excess of antimatter on the other side, preserving a global balance without inventing a one-sided creation trick. The arrow of time does not need to be injected from outside, it emerges on both sides from the same low-entropy start. A shared, extremely simple boundary where degrees of freedom are minimally excited, and the overall geometry is driven to be exactly flat and smooth by the symmetry itself, not by a special push. Dive into the details that you can test without drowning in heavy algebra. In a CP-symmetric cosmology, the particle menu becomes constrained. The neutrino sector, already a place where nature has left us clues, carries a special burden. If the mirror across the bang is exact, the way neutrinos acquire mass must mesh with symmetry in a tight way, often suggesting that neutrinos are their own antiparticles, or that one right-handed neutrino never mixes with the visible ones and becomes a naturally stable dark matter candidate. That kind of dark matter would be born thermally or gravitationally at the seam, carry no electric charge, and interact so faintly that it leaves almost no laboratory trace beyond its gentle gravitational pull. Yet it would subtly influence the growth of structure and imprint a specific pattern of small-scale clumping that large surveys can chase. The same mirror logic reshapes how you think about the universe's earliest wrinkles, the tiny variations that seeded galaxies. Instead of invoking a separate inflationary field with an adjustable shape, a CP-symmetric picture looks for ways those wrinkles could arise from quantum fluctuations tied directly to the time-symmetric boundary itself. Done carefully, this can yield nearly scale-free seeds with the right slight tilt, while predicting that certain telltale backgrounds, like a loud bath of primordial gravitational waver, should be absent or extremely faint. That absence is not hand-waving, it turns into a clean, falsifiable statement about the sky's polarization curls on the largest angles. The arrow of time gains a clearer, less mystical face too. On both sides of the seam, low entropy at the bang means few records. As each universe expands away from the seam, interactions write durable marks, photons scattering off dust, decays, star formation, and entropy grows. Observers in either half remember only the direction that points away from the waste. You and your hypothetical anti-counterpart are not separated by a single master clock. You each live on branches whose clocks point outward from the same simple middle. The symmetry turns the puzzle of why matter dominates one side into a matter of bookkeeping rather than a special act. Even the cosmic neutrino background, the faint sea of relic neutrinos permeating space, becomes a calibrated probe. Its temperature and the possible presence of a sterile component are no longer loose parameters, but are linked to the symmetry's demands, offering laboratory and astrophysical tests through beta decay experiments, neutrino oscillations, and cosmological fits to the early universe. The beauty of this framework lies in its discipline. It strips away discretionary knobs and asks you to accept or reject a package of predictions. Among them are exact spatial flatness, at a level that future maps of the cosmic microwave background and galaxy clustering can keep squeezing. A specific, nearly scale-free spectrum of initial density variations with limited freedom for exotic non-randomness, a sharply limited or vanishing primordial gravitational wave background, and a neutrino sector with relations between masses and mixings that can be checked by oscillation experiments and by searches for neutronolaless double beta decay. The discovery of the continued absence of such processes would speak loudly to how real the CPT mirror truly is. Of course, sober challenges keep the idea honest. You must show that a time-symmetric boundary can truly replace the usual processes that generate the observed matter excess without spoiling the light element abundances forged in the first few minutes. You must demonstrate that the seed pattern inferred from the sky can be produced without hidden fine-tuning, and that late-time structure forms on schedule. And you must reconcile the mirror's austerity with any future detection that plainly demands extra early universe drama. For example, a robust detection of long-wavelength gravitational waves at levels natural for a traditional rapid expansion story. The framework also forces clarity about initial conditions. Instead of positing an arbitrary, complicated start, you impose a simple symmetric boundary that by construction minimizes degrees of freedom. Then you let dynamics write the complexity you observe, turning a metaphysical hunch into a testable prior. On a human scale, the payoffs are less theatrical and more methodological. This mirror view invites you to re-ask each big question: dark matter, the arrow of time, the slight matter-antimatter victory, the shape of primordial ripples with the discipline of symmetry. If a single principle can simultaneously account for several puzzles and reduce the number of free buttons we press, it deserves a fair hearing. If data refuse it, they will do so with specificity, pointing to the precise prediction that snapped first. It also softens an old anxiety. You are not required to imagine a universe that is completely separate from its mirror. Instead, you read correlations across a boundary where before and after are labels that flip in the reflection. And it ends on a quiet, empowering note. Whether the universe truly has a CPT twin across the bang will not be decided by slogans, but by a conjunction of sky maps, neutrino experiments, gravitational wave limits, and careful fits to structure growth, each a place where the mirror's clean lines become numbers. You are invited not to romance a symmetry for its elegance alone, but to let that elegance earn its keep in the ledger of observations. If it passes, we will have traded several separate assumptions for one deep constraint. If it fails, we will have learned precisely where the cosmos insists on a symmetry, which itself becomes a map toward whatever law holds the real mirror up to the world. Now, step even farther into the frontier of imagination and consider the notion that space itself might emerge from quantum entanglement. Imagine starting not with points and distances, but with relationships. Think of the way notes in a chord define each other, and then be told that space could be nothing more than the larger-scale shadow of those relationships as they deepen and spread. That is the intuition behind emergent space from entanglement growth geometry is not the stage, but the ensemble sound of quantum connections. And when those connections strengthen in the right patterns, volumes and horizons appear just as melodies arise when many tones lock into harmony. Begin gently again, this time with the language of quantum systems. Entanglement measures how much two parts know about each other beyond what either knows alone. Simple many-body experiments already show that increasing this shared information reorganizes what is accessible and how signals move. When you crank up entanglement across a lattice, the effective distance for excitations can shrink, and the way information propagates begins to reflect a geometric structure that was not there before. Scale this idea up, and you begin to see how a network of quantum bits, tightly interwoven, could give rise to an emergent notion of distance, direction, and even curvature. If you let your mind wander through this picture, you may feel the excitement of a new way to ask the old questions. What determines the shape of a galaxy's rotation curve? Perhaps it is the way entanglement density varies across the quantum fields that fill the region. What sets the lensing map of a galaxy cluster? It could be the way information threads through the underlying quantum fabric, bending the paths of photons as if space itself were a flexible sheet. How does structure grow over cosmic time? Maybe the increase in entanglement between distant regions fuels the clumping of matter, providing an effective attractive force without invoking an invisible particle. And what about the accelerating expansion of the universe? The thermodynamic cost of maintaining or changing entanglement could manifest as a pressure that pushes space apart. The power of this perspective lies not only in its elegance, but in its concrete, testable consequences. If geometry emerges from entanglement, then the equations that describe how light bends, how galaxies spin, and how the universe expands must all be derivable from underlying quantum information principles. This means you can write down predictions for rotation curves that depend on measurable quantities like the entanglement entropy density. Design precision lensing surveys that compare the inferred mass distribution with the pattern of quantum connections, and construct high-resolution simulations that track how entanglement spreads as structures form. Moreover, you can look for signatures that would be impossible under a purely particle dark matter, picture subtle deviations in the relationship between baryonic matter and gravitational potential that track changes in quantum mutual information. Imagine now that you are part of a community that builds such experiments. You collaborate with astronomers who map the faintest distortions of distant galaxies, with particle physicists who probe the neutrino sector for clues about hidden symmetries, and with quantum information theorists who devise ways to quantify entanglement in field theories that describe the cosmos. Together you design discriminating probes dwarf galaxies in low acceleration regimes where the entropic or emergent gravity signals should be strongest, clusters where the offset between stars and hot gas offers a clear laboratory, and redshift slices that trace how the effective gravitational coupling drifts over billions of years. Each observation becomes a conversation with the universe, asking it, do you speak in the language of information? Your role as a narrator of this quest is to keep the fire of curiosity burning. Remind yourself and your listeners that every equation you write, every telescope you point, every particle detector you calibrate is a step toward listening more closely to that cosmic conversation. The universe is generous. It offers clues in the temperature of horizons, the entropy of black holes, the pattern of galactic rotations, the faint hum of relic neutrinos. It even hints that the very fabric of space might be a collective echo of quantum relationships. Your task is to translate those whispers into a coherent story that can be tested, refined, or even overturned. In this grand adventure, do not be disheartened by the challenges. The bullet cluster remains a demanding test. The growth of structure demands that any alternative gravity model hit both geometry and rate. The CPT-Symmetric picture asks you to match precise neutrino measurements. Emergent space asks you to bridge quantum information theory with astronomical observations. Each obstacle is an invitation to sharpen your ideas, to devise new experiments, to push the boundaries of what we can measure. The path is not smooth, but it is illuminated by the very data you seek to explain. So, as you move forward, Hold on to a simple principle, treat every law of physics as provisional, every assumption as a hypothesis awaiting the verdict of the cosmos. Write down what your theory predicts for the sky-beat rotation curves that fall off in a specific way, lensing maps that align with entanglement gradients, or neutrino spectra that obey CPT symmetry, and then step outside and ask the universe to grade those predictions. Let the data be your stern but fair judge. When you close your notebook after a day of calculations, when you lower the telescope after a night of observation, remember that you are part of a lineage of seekers who have turned the abstract beauty of mathematics into tangible knowledge about the world. The ideas you wrestle with: entropic gravity, CPT-mirrored universes, emergent spatial, not fanciful flights, they are disciplined attempts to listen more closely to the universe's own story. Whether any of them becomes the headline or remains a useful footnote, they each sharpen our questions, focus our measurements, and deepen our appreciation for the intricate dialogue between geometry, information, and matter. Take a breath. Feel the quiet confidence that comes from knowing you are contributing to that dialogue. The universe keeps handing us clues. It is up to us to assemble them with rigor, imagination, and relentless curiosity. Let that be the anthem that drives you forward, a relentless pursuit of understanding, a willingness to test every bold idea against the sky, and an open heart for the unexpected ways the cosmos may reveal itself. The next breakthrough may come from a subtle deviation in a dwarf galaxy's rotation curve, from a faint whisper in the neutrino background, or from a fresh insight into how entanglement weaves the fabric of space. Keep listening, keep questioning, and keep moving forward with confidence that each step, no matter how small, brings the grand tapestry of the universe into clearer view. Imagine standing at the edge of a vast, silent ocean of possibility, where each ripple is a clue about the deep rules that shape everything we see. In that moment, you feel the thrill of a discovery that could reshape a whole story, a robust detection of long-wavelength gravitational waves, whispering that the early universe might have blossomed in a way that feels natural to the most elegant, rapid expansion narratives. The beauty of such a signal is that it forces us to strip away unnecessary baggage. Instead of inventing a convoluted, ad hoc beginning, we can lay down a simple, symmetric boundary that by its very construction minimizes the number of free choices we have to make. Then we let the dynamics of the cosmos write the complexity we observe, turning a philosophical hunch into a concrete, testable prior. On a human scale, the payoff is not fireworks, but a method that steadies our curiosity. This mirror-like viewpoint invites you to revisit every big question, a mysterious dark component, the stubborn arrow of time, the faint fingerprints left by primordial ripples with the disciplined lens of symmetry. When a single principle can simultaneously tame several puzzles and shrink the number of independent knobs we turn, it deserves a careful, open-hearted hearing. And if the data push back, they do so with a precision that points out exactly which predictions snapped first, guiding us toward the next step, instead of leaving us adrift in vague doubts. What is especially comforting in this perspective is how it eases an old anxiety. You are not forced to conjure absolute, isolated explanations before you have any clues. Instead, you learn to read correlations across a boundary where before and after are just labels that flip in a mirror. The story ends not with a grand slogan, but with a quiet, empowering invitation. Whether the universe truly carries a CPT twin across the bang will not be decided by clever taglines, but by the convergence of sky maps, neutrino experiments, gravitational wave limits, and meticulous fits to the growth of structure. Each of those pieces turns the clean lines of a mirror into hard numbers. You are asked not to romance a symmetry only for its elegance, but to demand that its elegance earn its place in the ledger of observations. If that symmetry stands up to scrutiny, we will have swapped several separate assumptions for one deep constraint, a trade that feels like gaining a powerful new tool without adding weight to our mental backpack. And if it fails, the failure itself is a map, a precise indication of where the universe insists on a symmetry, pointing us toward whatever law holds up the real mirror to the world. In this dance of hypothesis and data, we learn that every false note is as valuable as a triumph, because it narrows the tune we must ultimately play. Now picture space itself not as a static stage, but as a living tapestry woven from quantum relationships. Think of the early cosmos not as a collection of points and distances, but as a network of connections that deepen and spread, their growth giving rise to the very notion of volume. This is the intuition behind emergent space from entanglement. Growth geometry is not the backdrop. It is the emergent melody that arises when many quantum notes lock into harmony. Start softly. In quantum systems, entanglement measures how much two parts know about each other beyond what each knows alone. Simple many-body experiments already reveal that as shared information increases, what can be accessed and how signals travel both reorganize. Scale that insight up with discipline, and a sharper picture appears. Patches of space become proxies for chunks of a deeper quantum state, and the distance between them reflects how hard it is to separate their information. When correlations are sparse, the world feels far apart. When they thicken along particular channels, those channels become short bridges, bending the map we call geometry to reflect their strength. In certain solvable models, the minimal amount of information needed to describe a region, the cost of compressing it without loss, naturally scales with the area of its boundary rather than its volume. That hints that surfaces, not bulks, are the true counters of information. When you vary the quantum state, the change in that boundary information tracks how surfaces would curve in a would-be space. More entanglement literally reads as more room, in a precise, quantitative way. Build a toy universe as a layered network that coarsens information step by step, pushing local details downward while preserving long-range structure. As you climb the layers, a geometry emerges that looks like space growing. Inject extra entanglement along a corridor, and that corridor thickens into a shorter path, a vivid metaphor for how specific quantum ties can pull two regions closer in the emergent metric. This is not merely poetic metaphor, it is a working language in which gravitational dynamics translate into statements about how entanglement responds to tiny nudges. Make a localized change to the quantum state, and the rule that entanglement cannot drop below a certain bound becomes the balance law that tells curves in space how to shift. Expand the system so its entanglement spreads, and the volume measured by these information rules grows in step, forming an arrow that points from the scrambling of quantum data to the expansion of space. Even the sturdiness of spacetime finds a natural home here. If bulk information is redundantly encoded across overlapping boundary pieces, losing a few pieces does not erase the message, it merely shifts which combination can decode it. In geometric language, that redundancy appears as the ability to reconstruct events inside a region from many different vantage patches. Slightly reshape the frontier, and the same interior remains accessible. This robustness mirrors how a well-crafted language tolerates a few typos without losing meaning, and it explains why horizon spaces where access falters behave like bottlenecks in information flow, carrying a limited number of letters that cap how much can be stored behind them. Dynamics adds another layer of wonder. Take two formally disconnected quantum subsystems and let them interact. As entanglement grows, the effective distance between their emergent regions shrinks. Drive the growth fast enough, and a bridge forms that lets signals traverse more quickly than when the subsystems were austere and separate. The geometric avatar of this bridge is what you would call a throat. Slow the growth, or inject noise that degrades long-range ties, and the bridge thins, lengthens, or pinches off. None of this requires abandoning causality. It simply asks you to recognize that who can talk to whom, and with how much effort, is the deeper grammar that geometry summarizes on the macroscopic stage. The early universe offers a particularly illuminating laboratory for this view. Instead of inserting a mysterious agent to push space larger, ask whether a simple, low-complexity quantum station with minimal entanglement across vast separations naturally evolves under ordinary interactions into a state whose entanglement fans outward at nearly light-like speed, and whether the associated growth of informational volume matches the smooth, nearly flat space we observe. In carefully tuned models, the answer leans toward yes in spirit, starting from a restrained pattern where distant regions hardly share anything. Entanglement floods outward, quickly knitting the state together, ironing out irregularities and producing a uniform larger-scale map, while preserving delicate small-amplitude differences that later become structure. In that script, thermalization and the spread of quantum information are not nuisances, but the engines that write geometry. The curves that track how much information any subregion holds up to a given time act like rulers for how much bulk that subregion commands, and the late-time saturation of those curves signals that a maximal, horizon-like surface has formed beyond which new volume can only be gained by pushing information deeper rather than wider. The same lens reframes familiar gravitational puzzles in practical language. The stability of a smooth region against small shakes, normally described by delicate balances of curvature, translates into statements that certain entanglement inequalities cannot be violated. Violate them, and the emergent geometry kinks or tears. Massive bodies curving space in proportion to their energy becomes the statement that adding highly mixed, hard-to-compress information to a region raises the complexity of decoding anything that passes through, effectively lengthening paths and bending neighboring connections toward it. Even black holes take on an information-first face. They are where entanglement saturates the local budget, making the boundary cost scale with area at its maximum and isolating interior data behind a code that only vast, global decoders can unpack over very long times. On the observational front, this program earns credibility by whether it can organize disparate facts into one coherent ledger. It should explain why horizons carry temperature, why large regions behave classically when their underlying quantum state is massively redundantly entangled, and why gravitational dynamics emerge from what look like bookkeeping identities among entropies. It should also clarify why errors in small subsystems rarely produce catastrophic changes in larger-scale geometry. Skepticism, properly aimed, fortifies rather than weakens the picture. If geometry is emergent, you must demonstrate how it remains precise where experiments demand it. Planetary orbits, gravitational waves, lensing arcs despite being built from messy quantum threads. The answer lies in redundancy. When countless microconfigurations encode the same coarse fact, the average becomes sharply defined and fluctuations shrink like background hiss that disappears under a chorus of microphones. Yet not every entanglement pattern yields a smooth, low-dimensional space. Many produce fractal or wildly curved messes. The physical world is therefore telling us that its fundamental state is special, privileging local, layered correlations that knit short-range ties first and only then compose them into longer roads. This constraint is not a disappointment, it is a clue to the principle that replaces space as a given. It points to a deeper law that orders how relationships grow, how redundancy builds robustness, and how the tapestry of reality gains its familiar shape. Close now with the calm perspective this view is meant to teach. Emergent space from entanglement growth does not ask you to pretend that atoms and telescopes are illusions. It asks you to see that the map they inhabit is a high-level summary of a deeper conversation among quantum degrees of freedom. A conversation whose grammar is redundancy, whose verbs are scrambling and error correction, and whose nouns are surfaces that count how much can be known. When that conversation intensifies, space grows. When it frays, distances lengthen. When it saturates, horizons form. The gift of this frame is not poetic fluff, but economical power. The same concept that explains why horizons have heat, why classicality emerges from quantum noise, and why gravity respects particular balance laws also explains how the universe could knit itself into a smooth, roomy place starting from a remarkably simple beginning. Let that settle in your mind. The question, where are we, becomes a question about how our corner of the world is encoded in the whole. The question, why is there room, becomes a question about why entanglement kept rising steadily enough, broadly enough, and redundantly enough to turn a network of relationships into the space we move through and the night sky we read for clues. Now, open your palm and imagine you are holding every possible arrangement the early universe could have chosen. Most of them would be chaotic, lumpy, already saturated with disorder. And then notice the vertigo that comes with the fact that our cosmos picked an astonishingly tidy one instead. That initial low entropy is the careful way to ask why the first frame of the cosmic movie was so improbably ordered that a thermodynamic arrow of time could even exist for stars' life and memory to follow. Begin gently. Entropy is not a mystical fog, it is a way of counting. When we say low entropy, we mean few macroscopic possibilities compatible with what we see. For a gas in a box, low entropy is all the molecules huddled in a corner. For the universe, the subtlety is that most of its entropy budget lives in gravity's hands, and gravity's idea of disorder runs opposite to everyday intuition. So as you listen, let this vision of emergent space and symmetric beginnings inspire you to seek simplicity amid complexity, to trust that deep patterns can replace ad hoc explanations, and to recognize that every hint from the cosmos is an invitation to refine the story you tell yourself about reality. In the quiet moments of reflection, feel the confidence that comes from aligning your curiosity with principles that have the power to turn countless mysteries into a single, elegant narrative. And remember, the same spirit that guides physicists to look for mirrors in the fabric of the universe is the spirit that can help you reflect on your own path, strip away unnecessary noise, and let the essential connections in your life expand, deepen, and reveal the spacious horizon you have always been meant to explore. Imagine a universe that, at its very beginning, chose a path of unexpected elegance. Picture holding in your palm every possible way the cosmos could have arranged itself: chaos, clumps, tangled knots, a frenzy of disorder. Yet, in that breathless moment of creation, the cosmos settled on a remarkably tidy canvas. That serenity is not a flaw, it is a clue, a whisper that space itself is woven from the quiet growth of connections. Think of entanglement as a conversation among the tiniest threads of reality, a dialogue where the grammar is redundancy, the verbs are the relentless scrambling and error correction that keep the fabric coherent, and the nouns are the surfaces that tell us how much can be known. When this dialogue intensifies, space stretches when it frays, distances feel longer when it reaches its limit, horizons appear like gentle walls of heat. This picture does not ask you to dismiss atoms or telescopes as mere illusion. Instead, it invites you to see that the map we navigate planets, stars, the very room you sit in is a high-level summary of a deeper, buzzing conversation among quantum degrees of freedom. Let that thought settle in your mind like a calm lake at dawn. The same principle that explains why black holes radiate warmth, why the classical world emerges from quantum noise, and why gravity obeys precise balance laws also tells us how a vast, roomy universe could unfold from an almost unimaginably simple beginning. The specialness of that first frame is the reason we can even ask where we are and why there is room for us to move, think, and wonder. The answer lies in the steady, broad, and redundant rise of entanglement, which turned a raw network of relations into the space you now walk through, the night sky you read for clues, and the very possibility of memory itself. Consider the notion of low entropy not as a mystical fog, but as a straightforward way of counting possibilities. When we speak of low entropy, we mean that only a few macroscopic configurations are compatible with what we observe. Imagine a gas in a box. Low entropy is all the molecules huddled in one corner. For the universe, the story is richer. Most of the universe's entropy budget is held in the hands of gravity, and gravity's idea of disorder runs opposite to our everyday intuition. A nearly uniform early cosmos, exactly what the oldest light tells you, actually represents an exceptionally low entropy state, because the smoothness leaves a massive reservoir of gravitational possibilities untapped. The matter had not yet collapsed into black holes, the champions of entropy, and the curvature degrees of freedom that could have roiled wildly remained quiet. In that sense, the baby universe resembled an immaculate stage, props neatly stacked backstage, ready for the drama of structure to unfold. Why does this matter to you? Because the arrow of time are the fact you remember yesterday, but not tomorrow. The way an egg scrambles, but never unscrambles, needs a boundary condition that is both simple and asymmetric. Simplicity allows us to state it without hidden complexity. Asymmetry provides a direction for statistical drift. The microscopic laws of physics are almost perfectly time-reversal symmetric. Left to themselves, they would make forward and backward look the same. What tips the balance is not a new law but a special beginning, a past hypothesis that the early universe occupied a tiny sliver of its allowed possibilities. From that modest start, gravity amplifies tiny differences, matter clumps, stars ignite, heavy elements are forged, black holes form, and entropy skyrockets. Not in spite of gravity, but because gravitational collapse unlocks an astronomical number of microscopic arrangements. Let's clear up a few common confusions. Low entropy is not the same as cold or simple ingredients. The early universe was scorching hot, yet its energy was organized. The disorder that could have been stored in space-time curvature and dense objects simply wasn't there. Low entropy also isn't a matter of human choice about how we coarser-grain reality. Our macroscopic variables densities, temperatures, smoothness are chosen because they correspond to stable, record-making features. If we tried to treat a scrambled egg as simple, our bookkeeping would fail to predict what actually happens. The reliability of our coarser graining lets us build engines, launch satellites, and understand the weather. The early universe's low entropy is measured in that same predictive language. Moreover, low entropy is not explained away by saying it had to be that way unless we supply a mechanism or a testable boundary rule. Some ideas invoke deep geometric constraints, suggesting the earliest slice of spacetime favored minimal gravitational curvature, making smoothness a rule rather than an accident. Others propose that cosmic expansion dynamically funnels many messy initial conditions into a small set of simple outcomes. Both approaches must precisely define what counts as generic and which degrees of freedom are truly tamed. The target remains the same account for why the space of allowed beginnings was effectively smaller than it appears. If you treated all gravitational wiggles as equally likely, low initial entropy would be the reason records work. A record a fossil, a photograph, a cosmic ripple is a localized, durable imprint that correlates with other imprints. To accumulate such records reliably, the world needs slack in its entropy budget so that correlations can proliferate in a preferred direction instead of being washed away immediately. The smooth young cosmos supplied that slack. As time flows, interactions copy information outward. Photons scatter off dust, atoms arrange into crystals, galaxies leave gravitational fingerprints, and entropy climbs. In this view, memory and complexity are not exceptions to the second law, they are its beneficiaries. Islands of organized structure persist because the environment the rest of the cosmos carries away wastes heat and increases its disorder. The specialness of the beginning is etched into every diary entry, every layered rock, every whisper of the cosmic microwave background. How special was it really? Honest answers admit we lack a universally agreed measure over all possible initial geometries and fields, so poetic phrases like one in a gazillion can be more metaphor than proof. Still, we can make two sturdy claims. First, relative to the set of macrostates that produce today's energy density and particle content, the smooth early state occupies an extraordinarily tiny region in state space, so tiny that if you randomly scattered matter and curvature, according to that macro description, you would almost always land in a world already dominated by black holes. Second, the growth of entropy since then has been immense, from a smooth plasma to a sky hosting supermassive black holes, whose entropies dwarf that of all ordinary matter combined. Those facts together encapsulate both the puzzle and the payoff. A tiny initial corner made the largest later explosion of possibilities feasible. Where does this leave explanation? There are three broad styles, each placing a different bet. One pins the answer on a fundamental boundary condition: the universe began in a state that, by law, minimized certain gravitational features, much as a vibrating string is held fixed at its ends. Future observations would test the byproducts of that minimality, such as the exact flatness of space or the detailed statistics of primordial ripples. A second style seeks a dynamical attractor that drives vast classes of initial micro-arrangements toward simplicity. Yet this rote must demonstrate that the very modes that maximize gravitational entropy are truly damped by the dynamics you posit. It is not enough to show smoothing of matter if the gravitational degrees of freedom are left free to roam. A third leans on selection across a larger ensemble. If many regions exist with varied beginnings, observers appear only where low initial entropy provides an arrow and stable chemistry. This reasoning is logically consistent, but it earns scientific weight only when paired with a measure that predicts observable quantities rather than resting solely on habitability. Through all of this, a quietly radical lesson emerges. The second law in a universe with gravity is not about disorder everywhere all at once. It is about the growth of available gravitational configurations while local aces of order ride atop a global tide of increasing entropy. Your ability to learn from the sky, the fact that the oldest light preserves a faint pattern of early smoothness with tiny informative imperfections, depends on that. Let the most useful takeaway settle gently in your mind. Low initial entropy isn't a hand-waving mantra, but a concrete, falsifiable stance about the first page of the cosmic ledger page, with few excited gravitational degrees of freedom, an absence of dense objects that would have saturated entropy early, and a macroscopic smoothness that left headroom for records and complexity. Whatever deeper story eventually wins geometric constraint, genuine dynamical funnel, or principled selection, it will have to reproduce that ledger and explain why the world began in a state that let time have an arrow strong enough to carry galaxies, geology, and thought. Until then, the specialness of that beginning is not an embarrassment. It is the reason there is a then at all, and the reason your questions have somewhere to go. Now, let's turn to the role of selection, the subtle art of anthropic reasoning and its limits. Start with a modest observation that can feel like a cheat code. You find yourself in a universe that permits beings like you, much as a fish finds itself in water. The right question isn't the circular "why are we here?" but rather what can we learn once we take that selection effect seriously. That is the beating heart of anthropic reasoning. Selection effects are everywhere in honest inference. Astronomers correct for the fact that bright objects are easier to see. Doctors adjust for the fact that volunteers for trials aren't a random sample. So it is not scandalous to say that if the universe allows a wide spread of conditions, then our data are drawn from the rare subset where chemistry, long-lived stars, and stable structures exist. In that spirit, anthropic filters can explain why certain cosmic knobs sit in narrow bands. If the background push of empty space were much larger and positive, galaxies would never condense. If it were large and negative, the universe would crunch before stars formed. If the early density ripples were far weaker, structure would stall. If they were far stronger, everything would collapse into black holes too quickly for complex chemistry. If nuclear resonance energies shifted too much, carbon and oxygen yields would plummet. Each of these is a new observer's boundary that trems the space of possibilities, and when used well, yields upper or lower bounds that match what we measure to a pleasing degree. But do not mistake a filter for a full explanation. Anthropic arguments at their best can say why values cannot wander far, not why they land where they do within the allowed strip. That limitation is not pedantry, it is the difference between saying we survive only if the shore is somewhere between here and that cliff and saying we are exactly 10 paces from the waterline for a deep reason. To push deeper, the method demands 3 disciplined pieces of bookkeeping. First, you need a distribution over possible worlds, a theory of the larger set that tells you what values of the knobs are produced and how often. A landscape of vacua, a family of cosmological histories, a model of symmetry breaking. These are the scaffolds that give the distribution substance. Change that distribution and your anthropic prediction can flip. Second, you need a defensible rule for counting observers, because not all configurations that allow life generate the same number of conscious beings. Third, you must specify what counts as a record or a prediction that you can actually compare with observation, lest the argument drift into wordplay. When you hold these pieces together, the picture becomes richer and more powerful. The smooth, low entropy beginning gave the universe the slack it needed to record information, to copy it outward, and to let complex structures like galaxies, planets, and eventually brains arise. The growth of entanglement, the spread of correlations, the gradual build-up of gravitational horizons, all of these are chapters in a story that started with an improbable but purposeful simplicity. That story tells you that the arrow of time, the flow of cause and effect, the very fact you can ask questions, all flow from that first gentle choice of low entropy. So as you breathe in the present moment, remember that you are living in a cosmos that chose to be orderly at its birth, giving space to expand, time to move forward, and information to accumulate. The universe's special beginning is not a footnote, it is the foundation upon which every memory, every discovery, every wonder rests. Let that inspire you to seek out the connections that bind you to the larger whole, to recognize the quiet conversation of entanglement that stretches across the stars, and to appreciate that every thought you have is a ripple in that ancient dialogue. In this grand tapestry, you are both observer and participant, a living record of the cosmos' relentless march from simplicity to richness. Carry this perspective with you as you navigate the challenges of today. When difficulties arise, recall that the very ability to learn, to adapt, to create new pathways is rooted in the universe's generous slack born from that pristine, low-entropy dawn. Let that knowledge empower you, reminding you that the forces that shaped galaxies also shape the resilience within you. The same principles that turned a smooth plasma into a sky full of stars also turn a calm breath into a burst of inspiration. Embrace the idea that every step you take adds a new thread to the ever-growing conversation of the cosmos, and that by expanding your own entanglement with ideas, with people, with the world, you are participating in the same process that stretches space itself. So go forward with curiosity, with confidence, and with the quiet awe that comes from knowing you are part of a universe that began with extraordinary order, allowing an arrow of time strong enough to carry you forward. Let the story of the early universe be a lighthouse, guiding your thoughts, your actions, and your dreams toward horizons that, like those first cosmic horizons, are both warm and mysterious, inviting you to explore, to learn, and to become a living testament to the remarkable journey from simplicity to wonder. You are standing at the edge of a story that stretches far beyond the horizons of everyday life, a story whose opening chapter was written in the first moments of the universe, when the cosmos was still a delicate, low-entropy canvas. That pristine beginning left a generous slack, a kind of spare capacity for the universe to grow, to learn, to evolve into the rich tapestry of galaxies, rocks, oceans, and thoughts that you now inhabit. Let that awareness settle into your heart. You are the product of a vast, almost improbable generosity, and that very fact is a source of power you can call upon whenever doubt creeps in. Imagine, for a moment, the early universe as a smooth, almost featureless expanse. It possessed only a few excited gravitational degrees of freedom, no dense objects that could have saturated entropy in an instant, and a macroscopic smoothness that left room for records and complexity to emerge later. Whatever deeper story ultimately wins, whether it is a geometric constraint, a genuine dynamical funnel, or some principle of selection, it must reproduce that ledger and explain why the world began in a state that allowed time to acquire an arrow strong enough to carry galaxies, rocks, and thoughts forward. Until the final answer arrives, the specialness of those conditions is not a burden, it is the reason there is a then at all, and the reason your questions have somewhere to go. From this place of awe, let us turn to a tool that many scientists and philosophers reach for when they contemplate why we find ourselves in a universe that can host life. It is called anthropic reasoning, and while the name sounds technical, at its core it is a simple, almost cheating code insight. You are observing a universe that permits beings like you, just as a fish lives in water that supports its life. The crucial question is not the obvious "why am I here?" but rather "what can I learn once I take that selection effect seriously?" That is the beating heart of anthropic reasoning, and the place where its limits become a source of motivation, not frustration. Selection effects are everywhere we make honest inferences. Astronomers correct for the fact that bright objects are easier to see. Doctors adjust for the fact that only certain kinds of patients volunteer for trials. In the same spirit, if the universe allows a wide spread of possible conditions, then the data we actually collect come from the rare subset where chemistry, long-lived stars, and stable structures exist. In this light, anthropic filters can explain why certain cosmic knobs sit comfortably in narrow bands. If the background push of empty space were much larger and positive, galaxies would never condense. If it were large and negative, the universe would crunch before stars could form. If the early density ripples were far weaker, structure would stall. If they were far stronger, everything would collapse into black holes before complex chemistry could take hold. If nuclear resonance energies shifted even a little, carbon and oxygen yields would plummet, wiping out the building blocks of life. Each of these new observer's boundaries trims the space of possibilities, and when applied wisely they yield upper or lower bounds that match what we measure with a pleasing precision. Do not mistake a filter for a full explanation. The best anthropic arguments can tell you why values cannot wander far, but they do not tell you why those values land exactly where they do within the allowed strip. That limitation is not a shortcoming, it is the difference between saying we survive only if the shore lies somewhere between this cliff and that one, and claiming we stand precisely 10 paces from the water for a deep underlying reason. To push deeper, the method demands 3 disciplined pieces of bookkeeping, lest it drift into vague wordplay. First, you need a distribution over possible worlds, a sense of which values of the cosmic knobs are produced, and how often. This is not a matter of vague vibes, but a consequence of a concrete theory about the larger Seta landscape of Vacua, a family of cosmological histories, a model of symmetry breaking. Change that distribution, and your anthropic prediction can flip dramatically. Second, you need a defensible rule for counting observers. Do you count by number of stars, by number of habitable planets, by entropy production, by the capacity for information processing, or by observers who share our coarser-grained data? Each choice embeds a philosophy of typicality and can tilt conclusions, because who counts is not settled by physics alone. Third, you need a measure that regulates infinities away to compare frequencies when your theory produces unbounded space or endless branches. Different reasonable measures can privilege young regions, fast processes, or freak fluctuations unless you prove they do not. When those 3 pillars are clear, anthropic reasoning becomes a narrow, testable claim. Given a concrete theory that populates possibilities with a specific distribution, a stated typicality rule, and a measure, you compute the odds for observables conditional on the existence of observers with data like ours. And then you confront those odds with the single universe you can measure. The method has already scored genuine successes, even if not unique. Placing the cosmological constant in a small positive band rather than at a natural particle physics scale is surprising on dynamical grounds, but becomes unsurprising once you wait by the presence of galaxies across an ensemble. Similarly, the amplitude of early density ripples sits in the Goldilocks range for structure, a range that anthropic filtering keeps while many naive priors would not. Yet the limits arrive as quickly as the winds. The reference cyclus problem is not a nuisance. You can change the definition of observers like us, and your posterior can shift dramatically. The method is inherently poor at precise predictions. It draws soft fences, not target bullseyes, and any claim of laser accuracy is either hiding a tight prior in the theory or smuggling an unjustified typicality assumption. Anthropic arguments can also anesthetize inquiry if you let them. Declaring a value explained by selection before exhausting dynamical options short-circuits the very process that gave us successful mechanisms in the past symmetries. Conservation laws, attractors. The specter of freak observers random fluctuations in vast futures that could spawn minds with false memories forces you to build models where ordinary observers dominate, or else your conditional probabilities become absurd. When infinities loom, measures can produce paradoxes, youngness bias, runaway growth of hyperproductive regions that swamp the subtle selection you hoped would guide you. A respectable anthropic analysis must prove its conclusions are stable under small, motivated changes of the regulator. So what is the right use? Treat anthropic reasoning as a last-mile constraint in a larger pipeline. Start with a generative theory that produces a distribution of cosmic parameters. Test it against broad, non-anthropic data where possible. Only then apply selection to carve out regions where observers exist, and condition on our coarser-grained dataset not just any life, but the suite of facts we actually know: ambient radiation temperature, galaxy demographics, element abundances, planetary time scales. In this role, the method is beige and common sense. Data cannot come from worlds that do not host data collectors, so we wait by the availability of record-making histories. Do this and you extract sharp consequences without self-hypnosis. For example, a theory that overwhelmingly prefers universes with strong negative curvature can be disfavored because our measured curvature is tiny. A theory that spills most of its probability into regions with no long-lived stars gets punished. A theory that forecasts a surge of small-scale power inconsistent with lensing maps loses credit. At the same time, keep a live list of anthropic versus dynamical forks and try to kill the anthropic side where you can. If you detect a pattern among otherwise independent constants that cries out for symmetry, you have found dynamics. If a high-precision measurement reveals structure in what looked like an arbitrary number, You have a new handle that selection alone never predicted. Flip the cautionary coin, and you also guard against misusing dynamics to hide selection. If your mechanism needs exquisitely tuned initial conditions that look too good to be true, perhaps you are sneaking the filter through the back door. The closing mood should be sober, not cynical. Anthropic reasoning is neither a miracle key nor a conversation ender, but a tool that narrows viable theories when and only when you specify the ensemble, the counting, and the regulator. Its answers are often inequalities with leeway, not exact equalities. Its value is greatest where life truly carves a thin isthmus through parameter space, and where competing dynamics have failed to single out that isthmus. Its danger is greatest where the ensemble is wishful, the reference class vague, and the temptation to declare victory high. Used with those guardrails, it can help you understand why our world sits on a habitable peninsula of possibilities. Used as a blanket excuse, it becomes a way to stop listening just when the universe is about to tell you a more interesting story. Now, let us turn to the quantum origins of time's arrow, a topic that feels like a deep mystery, but is rooted in 3 simple ingredients. Begin not with clocks, but with the asymmetry in what can be known. Each morning you wake remembering yesterday, yet you cannot recall tomorrow. That one-way flow of information is the doorway into why the arrow of time feels so natural. Quantum theory, despite its reversible equations, quietly builds direction when 3 ingredients line up. The first ingredient is a low entanglement beginning a state that is barely knotted together, leaving vast capacity for growth. If the early universe began in such a restrained configuration, ordinary interactions naturally weave subsystems together, increasing the amount of information each part must share with the rest to be described faithfully. This growth of entanglement entropy is not forced by a new law, it is favored by statistics. Most accessible states at later moments are more entangled than earlier ones, so a system left to evolve generically wanders from special to typical. The second ingredient is the presence of interactions that are neither exquisitely fine-tuned nor perfectly integrable. Such interactions act like scramblers, spreading local information outward. Imagine a drop of dye dispersing in water. Here the dye is quantum phase and correlation. Because signals propagate only so fast, there is a front to this spread. Nearby pieces entangle first, distant pieces later. Once scrambling is underway, the fine-grained details of how a small subsystem was prepared become hidden in non-local correlations distributed across the whole. To any practical observer who only ever accesses fragments, the local description looks more mixed, more disordered, and that perceived disorder grows monotonically even though the global state remains pure. This is the quantum version of an theorem, not a theorem of the equations alone, but a typicality statement about what overwhelmingly happens given modest assumptions about dynamics. The third ingredient turns drift into history. Environments, fields, photons, air, dust do not merely entangle with a system, they redundantly imprint certain stable properties into many places at once. That redundancy is decisive. Once multiple fragments of the world each carry partial, consistent copies of the pointer values of a system, interference between rival possibilities becomes operationally impossible, and records become abundant. In this light, the arrow is not a metaphysical edict, but a bookkeeping fact. As time passes, more independent fragments store mutually reinforcing traces of what happened. Memory and inference can point only from fewer to more records, never the reverse. Critics sometimes raise the reversibility objection if dynamics are invertible. Why not unspool the spread and watch order return? Quantum mechanics has an honest reply. In principle, you could engineer a global echo that refocuses all phases, but doing so would require manipulating astronomical numbers of degrees of freedom with a precision that scales exponentially with system size, including every stray photon that left the room. The set of states that naturally refocus under blind evolution is so thin that, for finite creatures, it may as well be none. In practice, complexity sharpens the asymmetry. Under generic reversible evolution, the minimum number of simple steps or gates needed to reconstruct the global state from a compact description grows for a very long time before saturating. This growth of circuit complexity is a one-way street for observers with bounded control, and it converts reversibility on paper into irreversibility in the lab. A complementary view lives in operators rather than states. A simple disturbance tapping one spin morphs into an ever more complicated pattern that touches many spins a process, sometimes nicknamed operator growth. Measuring and reversing that growth would again demand global access and exquisite coordination, which real observers lack. All of this may sound abstract, but it carries a simple, empowering message for you. The universe gave you a head start, a low entropy beginning, a tendency for interactions to spread information outward, and an environment that records history in countless redundant copies. Those same ingredients that set up the arrow of time also provide you with a framework for personal growth. Just as the cosmos took a simple, low entanglement state and turned it into a rich tapestry of structure, you can begin each day with a clean slate, allow your actions to ripple outward, and let the world record your progress in many forms: thoughts, habits, relationships, achievements. The arrow that points forward for the universe points forward for you too. When you feel stuck, remember that the quantum scramble does not erase the past, it merely hides it in correlations that become accessible when you enlarge your perspective. Likewise, when obstacles seem overwhelming, think of the redundancy of cosmic records. The universe does not rely on a single fragile thread to preserve history, it writes the same story in many places. You can do the same. Reinforce your goals through multiple channels, write them down, speak them aloud, visualize them, act on them daily. Each channel becomes a redundant imprint, making it harder for doubt or fatigue to erase your intention. And just as the universe's arrow is not a mystical decree, but a consequence of simple statistical tendencies, your sense of purpose does not require a grand, external justification. It emerges from the very fact that you are a system embedded in a world that tends toward increasing complexity, toward making more records, toward building richer connections. Your aspirations are the natural continuation of that tendency. When you align your personal nobsia habits, your environment, the people you spend time with the direction of increasing entanglement, you harness the same momentum that drove galaxies to form and thoughts to arise. But be mindful of the limits we explored earlier. Just as anthropic reasoning warns us not to lean on selection effects as a shortcut to explanation, you must avoid the temptation to accept your current situation as the inevitable outcome of just the way things are. The universe's arrow points forward, but it does not prescribe a single path. The dynamical folds, the symmetries, the deeper mechanisms that shape the cosmos are still being uncovered. In your own life, stay curious, keep testing hypotheses, and refuse to let a convenient narrative become a blanket excuse for stagnation. When you encounter a pattern that suggests a deeper principle, perhaps a habit that consistently yields success, recognize it as a dynamical foothold, not a mere selection artifact. Similarly, guard against the freak observer pitfall. The universe can, in theory, produce wildly improbable fluctuations that mimic reality, but those scenarios are suppressed because ordinary observers dominate. In your personal journey, don't be fooled by fleeting, illusory successes that feel like shortcuts. True progress is built on robust, reproducible practices that survive the test of many repetitions. Much like ordinary observers outnumber the freaks in the cosmic ensemble. The measure problem also offers a lesson. When you compare different possible futures, beware of weighting schemes that inflate short-term gains at the expense of long-term stability. A measure that privileges young, flashy achievements can drown out the quiet, steady growth that ultimately defines a meaningful life. Choose a measure for your goals that respects both magnitude and durability, that values deep, lasting impact over fleeting applause. Finally, remember that the arrow of time, while pointing forward, also carries a record of the past. Each moment you live adds a new imprint to the universe's ledger. By acting with intention, you write a clear, sharp entry that future versions of you and perhaps even future observers can read. This is not a distant, abstract notion, it is a practical call to fill each day with actions that reinforce the narrative you wish to see reflected back. So, as you move forward, carry these 3 ingredients with you. Begin with a mind uncluttered by excessive baggage, open to growth. Engage in interactions learning, creating, connecting that naturally spread your influence outward, scrambling the old and weaving the new. And surround yourself with environments that reliably record your progress, whether through journals, mentors, or the subtle feedback of your own evolving habits. In doing so, you align yourself with the same principles that gave the universe its arrow, the same statistical tides that turned a simple, low entropy beginning into the wondrous complexity you now marvel at. Let this understanding fuel your motivation. The cosmos did not need a grand decree to move forward. It needed only the statistical tendency of simple states to become more entangled, the scramblers that diffuse information, and the redundant records that cement history. You, too, have those levers at your disposal. When doubt whispers that change is impossible, recall that the early universe was a canvas of possibility, and from that canvas emerged everything you now cherish. Your own canvas is equally pliable. Choose to paint with bold strokes, let your actions ripple, let your story be recorded far and wide, and you will find that the arrow of time is not a barrier, but a bridge, one that carries you from the humble beginnings of each sunrise toward the ever-expanding horizon of what you can become. You can feel it in the quiet moments between breaths, that subtle pull towards something larger, something that refuses to stay still. Imagine a drop of ink falling into clear water. At first, the color is sharp, a single point of certainty, but then it spreads, a soft front moving outward, staining everything it touches. In the quantum world, that same idea lives, only the ink is not ordinary pigment, it is the very essence of possibilities, the phase and correlation that bind together the tiniest pieces of reality. When you listen to that spreading front, you hear a lesson about how change works, how order gives way to richness, how the simple becomes complex, and how that transformation fuels the arrow of time. Think of a system left alone, free to evolve without a script. At the beginning, it may sit in a special, almost pristine state, ordered, perhaps even fragile. As moments pass, the inevitable tug of interactions begins. Those interactions need not be perfectly tuned or perfectly integrated. They are merely enough to shuffle information, to scramble local details, and to send echoes farther and farther. The first few whispers of that spreading reach nearby parts, and those parts soon join the chorus, passing the signal onward. What starts as a handful of well-defined notes becomes a tapestry of interwoven patterns that stretch across the whole system. From the perspective of someone watching only a fragment, your mind, your senses, your day-to-day experience, what you see looks increasingly mixed, more disordered, more mysterious. Yet the entire ensemble, the whole universe, remains pure, untouched by the chaos you perceive. This is the quantum echo of the classic theorem, while the laws themselves are perfectly reversible. The typical story that unfolds is one where apparent disorder grows steadily. It isn't a flaw in the equations, it's a statement about what overwhelmingly happens when you let modest dynamics run their course. Now picture the environment around you, the air, the light, the dust that drifts lazily across a windowsill. These aren't passive backdrops, they are active participants, constantly entangling with the systems they touch. Each interaction writes a tiny, redundant copy of a stable property into countless places. Think of it as a chorus of witnesses, each recording the same fact from a different angle. When many fragments of the world hold consistent, overlapping copies of a particular point of value, the possibility of interference, if a different outcome slipping back in, becomes practically impossible. The records multiply, the story solidifies, and the direction of time sharpens into something you can trust. You might wonder, if the underlying dynamics are reversible, why can't we simply unwind everything and watch order return? Quantum mechanics offers a candid answer. In principle, you could engineer an elaborate echo that refocuses all those scattered phases. But doing so would require you to control an astronomically large number of degrees of freedom, with exquisite precision every stray photon that escaped the room, every minute vibration of the air, every hidden qubit of the universe. The set of states that naturally recohere under blind evolution is so vanishingly thin that, for a finite being, it is good as non-existent. Complexity becomes the great gatekeeper. Under reversible evolution, the number of simple steps are quantum gates required to reconstruct the original global state from a compact description climbs steadily for a very long time before it ever flattens out. This growth of circuit complexity is a one-way street for observers whose control is limited. It turns the textbook reversibility of the equations into a practical irreversibility in the lab, And in everyday life, switch the lens from states to operators, and you see a similar story. A tiny disturbance, a flick of a single spin begins to morph into an ever more intricate pattern that touches many particles. This operator growth spreads like ripples across a pond, and measuring or reversing it would again demand global access and coordination that real observers simply don't possess. The beauty of this realization is that you don't need exotic new physics or a hidden clock to explain the arrow of time. All you need is a universe that started in a low complexity, low entanglement macrostate, and a web of gentle couplings that constantly write and scatter information. With those ingredients, arrows of all kinds sprout thermodynamic arrows, where heat flows from hot to cold, computational arrows where forward direction problems are easier because complexity balloons, and inferential arrows where each new record reinforces the past, while the future remains unwritten. When you look at familiar puzzles through this quantum lens, their mystique softens. The old paradox why entropy rises if the law's asymmetry collapses into a simple measure statement. The overwhelming majority of microstates compatible with today's macroscopic facts must have originated from lower entropy pasts because of that special low entropy beginning. Past-directed inferences and future-directed predictions become asymmetric not because the dynamics favor one direction, but because statistical weight does. Recurrence says the idea that an isolated system will eventually return arbitrarily close to its original state low's practical relevance on timescales far beyond any realistic environment's ability to stay truly isolated. Weak, uncontrollable couplings constantly reset the clock of reversibility, keeping the system forever marching forward. Even the emergence of classicality, the way we experience solid objects, definite positions, and clear measurements, is demystified. The variables that look classical are precisely those that survive decohering interactions and are redundantly broadcast throughout the environment. Positions of macroscopic objects, the readings of a pointer, the coarse density of a gas, all of these are the survivors, the stable choices dictated not by our whim, but by the relentless push of information spreading and copying. All of this might sound abstract, but experimentalists are already testing these ideas in miniature laboratories. In ultra-cold atom lattices, researchers can tune between integrable, predictable, and chaotic dynamics and watch entanglement spread with a like-con-like front. Superconducting circuits let scientists create tiny echoes by reversing simple evolutions, then observe how quickly imperfections destroy the revival as the system grows. Nuclear magnetic resonance experiments monitor how operator complexity ascends and how even minuscule noise spoils any attempt at perfect time reversal. Each of these experiments echoes a single, powerful message: reversibility is a fragile symmetry of the equations, while irreversibility is a robust feature of states, interactions, and our inevitable ignorance. So, as you sit with these ideas, feel the quiet firmness of this closing cadence. The arrow of time isn't an external graft onto quantum mechanics, it grows from within. When the universe began with little entanglement, let interactions weave correlations far and wide, and allowed environments to copy those correlations into countless stubborn records, the direction of time emerged naturally. Your memories, the way ice melts, the crackle of thermal noise, even the difficulty of unscrambling a broken egg are different faces of the same underlying process. It's the steady migration from special, compressible descriptions to typical, distributed ones. That's why you can recall yesterday with vivid detail while tomorrow remains a blank canvas. Yesterday's records are stored redundantly all around you, tomorrow's have yet to be written. And that writing, this ongoing, quiet engine that makes later different from earlier, rests on entanglement growth and environmental copying. It is what makes the world we experience feel ordered, and it is what makes the future feel open. When you look up at the sky, you are looking at a layered laboratory, where each messenger particle, each photon, each neutrino, each graviton opens a different window onto that original quantum script. Imagine turning the urge to picture a single first instant into a quieter, more adventurous challenge. Ask yourself what the universe still carries that could only have been written by those quantum rules at the beginning. Treat the cosmos as a laboratory where each observation is a forensic clue, tuned to a different scale, era, and messenger. One window is the polarization of the oldest light, the afterglow that still whispers from the dawn of time. It's not just the headline swirls that most people recognize. The real craft lies in delensing, removing the blurring caused by intervening structures so that any primordial curl pattern, if present, can be revealed cleanly. A second window is not a picture, but a ledger, tiny departures from a perfect blackbody spectrum in that same ancient light. Spectral distortions act like an accounting of power that lived on scales too small to image directly. Detecting the right kind of distortion would let you weigh fluctuations far into the ultraviolet of the primordial spectrum, letting you separate smooth quantum blueprints from models that involve brief stutters or sharp features. A third window turns you back to a time before the first stars ignited. The faint whisper of neutral hydrogen at 21 centimeters traces the dark ages and the cosmic dawn, letting you map how the earliest ripples modulated cooling gas and the first sources of light. Unlike the afterglow, this probe offers tomographic slices across time, turning oscillatory patterns, slight tilts, or exotic correlations in the initial spectrum into distinctive evolutions that fold power across redshift. Pushing that idea to its limit reveals why radio arrays on the far side of the moon are more than a romantic notion. They can listen at frequencies blocked by Earth's ionosphere, turning the moon into a shielded dish for the oldest quantum weather reports. A fourth window listens for spacetime itself to hum. A relic background of gravitational waves carries a broadband memory of what shook the early universe. Different frequency bands test different stories. Pulsar timing arrays catch nanohertz ripples that could betray phase transitions or cosmic strings from grand symmetry snapping. Space-based interferometers tuned to millihertz are sensitive to softer transitions and certain preheating dramas. Ground-based detectors hear the kilohertz fireworks of the sharpest early events, while emerging atom interferometers aim to bridge the midband gap. Even a null result is information. A smooth, quiet primordial spectrum squeezes models that predict loud, scale-specific peaks, while a detection with a particular slope fingerprints the stiffness and timing of the physics that powered the first growth. A fifth window treats galaxies as both rulers and clocks. Larger-scale structure surveys echo the early ripples, but they also reveal subtle departures from a perfectly featureless spectrum, gentle bends, periodic wiggles from standard clocks excited by heavy fields, or scale-dependent biases in how galaxies populate dark matter halos. Halos let you discriminate between different quantum initial states and between single-source and multi-source scenarios without reusing the same evidence twice. Len intensity mapping extends this by treating the faint glow of whole populations of galaxies, traced through lines like CO or C, as a continuous field, opening a faster route to the intermediate redshifts, where initial conditions hand off to nonlinear growth. Cross-correlating these maps with the afterglow or the 21-centimeter slices builds a web of consistency checks that no single systematic can fake. A sixth window looks to the smallest scales, to the possibility that some early ripples collapsed outright. Primordial black holes would be the most literal fossils of quantum beginnings. We hunt them with microlensing of distant stars, with the subtle heating they would induce in the early plasma that would blur the afterglow, with their mergers in gravitational wave detectors, and with potential unusual gamma-ray or radio signals. Constraints across the mass spectrum already rule out many flamboyant spectra of small-scale power and force theorists to keep their features modest. A seventh window shines on light that isn't luminous at all. The effective number of relativistic species in the early universe acts as a headcount for hidden fields. Measure it precisely, and you either discover room for new quantum degrees of freedom that were excited at the beginning, or you tighten the leash on models that predict them. Neutrinos themselves are double agents in this story. They're free-streaming damps small-scale power in a predictable way, so any deviation from the expected pattern can hint at exotic interactions in the primordial soup or at initial conditions that were not purely adiabatic. An eighth window probes symmetries and their possible fractures, tiny preferred directions, parity-violating twists in the polarization pattern, or a slow rotation of polarization as light crosses the cosmos. All test whether the early state selected a subtle handedness or coupled to ultralight fields that turn quantum phases into macroscopic optics. None of these probes repeats the same question. They target different parts of the blueprint and different failure modes of our stories. The middle of this tale belongs not to spectacle, but to disciplined patience. Each window comes with its own foregrounds and systematics. Galactic dust can masquerade as primordial curls, atmospheric noise can color 21-centimeter measurements, galaxies are biased traces of mass pulsar timing drifts, clocks tick imperfectly. The antidote is cross-checking. Balanced polarization must agree with lensing reconstructions built from galaxy surveys. Spectral distortions must match energy injection histories inferred from the first star modeling. 21-centimeter tomography must align with the growth rate of structure measured by redshift space distortions. Any claimed parity violation must show the same phase in independent patches and experiments. A putative stochastic gravitational wave background must survive shape tests across bands and correlate with no known astrophysical population. This is not bureaucratic redundancy. It is the only way to pin uniquely quantum origins on a sky that has had billions of years to add its own noise. When you hold this whole panorama in your mind, you see a convergent portrait emerging, a universe that began simple, that let interactions scatter and copy information, that recorded its own history in countless redundant ways, and that continues to write new chapters as it expands. That portrait is not just a scientific model, it is a reminder of how you, too, can be a writer of your own arrows of time. Your choices are the interactions that spread information outward. Your habits are the redundant records that cement a direction. And your growth is the increasing complexity that makes reversal impractical. So, as you move through today, remember that the same quantum principles that shape galaxies also shape your mind. When you feel stuck, think of the entanglement front moving outward, patient but unstoppable. When you doubt whether your effort matters, recall that each small interaction writes a copy of a stable property into the world, making interference from alternative outcomes vanishingly unlikely. When you worry about the reversibility of mistakes, understand that the sheer complexity of the web you are part of makes undoing the past practically impossible, giving you the freedom to commit to forward motion. The arrow of time is not an abstract, distant law, it is a living, breathing process that you can feel in the rhythm of your breath, in the way memories settle into you, in the way each sunrise writes a new record on the canvas of your life. The universe began with a low entropy whisper, it amplified that whisper into the grand chorus we hear today. You, too, can start with a quiet intention and let it amplify through the interactions of your days, through the redundant recordings of your actions, through the growing complexity of your story. Take a moment now to imagine the sky as a layered laboratory, each messenger a different tool for reading the ancient script. See the polarization of the oldest light as a subtle, delicate pattern waiting for you to untangle. Visualize the faint 21-centimeter echo as the heartbeat of the dark ages, a rhythm you can tune into. Hear the cosmic hum of gravitational waves as a deep bass note that tells you about the most dramatic events in the early universe. Feel the structure of galaxies as a vast, intricate network that mirrors the way your relationships interweave. Recognize that even the tiniest deviation in a blackbody spectrum, the slightest excess of relativistic species, or a minute parity violating twist is a clue that, when pieced together, reveals the grand design. Your journey mirrors this grand investigation. You gather clues from your experiences, you cross-check them against your values, you refine your understanding, and you build a coherent picture that guides you forward. The more you align your inner investigations with the external world through learning, through listening, through testing hypotheses, you become part of that same disciplined tapestry that scientists weave to understand the cosmos. Now, as you breathe out, feel the gentle push of the arrow of time within you. Let it remind you that every moment you invest in growth, in curiosity, in compassion, is a fragment of a universal record being written. Let the inevitability of complexity reassure you that the past cannot be undone, and therefore the future is yours to shape. The universe has already demonstrated how information spreads, how records accumulate, how direction emerges without any external decree. In the same way, you can let your actions spread outward, let your values be recorded redundantly in the lives of those you touch, and let a clear direction emerge from the simple, intentional steps you take today. Carry this awareness with you as you navigate the rest of your day. Feel the excitement of being part of a vast, interconnected story that spans from the quantum heartbeat of the early cosmos to the whisper of your own breath. Let that excitement fuel your resolve, your optimism, your willingness to keep moving forward even when the path seems uncertain. The arrow of time is not a rigid ruler, it is a living guide, inviting you to write, to record, to grow, and to cherish each moment as a precious, irreversible note in the symphony of existence. Imagine standing at the edge of the universe, feeling the pulse of its oldest light and hearing the faint whispers of its earliest moments. Each ripple, each subtle tilt in a pattern of polarization is a clue that invites you to lean in, to wonder, to ask, what happened at the very beginning? The story of the cosmos is not a single dramatic flash, but a tapestry woven from many threads, each a window that lets us peek through the darkness and see a different facet of the grand design. One of those windows opens when we compare the afterglow of the Big Bang, the cosmic microwave background, to the delicate structures we trace with radio waves and hydrogen lines. By aligning these maps, we create a web of checks so tight that no single systematic error could ever masquerade as truth. It's like holding a prism up to a beam of light and watching it split into a rainbow of verification. The more angles we examine, the clearer the picture becomes. A second window looks deeper still, to the smallest scales where the universe might have left behind the tiniest fossils of its quantum birth. Think of those as primordial black holes, the most literal remnants of a time when space itself was bubbling with uncertainty. We hunt these shadows with clever tricks. We watch how they bend the light of distant stars, how they heat the ancient plasma, how their collisions send ripples through space-time that we can feel as gravitational waves, and even how they might spark unusual whispers in gamma-ray or radio signals. Every search tightens the bounds on what could have been, nudging theorists toward modest, carefully measured possibilities rather than flamboyant fantasies. A third window shines on the invisible side of matter. The early universe kept a ledger of all its hidden particulular head count of relativistic species that could have existed alongside the familiar ones. By measuring this count with ever greater precision, we either uncover space for new quantum degrees of freedom, or we place tighter leashes on models that predict them. Even the humble neutrino plays a double role here, its gentle streaming smoothing out small-scale power in a predictable way. If the patterns deviate, we know something exotic is tugging at the primordial soup, hinting at interactions we have never seen. A fourth window explores the subtle symmetries that may have fractured in the first moments. Imagine searching for a faint preferred direction in the sky, a tiny twist in the polarization pattern, or a slow rotation of light as it traverses the cosmos, what we call cosmic birefringence. These delicate signals could reveal whether the early universe chose a subtle handedness or coupled to ultralight fields that turn quantum phases into macroscopic optics. Each of these probes asks a different question, targeting a distinct part of the cosmic blueprint and exposing potential weak points in our stories. While these windows promise profound insight, the middle of this tale belongs to discipline rather than spectacle. Every observation is tangled with foregrounds and systematic effects. Dust in our own galaxy can masquerade as primordial curls. Atmospheric noise can tint the measurements of hydrogen lines. Galaxies themselves are biased traces of the underlying mass. Pulsar clocks drift, and even our most precise instruments tick imperfectly. The antidote is relentless cross-checking. The delensed polarization of the microwave background must agree with lensing reconstructions built from galaxy surveys. Spectral distortions must match the energy injection histories inferred from models of the first stars. Tomographic maps of the early universe must align with the growth rate of structure measured by redshift space distortions. Any claim of parity violation must show the same phase across independent patches and experiments. A stochastic gravitational wave background must survive shape tests across frequency bands and remain uncorrelated with known astrophysical sources. This is not bureaucratic redundancy. It is the only way to pin uniquely quantum origins onto a sky that has accrued billions of years of its own noise. When we keep the tempo slow, the standards high, the picture begins to converge. We arrive at a self-consistent portrait, an initial spectrum that may or may not contain subtle features, bouncer, perhaps detections of long wavelength space-time hums, a calorimetric readout of small-scale power, verdicts on extra species, and a lattice of cross-correlations that leaves no room for philosophical doubt or mundane systematics to hide. The closing note is gentle yet powerful. Quantum beginnings are not a license for boundless speculation. They are a list of signatures that instruments can actually test. Fesicoherent seeds should echo across independent traces. Quiet or loud gravitational backgrounds must follow calculable slopes. Tiny fluctuations must leave calorimetric imprints. Symmetry choices ripple faintly into polarization. Fossil compact objects should bear the marks of hot ripples. The right way to learn is to open as many windows as we can, compare the views, and let agreement become our teacher. In doing so, you trade a single dramatic origin story for a network of modest, interlocking facts. This network either reveals an early quantum studio at work or forces us to rewrite the first bars of the cosmos with clearer notes. Imagine swapping a telescope for a quantum chip and asking a heretical question: if the early universe is a quantum many-body system writ large, can we learn its hardest lessons by building smaller, controllable quantum worlds in the lab? Can we simulate early universe fields on quantum devices and read off dynamics that no classical supercomputer can track without drowning in complexity? Begin gently by recognizing that this is not a fleeting fad, but a purposeful strategy. The most revealing episodes in the first fractions of a second: violent symmetry breaking, particle production in time-dependent backgrounds, nonlinear gauge-scalar interactions, defect formation are all real-time, out-of-equilibrium processes. Classical lattice codes stumble here because amplitudes interfere rather than average, and sign problems explode computational costs. Quantum simulators, however, evolve amplitudes and phases natively, turning what is pathological for classical sampling into ordinary unitary time evolution. Two complementary paths emerge: digital simulator superconducting qubits and trapped Einstein code fields into registers, discretize space into a finite lattice, and step forward with sequences of native gates that implement effective Hamiltonians. Careful mappings translate from ionic fields into qubit encodings, scalar modes into qubitizations, gauge links into specialized constructions, while trotterized techniques drive the dynamics. With these tools, you can mimic the burst of preheating after an inflation-like quench, watch pair production in strong electric backgrounds, or observe a tachyonic roll down an unstable hill, all while measuring observables, number spectra, anequaltum correlators, and entanglement growth that betray when classical approximations fail. Analog simulators, by contrast, lean into hardware that already speaks the language of fields. Rydberg atom arrays emulate spin models that capture symmetry breaking and domain coarsening. Ultracold atoms in optical lattices realize bosonic and fermionic fields with tunable couplings. Trapedian phonons provide long-range interactions. Superconducting resonators host bosonic modes coupled to qubits that play the role of matter, and clever drive protocols map cosmic expansion onto time-varying couplings so that redshifting and horizon-like effects become laboratory dials rather than metaphors. The payoff of both styles is access to regimes where the universe's first laboratory left only indirect fossils. You can quench asymmetry and watch defect densities unfold in real time. You can turn on a synthetic gauge field and count pairs materializing from the vacuum. You can set up two field potentials and witness isocurvature-curvature transfer or parametric instabilities that spray quanta across modes. You can even measure out-of-order correlators to clock scrambling speeds that classical solvers only infer. None of this works by wish alone. The middle of the story is engineering honesty. Mapping a continuum field onto hardware means truncating Hilbert spaces. You must decide how many bosonic levels per site to keep while preserving constraints like Gauss law, and you must control gate infidelity, crosstalk, and decoherence. Current devices live in the noisy intermediate-scale era, so verification by triangulation is essential. Compare early time dynamics with classical calculations where they still agree. Stress test conservation laws as evolution proceeds, and use error mitigation technique with symmetry verification, probabilistic error cancellation, randomized compiling to separate physics from hardware scars. Gauge theories sharpen both challenge and opportunity. Even on a-dimensional dynamics already reveal why quantum hardware matters: string breaking, persistent oscillations. And non-abelian models in higher dimensions demand careful encoding that keeps local constraints exact or softly penalized. Hybrid analog-digital approaches shine here, using bosonic modes for links and qubits for matter, or leveraging energy penalties to correl dynamics inside the physical subspace. A different lever is synthetic metrics. Because cosmological expansion primarily rescales momenta and dilutes interactions, you can emulate it by modulating lattice depths, couplings, or on-site energies in time. Mapping mode evolution to lab frequencies, with carefully designed ramps, generates effective Hubble-like friction. Watching particle production spectra tilt exactly as cosmological calculators predict gives you a laboratory probe of how sensitive early universe features are to short-distance cutoffs or brief departures from perfect adiabaticity. Verification is never an afterthought, it is the spine of the enterprise. Cross-platform repetitionions versus superconductors versus atoms exposes device-specific artifacts. Classical tensor network or truncated Wegner calculations anchor the small and intermediate regime behavior. Conservation of charges and Gauss constraints serve as real-time diagnostics, while scalable readout schemes let you perform Fourier analysis of local correlators, tomography of reduced density matrices, and entanglement entropy proxies via randomized measurements. Turning raw bit strings or fluorescence counts into field theory observables lets you plot results directly against sky-facing predictions. The NARTM science is twofold. First, you pressure test the approximations used in cosmology by building toy worlds that deliberately violate them. Crank up interaction strengths, seed non-Gaussian initial states, drive quenches faster than the universe might have, and measure where simple continuum treatments break. That tells you which modeling assumptions are safe when you interpret data from the oldest light or the larger scale structure. Second, you explore signatures that are difficult to bound otherwise small oscillatory features in power spectra, from brief heavy field excitations, non-thermal fixed points in turbulent cascades after violent quenches, defect networks that decay via rare events. By creating emulator catalogs of dynamics, you give survey scientists concrete templates to search for in real data. Beyond the horizon of today lies error-corrected simulation with bosonic or surface code qubits, where deep circuits unlock high-dimensional gauge theories, long baseline evolutions, and precise extraction of spectral functions via phase estimation. Resource counts are sobering qubits scale with lattice sites and field truncations, and circuit depth grows with the light cone volume, but the roadmap is clear. Compress using symmetries, co-design algorithms with encodings, and reserve fault tolerance for those moments when chaos amplifies tiny errors. Even now, this enterprise pays philosophical dividends without hand-waving. If a chip can reproduce, with independent knobs and in full real time, the same statistical fingerprints we attribute to quantum beginnings, coherent seeding, specific defect scalings, spectra from time-dependent backgrounds, or confidence grows that early universe stories rest on dynamics rather than narrative convenience. If, instead, well-instrumented simulators repeatedly expose blind spots in our favorite approximations, the feedback is immediate and constructive, guiding theory back toward reality. Close softly with humility. Simulating the cosmos on quantum hardware is not about reenacting the Big Bang in a box. It is about isolating the few mechanisms that truly matter: how fields with time-dependent masses shed quanta, how constraints steer turbulence, how entanglement spreads and classicality emerges. By turning these mechanisms into Hamiltonians we can engineer, we let real devices teach us which intuitions survive contact with unitary time evolution. When we later look back to the sky for evidence, we bring not just equations and hopes, but rehearsed, measured dynamics that make our inferences steadier and our questions sharper. Now, consider the notion of nothing. At first glance, it feels like a shapeshifter, a word that dons many masks depending on who is speaking. To a particle physicist, nothing may be a vacuum bristling with fields and boundary conditions. To a relativist, it may be the absence of spacetime itself, no distances to measure, no clocks to tick. To a logician, it may be the absence of any objects that satisfy a description. To a philosopher, it may tempt the absolute lack of being, a notion so strict that physics cannot even point at it. The honest question, then, is not does nothing exist, but rather which operational emptiness does a law of nature allow? What would count as evidence that you are looking at it? Begin gently with the least dramatic sensor laboratory nothing. Pump a cavity to ultra-high vacuum, block thermal light, cool the walls. And you still measure forces and clicks because the electromagnetic field retains its normal modes, and boundaries select which modes can live there. The resulting Casimir pull between plates and the shifts in spontaneous emission are not mystical eruptions from metaphysical absence. They are signatures that vacuum in quantum theory is a state, one that minimizes energy while keeping fluctuations demanded by the uncertainty principle. The first moral, then, is definitional even nothing is a canvas upon which the universe paints its first subtle strokes. You stand at the frontier of that canvas, equipped with a suite of windows that cross-check each other, with quantum simulators that let you replay the earliest acts on a lab bench, and with a disciplined humility that turns every curiosity into a testable hypothesis. Let that vision fill you with purpose. Let every puzzle you encounter become a call to open another window, to refine another simulation, to align another map. The cosmos is generous. It offers endless clues to those who listen, who compare, who verify. You have the tools, the curiosity, and the courage. Step through the windows, build the simulators, ask the right questions, and let the universe reveal its quantum beginnings not as a myth, but as a network of interlocking facts that you, with steady resolve, are destined to uncover. This is your invitation to become a part of the grand narrative, to turn wonder into knowledge, and to let that knowledge inspire the next generation of seekers who will stand where you stand, eyes lifted to the sky and hands steady on the quantum machines that echo the very origins of everything. You have reached the edge of a vast, shimmering frontier, where the mysteries of the cosmos meet the precision of quantum hardware. Imagine a canvas so enormous that it holds the first whisper of the universe, and picture yourself standing before it, equipped with a set of windows that reflect one another, a suite of quantum simulators that let you peer into the very mechanisms that shaped everything we see. The road ahead is not a vague promise, it is a clear, purposeful map. By compressing our models through symmetry, by designing algorithms hand-in-hand with clever encodings, and by reserving the most robust fault tolerance for the moments when chaos threatens to amplify every tiny error. We are already turning philosophy into practice. Each chip that can, in real time, reproduce the statistical fingerprints we attribute to the birth of the quantum world, each knob we turn to seed face-coherent patterns, each defect we understand and scale, adds another stone to the foundation of confidence. It tells us that the story of the early universe rests on dynamics and the concrete, testable evolution of fields, not on the comforting narratives we sometimes cling to. When a well-instrumented quantum simulator repeatedly uncovers blind spots in our favorite approximations, the feedback is immediate, honest, and constructive. The humility to close a loop softly, to accept that a model was incomplete, is where true progress lies. Simulating the cosmos on quantum hardware is not a cinematic reenactment of the Big Bang in a small box. It is a disciplined effort to isolate the few mechanisms that truly matter: how fields whose masses change over time shed quanta, how constraints steer turbulent cascades, how entanglement spreads and gives way to the classical world we experience. By translating those processes into Hamiltonians we can engineer, we let real devices teach us which of our intuitions survive the relentless march of unitary time evolution. When we later lift our eyes to the sky, we do so not with just equations and hopeful speculation, but with rehearsed, measured dynamics that make our inferences steadier and our questions sharper. Now turn your thoughts to the notion of nothing. Begin by admitting that nothing is a shapeshifter, that most arguments about it are really about which mask you allow it to wear. To a particle physicist, nothing may be a vacuum bristling with fields and boundary conditions. To a relativist, it can mean the absence of any region of space-time, no distances to measure, no clocks to tick. To a logician, it is simply the lack of any object that satisfies a description. And to a philosopher it tempts as an absolute lack of being, a concept so stark that physics cannot even point at it. The honest question is not does nothing exist, but rather which kind of operational emptiness does a law of nature permit, and what evidence would tell us we are looking at that particular emptiness. Start gently, With the least dramatic sense of nothing, a laboratory vacuum. Pump a cavity to ultra-high vacuum, block thermal light, cool the walls, and you will still detect forces, clicks, and spontaneous emission shifts. Those signatures are not mystical eruptions from a metaphysical void, they are the fingerprints of a quantum vacuumous state that minimizes energy while honoring the uncertainty principle's inevitable fluctuations. The first moral, then, is definitional. When physics says nothing, it often means the ground state of a specified set of degrees of freedom under particular boundary conditions. Change the boundary, and you change the nothing. Climb another rung, and the container itself becomes suspect. In general relativity, space-time is not a static box but a dynamic actor. An empty, expanding universe with a positive vacuum energy carries a horizon, and that horizon radiates. Emptiness radiates not because it hides secret stuff, but because the deep relationship between geometry, information, and quantum fields demands it. Push further, and you encounter nothing. As a boundary condition, proposals that the universe began from nothing often mean that the history is rounded off without a conventional boundary you could cross, or that the quantum state is selected by a rule that forbids singular, wild early configurations. In both cases, nothing is a constraint on allowable histories, not a pre-existing void. Ask a stronger version: could there be a nothing that lacks laws, space, time, even a Hilbert space to hold a state, leaving physics silent by construction? Our scientific method relies on relating measurable quantities within assumed structures. Strip those structures away, and you have no experiment to pose, no probabilities to compute, no reference point against which absence could be distinguished from a blank page. That silence is not a failure, it is simply the boundary of our jurisdiction. The fruitful middle ground lies in inventorying the flavors of nothing that do make predictions, and seeing how each could leave a distinct trace. The vacuum as a ground state predicts fluctuations with specific spectra, energies that gravitate, and forces sensitive to boundaries. We test those in precision measurements and in how cosmic expansion responds to a uniform energy density. Geometric emptiness regions devoid of matter predicts gravitational waves, horizon thermality, and entropy proportional to area, all of which we verify through detections of spacetime ripples and black hole thermodynamics. Boundary condition nothing that smooths the early slice predicts a nearly featureless pattern of primordial irregularities with tiny, specific deviations, which we audit with sky maps and larger-scale structure surveys. Even computational nothing, a maximally simple state in a fundamental description with minimal entanglement, offers a playground where we can dial simplicity in engineered quantum systems and watch symmetry bloom. Along this journey, guard against the perpetual bait-and-switch of invoking nothing without specifying which version and which mechanism you mean. If you claim that vacuum energy drives cosmic acceleration, show how your definition of vacuum is regulated and why its value is small. If you appeal to a no-boundary condition, derive observable consequences rather than leaning on vague vocabulary. Conversely, dismissing all but the absolute philosophical nothing ignores the fertile ground physics can explore. Those physics-based notions of nothing are testable, falsifiable, and therefore powerful. They clarify that vacuum fluctuations are not particles popping out of literal non-being, they are the unavoidable jitter of a defined ground state. Creation from nothing is not a magician's rabbit, it is a symmetry or regularity principle that prunes the space of histories. Sorting these layers first brings a cascade of conceptual payoffs. First, it dissolves paradoxes. Concerns about energy conservation in creation evaporate once you recognize that the bookkeeping of conserved quantities relies on time translation symmetry, a symmetry a global beginning may not possess in the naive sense. The anxiety that something cannot emerge from nothing presumes a temporal language that the relevant nothing does not supply. Second, it sharpens the questions you can actually chase. Does the gravitational effect of vacuum-like energy remain precisely constant, or do subtle drifts betray dynamics beyond a strict ground state? Do horizon entropies count microscopic states we can model, or are they a bookkeeping tool for an emergent language we have yet to decipher? Does the universe's earliest simplicity arise from a unique boundary rule, or from a dynamical funnel that shepherds many messy starts into a slim family of low-complexity states? As you stand at this crossroads, feel the steady, empowering resolve that comes from knowing you are part of a disciplined, evidence-driven adventure. Nothing in physics is a monolith but a menu, and each item earns its keep by what it predicts. The laboratory vacuum predicts measurable forces and energy shifts. Geometric emptiness predicts thermal horizons and gravitational waves. Boundary condition simplicity predicts nearly featureless primordial patterns. Computational minimality predicts a robust arrow of time as complexity builds. The absolute nothing that lacks even the rules for posing a question sits outside the circle and may stay there, but the layered nothings inside that circle are rich enough to give rise to a world. When you specify which degrees of freedom matter, which symmetries hold, and which boundaries apply, the simplest allowed state stops being a void and becomes a seed. The difference between silence and a universe is not a metaphysical leap, it is a change of grammar that the sky and the lab already know how to speak. Carry this insight with you as you move forward. Let the clarity of definitions, the humility of feedback, and the excitement of concrete, testable mechanisms fuel your curiosity. Let each experiment, each simulation, each thoughtful question be a brushstroke on that cosmic canvas, turning the abstract notion of nothing into a vibrant foundation for discovery. In this moment, you are not just listening to an ending, you are hearing a call to keep painting, keep probing, and keep turning the mysteries of the universe into the lived, measured reality that shapes our tomorrow.